Okay, so today I would like to tell you about some correlation between superconducting state property and crystallinity degradation in iron-based superconductors. So my presentation will be concerned not only two simplest example of iron-based superconductors. It is so-called 1,1 and 1,2 superconductor. The outline of my talk is presented here, so I will start with to show you some correlation between inhomogeneity and superconducting state properties in rubidium, iron, selenium superconductor. And later on, I will switch to iron, selenium, tellurium superconductor, and I will describe you correlation between superconducting state properties in these materials. And just this disorder, it will be introduced just by changing of crystal growth properties or by applying hydrostatic pressure or by hydrogenation of the material. So let's start from the beginning. So if you have a material like 1 to 2, this material is basically inhomogeneous, and you have just some kind of crystals or phases like this phase or like this phase. And all of this concerns single crystal. This is just a description how the crystal was grown. And why is it? It is. If you are looking for differential scaling calorimetric data at this temperature above 500 Kelvin degree, there is a structural transition. Above this temperature, this different structure than below, and this structure is responsible for superconductivity. Nevertheless, there is some phase temperature below 500 Kelvin when appear phase separation. And below, in this area, there is one phase, but below this area, there is a phase separation. So if you anneal sample for a long time in this temperature, you can get different phases in the material. Here, there is just a crystal which was grown in standard way, and this is crystal which was annealed for a long time after growing. So this is scanning transition electron microscopy image. You can see differences in this image. So just our idea was to check if how the superconducting properties will be changed in such a way. And this is just several of examples of magnetization curve versus temperature in low magnetic field for the sample which was unannealed and annealed for a certain time. This is initial magnetization curve, and here this is upper critical field determined by resistivity measurements. And so all of this data show improvement of superconducting state properties after annealing. So we wanted to correlate what really happens in structure. And yesterday it was shown that how useful is you can be muon spin relaxation measurement. So here there is just you know very well already how muons work. Basically, muons can just check how homogeneous or how homogeneous is magnetization inside of the sample. And so this is a sample which was annealed, and this is samples which was annealed. And this sample has much better superconducting properties. But if you are looking for these samples, the magnetic field distribution in these samples is much more homogeneous. So at that time, it was about, we performed this experiment about 10 years ago, and we concluded that mu-SR measurement and scanning transition microscopy measurement indicate that if the sample is more homogeneous, it has a much better superconducting properties. However, this is sample which is quite inhomogeneous, not single phase screening. It is not full superconducting, because if you are looking screening properties of magnetic field is only a few order of 10%. So we decided to just to study if we can just get similar data to this data for the sample, which is very simple, iron, selenium, tellurium. Phase diagram, it is like this, and just if you start with iron, tellurium, which is non-superconducting, and if you start to increase selenium content, sample became superconducting. In AC susceptibility or DC AC susceptibility is given here, and depending on the content of selenium versus tellurium, transition temperature is changed in this way. The highest transition temperature is for the samples with it is 0.5, 0.5. Nevertheless, the best superconducting properties indicate samples which is about 0.65 tellurium. This is almost ideal from crystallographic structure superconductors. What means almost ideal? It is picture is given here. You have tetragonal host lattice, and in this tetragonal host lattice still you have some hexagonal phases. But the amount of this hexagonal phases is very small. You can find somewhat of such phases in the samples, but they are very, very limited. And this is a single crystal material. But if you grow single crystal materials, you can play with grow velocity. And if you play with grow velocity, basically you can get crystals which have slightly different structure. You can see here X-ray diffraction peaks. The difference is in the width of some X-ray diffraction peak. For example, this peak, which is 004, the width of this peak can vary between 1.67 minute and 6 minutes. So you can see. And here there is just AC susceptibility of the crystals. This crystal is grown very fast, and this crystal is grown extremely slow. And you can see a huge difference in AC susceptibility data. There is also difference in calorimetry in heat capacity data. Here the peak is very well developed. Here is not as well developed. And if you try to correlate the superconducting state properties with the width of this peak, 004, you can get a correlation like this, that superconducting state properties are very good for the samples with a very wide peak. So the situation is like this, that if the crystal is grown very slow, very fast, the structure is like this, there is huge amount of these hexagonal phases, but they are extremely small and they are homogeneous in distribution. If the crystal is growing very slow, the hexagonal phases are much better developed, but they are much bigger. So the boundary between these phases, the amount of that boundary between these phases is much smaller. So for the crystal which is grown very fast, this peak are very wide. Here the peaks are very narrow, but superconducting properties of these phases are much better. So this is again in extended scale as it was shown in the previous page. So we concluded that if you have a crystal which is inhomogeneous, the superconducting properties are much better. It is important to check, because it is AC susceptibility measurement or magnetization measurement. Is important to check if it works also for the transport. This crystal is grown very fast. This crystal is grown very slow. So this crystal has a wide X-ray peak. This crystal has narrow X-ray peak. This is just structure. And a few years ago, we published this paper about microstructure of these materials. And it was done just some kind of bridges, and current was measuring along these bridges. So this crystal, which is grown with very inhomogeneous crystal, is also characterized by extremely high critical current. The crystal, which has very high crystallographic quality, it's show very slow critical current properties. This is width of hysteresis loop. Nevertheless, if you take some material with the ages of this crystal, which is very good, it is something between. So if you have materials which is more worse crystallographic quality, it starts to show better superconducting state properties. This is just a scaling showing that the scaling is similar, and this is critical current versus temperature. All of this data are consistent. So we decide to, so we know that if we have crystals which are grown in various way, we can just make better superconducting state properties and worse superconducting properties depending on the growing condition. The problem is that if we can change this superconducting properties in a reversible way, and in order to check in a reversible way, we can apply hydrostatic pressure, or we can hydrogenate materials. After hydrogenation, we can remove hydrogen. And here, by applying pressure, we can remove pressure. And it is well known from many years that under superconducting pressure, under pressure, all of superconducting properties are improved. So here it is, for example, just shift of transition temperature. This is for two crystals. One crystal was grown with a higher speed, another was grown with a slower speed, but doesn't matter. In all of the case, transition temperature increase. There is improvement of HC1, improvement of penetration depth. The crystal is moved on in Uemura plots too. Here there is just summary of the data, including HC1 and coherence length, and you can see that this is crystal without applied pressure, and this is crystal with applied pressure. And this data are concerned particular crystal 0.5, 0.5. But if you perform this experiment with a crystal with 0.65, 0.35, you will get similar data. And here there is just some summary of the data obtained for several crystals. You can see that under pressure you have improvement of superconducting state properties. So the question is, what happens with X-ray data? What happens with structure under pressure? Here there is just map of 001 peaks, and this is the data without pressure, and this data under applied pressure. And if you make contour map of this peak, you can find a situation like this, that without applied pressure, the situation gets like this. Under applied pressure, the peak became like this. So the peak became wider under applied pressure. This material became less homogeneous, not homogeneous. And still you have correlation between homogeneity of the material and superconducting state properties. So the paper was published in 2 years ago, and we just concluded that there is announcement of superconducting properties, and this is correlated with crystallographic quality. But still, this is just pressure, just mechanical shift. So let's check what will happen if we try to hydrogenate materials. And this is the, again, iron selenium tellurium. This is crystallographic data, and the material is hydrogenated by annealing in this temperature for certain time. The temperature, maximum temperature is about 200 Celsius degree, and this is annealing time is a few hours. This is evolution of X-ray peak. And again, after this hydrogenation, this X-ray peak became wider and wider. And here there is just data for AC susceptibility. Okay, this measured by DC method, so susceptibility, DC susceptibility. And here there is a shift of transition temperature of hydrogenated materials, improvement of critical current under as a result of hydrogenation. Here there is data from EPR and showing that there is shift of transition temperature as a result of hydrogenation. And it was published in December 2021, and we concluded here that for the sample which is hydrogenated, and it shows destroying of crystallographic property, we observe better superconducting state property. So the final conclusion it is like this, that in all of the studies, iron-based superconductors, we have just correlation that high crystallographic quality, it is bad superconducting state properties, and vice versa. If you want to have materials with good superconducting state properties, it should be very bad superconducting state. This should, if you want to have very good superconducting state properties, it should be very bad crystallographic quality. This data was done in the Institute of Physics mainly, but it was done in collaboration with Jagiellonian University. Dariusz Paliwoda was from, Damian Paliwoda was from Jagiellonian University, and it was done also with low temperature physics institute in Ukraine. And so the authors are from this institute and also Institute of Physics of the Czech Academy of Science. This the Ukrainian institute is from Kharkov. Thank you very much for your attention.
Dan, thanks a lot. We have time for one question. Well, he was quite. Do you have a question?
But we can go to the next speaker because we have a connection with the.
Okay. Okay.
Because I'm asked
To shrink. Yes, I understand.
I do my best.
No, you were perfect in time. Actually, quite fast. Okay.
I can't share the screen.
Try now.
Yes, now it should work.
Okay.
Okay, it works.
Yeah.
Should I go ahead or?
Yes, yes.
Yeah. Okay.
Yes, yes, you can start.
Okay, yeah. So I want to thank also the organizers for inviting me for this very nice conference, and I'm very grateful that despite that I unfortunately cannot be present in person, that it was possible to also have this hybrid mode, and by this be able to participate and also present my results in this flexible way. Thanks a lot to the organizers for this. I want to begin with giving credit to my collaborators of this work. So this work is a collaboration between my group and the group of Jingye Liu at Beijing University, And we have also intensive collaborations with Rice University with the groups of Jimmy Shi and Peng Dai on this work, and other collaborators as well, which are credited here. So I want to just begin with defining or reminding us what nematic order is looking like in both real and momentum space. So you see here on the left side the typical magnetic configuration of a system which shows magnetic order, which is basically having, for instance, here a ferromagnetic spin alignment in the horizontal direction and the antiferromagnetic spin alignment in the vertical direction. So by this, one nicely can illustrate what nematic order means, which is, for instance, the case in the spin structure of barium 122 iron arsenide, is that nematic order breaks the rotational symmetry, which means that you have automatically an inequivalency of the x and y directions in the iron plane, which is just the case here for this magnetic configuration I'm showing. In the brilliant zone and the momentum space, this means that the magnetic susceptibility, for instance, will have in the magnetic order basically a different response depending if you're on an x or y axis, which you can just see here. And if you go above the magnetic ordering transition, this inequivalency will basically vanish. So we were looking at nematic order in the iron selenide system. That's why I want to just review a little bit the basic properties which are relevant for the iron selenide in the very beginning. So here on the left side, you see the structure of iron selenide, which is consisting of iron and selenide just on plane, with the iron 2 plus and selenium 2 minus oxidation states, and then the selenium being either above or below the iron plane. So the structural or nematic transition of this system is exactly 90 Kelvin. And it's important to mention here that you have no long-range magnetic order. So it's a really peculiar iron-based superconducting system. So it doesn't have long-range magnetic order in its parent phase, unlike the iron pink-type superconductors. TC is relatively low, about 8 Kelvin in bulk form, but it has been shown that the TC can be significantly elevated by having heterostructuring or bringing thin films on, for instance, STO surfaces. So by this, the TC seems to be highly tunable, which is very nice. Early work on the superconducting order parameter was showing that you seem to have an orbital selective Cooper pairing. So here, this was an early study by Spau where they were showing that you have anisotropic superconducting energy gaps, which they could extract by their STM studies here. The anisotropic energy gaps in the middle and the edge of brilliant zone. So I want to just summarize very quickly how you basically see the nematic ordering transitions. So the most prominent probe is, of course, just simply resistivity. So the nematic order transition would give rise basically to first the structural transition, ES here, which is occurring between a tetragon and an orthorhombic state. So you have also a lattice distortion then occurring. So you can see that you have a lattice distortion of about 0.0027 here between tetragon and orthorhombic state. And of course, then the resistivity along A and B axis will be inequivalent. In addition, you have the nematic susceptibility, which is basically diverging if you are approaching the nematic ordering transition or the structural transition in the case. And just in the top here, in this overview paper, was shown that you have also a large evolution of the Fermi surface topology when you're crossing with the tetragonal and the nematic orthorhombic state. So the question is now, what is the real origin of this electronic nematicity? And there is, of course, two different scenarios which are candidates. There's the orbital or the spin-driven scenario. It's the question now which is really true, because they are, of course, entangled, because the spin orbital degrees freedom of the, of course, strongly entangled. And of course, it's also important now to study in this connection correlation between magnetic excitations, nematicity, and the superconductivity. So for doing that first, you resort often to inelastic neutron scattering and look at low energy spin excitation, which is done here on the right side. But of course, you can also do studying low energy spin excitations by NMR. And here there was work by the Büchner group already in 2014, where they were looking at the spin relaxation rate with NMR, and they were observing no anomaly in the spin relaxation rate, which speaks for rather an orbital driven nematicity. In contrast to this, the inelastic neutron scattering results were observing the typical spin resonance mode at very low energy, around 4 millielectron volt here, which is tightly related to superconductivity, of course, which you can see here on the right side, where the spin resonance is basically having a low intensity above the superconducting transition temperature, and is sharply rising exactly when crossing the superconducting transition temperature, TC. So now is the question, what is the interplay with the nematic phase transition? And there it was shown that actually you have very low spin excitations around 2.5 millielectron volt, which showing a strong interplay to the nematic transition TS, which you can see here on the left side. So basically it's evolving as a order parameter like form. So basically at the nematic phase transition TS, you have the low energy spin excitations around 2.5 following exactly the lattice distortion delta here in this case. So and this suggests then that of course the spin fluctuations could be really the driver for this electronic nematicity. So this inelastic neutron scattering studies rather speaks for the spin driven scenario. So then more inelastic neutron scattering results on a larger energy range and more advanced instruments over energy range up to about 150 and nearly 200 millielectron volts. We're showing actually two types of spin fluctuations, stripe and Neal type spin fluctuations, which you can see here in the brilliant zone where they are situated. So they are situated either more in the middle or in the edges of the brilliant zone. And it was found that actually across the nematic ordering transition TS, you have a strong competition between these stripe and Neal type spin excitations. And it was, as you show here on the right side, it was obvious when you were now integrating the intensity for this spin excitation around 45 millivolt. It was shown that actually in the orthorhombic nematic state, you have a favoring of the stripe type spin excitations seen here in black for low temperature. And in the paramagnetic tetragonal state here at higher temperature, you have enhancement of the Neal type spin excitation. So all of these data taken with inelastic neutron scattering experiments were all at twinned crystals obtained, and there was for a long time no data on detwinned crystals. And then there was progress made 3 years ago that you could detwin iron selenide in a neutron scattering experiment, and just show the principle how this is done. So this is work by the Pencheng Dai group. Just show how they have done this. So they use basically barium iron arsenide as a substrate for detwinning the iron selenide. And this they can do because the barium iron arsenide has a structural transition which is higher. It's about 140 Kelvin, which is higher than the structural transition of iron selenide, which is 90 Kelvin. And it has a large orthorhombic distortion, which is about 0.36%, which is enough basically to detwin the iron selenide if the iron selenide is just simply glued on top of the barium iron arsenide. And it is a good match because you also have here the spin wave energy gap of barium iron arsenide, which is 10 millivolts. So at least you can study by this the low energy spin excitations without having any masking by the barium iron arsenide. With neutron scattering, of course, you see everything integrated over all volume. So you can also show that this technique was having a large detwinning ratio. So the measurement of this detwinning ratio could be done by nuclear peak monitoring, and it was shown that they have all over always a detwinning ratio of about 50%. So in this neutron scattering study, they were then immediately observing unisotropy spin fluctuations of the detwinned iron selenide. So in the spin resonance, about 4 millielectron volts, they saw this anisotropy along 0,1 and 1,0, both in a superconducting normal state, and actually all over the low energy spin fluctuations you have the anisotromy, which you can see here on the left side, and exemplified by it for the mode at 8 millielectron volts. So how was that then reconciled? It was reconciled in a itinerant spin scenario where you have spin fluctuation. You have a spin fluctuation-driven orbital selective Cooper pairing, which is basically a combination of course, learned on the gap asymmetry, and now introducing that you have scattering of spin fluctuations between different parts of the Fermi surface. You see that the part which is mediated also by the dy set orbitals is basically contributing most. So that means not all scattering paths are contributing the same way. That's why it's basically the spin fluctuation which is driven by orbital selective. So now is the question remaining: what is the evolution of the high energy spin excitations across the nematic transition? Because in this inelastic neutron scattering, you could not go to neither high energy because you're blocked beginning with 10 millivolt already due to the overlapping of barium iron arsenide and iron selenide in the spin excitation response, and you are also blocked to go to higher temperature, which is not possible in this instance. So here comes into play resonant inelastic X-ray scattering, because it's a nice technique. They can study also the low energy and high energy excitations in the system. So here we have the facility where we undertake our study at the Swiss light source. So you see here the Rig spectrometer at the address beamline, which has a resolving power energy over energy resolution of 10 to 14,000. And we employed now Rigs, which is a photon in, photon out, the spectroscopic technique between core level and conduction levels, and then having a recombination from the valence level in order to study the energy loss to the system, and also the momentum transfer to the system. And this is a very nice technique to now access all charge neutral or elementary excitations like Elkin hole, charge, orbital spin, and so on. So this has early on been demonstrated by us, like nearly a decade ago, that it can be employed for iron-based superconductors. Here, for the example of barium iron arsenide, where you see here the absorption spectrum on the top, and you see then for the excitations of incident light at the absorption maximum, the following Riggs response, which is characterized by a broad fluorescence electronic response, which is explained due to a strong itineracy of iron 13 arsenide orbitals. So basically you have a lot of electronic structure which gives all the spectral weight, but you have at low energy next to the elastic line also response due to the quantum excitations, which are now changing as a function of position in the brilliant zone. And we had then studied basically how this is evolving when you go across pi 0 or pi direction in brilliant zone. You see that this is changing here close to the elastic line. But what you need to do in order to now analyze this in detail is to subtract this fluorescence electronic background, which can easily be done. And by this extract the spin excitation spectral weight, which has been done here. And you see you clearly have spin excitations which are collected, can be fitted by dynamical spin susceptibility. And actually, when you are now doping the barium arsenide 1-2 system by holes, you were seeing that the spin excitations are clearly softening as a function of hole content. So now I come to the main part of the study, which is now looking at the iron selenide with RIGS. So we follow exactly the same strategy how to detwin. We use barium iron arsenide as a substrate. We glue the iron selenide on top of it, and then we basically detwin the barium iron arsenide, which is then in response detwinning the iron selenide. So now is the question, how do the high energy spin excitations evolve with RIGS across the nematic transition? And that's what we're tackling with RIGS. You see here on the left side, absorption spectrum iron selenide, and you see overlaid the spin excitation response, which is exactly maximizing at the resonance. You see here down a RIGS map. That means energy loss as a function of all incident energies, and basically many RIGS slices which show that the dominating response here again, as in barium arsenide, is coming from the fluorescence, but at low energy you have a clear Raman-like magnetic excitation response. So in order to now analyze in detail the low energy spectral weight of the magnetic character, we need to basically do a fitting analysis accounting for fluorescence, the elastic line, and we parameterize, analyze the low energy spin excitations with a formula of a damped harmonic oscillator. So that's the results which we observed or obtained as a reference. So basically our reference material was barium iron arsenide, where we know that we have a defined spin structure, which is ferromagnetic and antiferromagnetic in the two different directions in real space. So you see a clear anisotropy between now the X direction and Y direction. You see here, so basically H and K directions have a clear shaped anisotropy. So here you see also the pi direction, and these spin excitations can well be accounted for extended Heisenberg model, which is see here in the right side. So basically we can explain this by a localized model, extended Heisenberg model, or also by RPA plus U calculation, which does similarly good. So if we now turn to iron selenide and do the same the same test, we see also clearly a strong asymmetry between the H and K direction and the brilliant zone. You see clear, strong anisotropic spin excitations in between iron selenide, and these excitations are even at very high energy scale, around 200 millivolt. That means actually the energy scale much higher than the orbital splitting between the XZ and the YZ. So we have here clear, unambiguous evidence for high energy nematic spin correlations or stripe-like correlation if you are below the nematic temperature. So it's now the questions: how do these stripe correlations evolve when you are heating the system, when you are going from deep in the nematic temperature range to cross the structural transition and a magnetic transition? And that's what has been done here on the right side in EF. See for barium iron arsenide, this nematic anisotropy, basically the anisotropy between X and Y direction, is fading away, and upon crossing TS is at some point vanishing. Basically about 20 Kelvin above TS is vanishing, and for iron selenide we have a very, very similar picture. So basically for low temperature you have clear anisotropic fluctuations, and if you go now 30-40 Kelvin above the magnetic structural transition and magnetic transition, this anisotropy is at high energy. The spin excitation rate is also vanishing. So that means you have spin excitation, you have the spin excitation anisotropy, which is decreasing with temperature, clearly is disappearing above a temperature which is a little bit above the structural transition. So we were then comparing our data with a localized moment-based picture. So we employed from the group of Shmitt an antiferromagnetic quadrupolar phase description of the spin structure factor, and compared now their calculations with our fitted experimental results. You clearly see that this kind of local moment-based picture can nicely describe the nematicity development between H and K direction in the brilliant zone for all of the probed brilliant zone points here. So basically, they can do a good job in now describing the nematicity of iron selenide in a local moment-based picture, which one should mention that this is in addition to already earlier descriptions which are based on itinerant approaches. So basically, it seems that you can describe the nematicity in iron selenide from both an itinerant side and also a local moment-based side, which speaks that the real physics is happening somewhere probably in an intermediate couple. So I just summarized now the whole study, what we have undertaken. Basically, we have detwinned iron selenide and barium iron arsenide. So we observe spin excitations in both barium iron arsenide and iron selenide, where they're mostly underdamped. You can see that here by the dispersion plots of the iron selenide, where we overlay below the damping. So the damping is always significantly smaller than the energy of this high energy magnetic mode. So you have really strongly underdamped excitations. And the conclusions are that we have clear nematic spin correlations. If you are below the nematic spin transition TS, nematic transition TS, so you have developing kind of stripe-like spin correlations below TS. The magnitude of the spin excitation anisotropy in that is comparable actually to barium iron arsenide, which has the fixed spin structure. Basically, ferromagnetic and antiferromagnetic directions. And importantly, it's to mention that they have a very large energy scale of these high energy spin excitations, about 200 millivolt, which is much larger than the orbital splitting between DXZ and YZ. And the most important fact is that actually the spin excitation anisotropy really disappears above TS, which has been held as an important criteria for the spin-driven scenario for the nematic transition. So basically, our conclusion is that the driver for the nematic transition in iron selenide is the spin degree of freedom. So I'm
thank
done,
you.
and I thank everybody for their attention. Thanks. Bye-bye.
Thank you. We have to close the session because it's time for coffee break.
Okay, everybody, I think we'll make a start. I think there are still some people coming back in, but we're already about 10 minutes after the start time. So the first speaker in this session is Alexander Gray, who's going to talk about atomic level design and ultra-fast terahertz electric field control of emergent electronic and magnetic phenomena at oxide interface. The same title was there.
Yeah, All right, thank you very much for your kind introduction. And yes? Those are not my affiliations. Those are the, yeah, I know. It's really something. So thank you for your kind introduction. And of course, heartfelt thanks to Antonio for organizing this conference and inviting me to, giving me an opportunity to give this talk and share some of our latest results. So yes, the research, the studies that I'll be presenting were done with many various collaborators who were really invaluable in this research. And before I even start with the scientific part of this talk, I would like to acknowledge and thank our wonderful collaborators who really made it possible. We have now several collaborators in Italy, Stefano Vanetti, Giancarlo Panaccioni, Ivana Babornik, our collaborators at PSI, Vladimir Strokov, ALS, Patrick Schaefer, and Forschungszentrum Jülich, Klaus Schneider, then wonderful synthesis people who synthesized the samples for the various studies that I will be presenting, Jack Chakalian and Yuri Suzuki, and finally our favorite theorist, Andy Millis, who has stuck with us for many years and helped us interpret the results, understand them, and develop the theoretical machinery to help us do all of this. So these are the real heroes, the students who really did all of these measurements and analyzed all the data, Abby and Jay, and the funding was generously provided by various government organizations, as well as the Alexander von Humboldt Foundation. So the scientific focus of the research that's done in our group is the X-ray studies of emergent phenomena at oxide interfaces. And there's a wide plethora of these phenomena that are now known, and this field has exploded about 20 years ago. And what we focus on, or what we've focused on for the past several years, is the study of the emergent ferromagnetism at the interfaces between complex oxides. So there's several seminal papers that I would like to mention in this regard on this topic. I think one of the first ones, maybe not the first one, was a paper that came out in 2001 from Tokura's group, where they discovered the interface ferromagnetism in the superlattices of calcium manganite and calcium ruthenate. And I apologize if I don't mention everyone, and if someone maybe have been involved in some of these studies. Another big study that made a big splash about 10 years ago was a study that came from Cam Muller's group at Stanford, where they've used a nanosquid to image the coexistence of ferromagnetism and superconductivity at the LAO-STO interfaces. Now, I'm very excited that the third speaker in this session is going to be Marta Gibert, who has done a prolific contribution into this field, and is one of our favorite papers. One of my favorite papers of hers is this paper on the interfacial control of magnetic properties of LNO interfaces. So it's definitely a fantastic paper. And the study that really inspired us, and then inspired us to collaborate with a group at Stanford, was a study by Yuri Suzuki, and it was done by Alex Gruder at the time that he was a postdoc in her group, and then went on to be very successful at NIST. And that's the discovery of the interfacial ferromagnetism at the interfaces of lanthanum nickelate and calcium manganite. So in this particular study, they used XMCD to first detect the magnetic moment on the manganese, on the interfacial manganese, and then used depth resolve techniques such as polarized neutron reflectometry, I believe at NIST also, to collect this data, analyze it, and extract the information that the magnetic moment is really concentrated within just one unit cell of calcium manganite right at the interface with lanthanum nickelate. So in a follow-up study, Charles Flint, who was also in Yuri Suzuki's group, has discovered that this magnetic moment on manganese actually scales with the thickness of lanthanum nickelate. And if you have studied MOT oxides, you probably know that lanthanum nickelate is a very interesting beast. It's a material that is metallic in the bulk form, and when it's a thin film, that's considerably thick. But as you start reducing the thickness, it undergoes a metal to insulator transition in the ultra-thin regime at a critical thickness of, it's still a little bit of a controversy, somewhere, let's say somewhere between 2 and 4 unit cells. So in the magnetic moment at the interface in the adjacent layer in calcium manganite depends on the thickness of this lanthanum nickelate. So, and this is very interesting, of course, and very promising, because it opens up a new possibility of controlling interfacial ferromagnetism with metal to insulator transition in the adjacent layer. So, what is the mechanism of this emergent ferromagnetism at the interface between the materials that are not ferromagnetic? Calcium manganite is antiferromagnetic, lanthanum nickelate is ferromagnetic. To investigate this, we've recently employed a technique that is kind of our specialty in our group. It's a technique called the X-ray standing wave technique, in particular standing wave photo emission, which was pioneered by Chuck Fadley about a couple of decades ago at UC Davis. If you're interested, there's a nice review paper that we've written together just unfortunately a few months before his passing. And there's also a fantastic book by Jörg Zegenhagen and Alexander Kazimierov that goes over the history of this effect, of this technique that started with Bob Batterman when he was at Bell Labs, who demonstrated the utilization of the X-ray standing waves for the studies of adsorbents at the surfaces of materials. So this is a depth-resolved X-ray technique. Now, the idea here is that if you want to investigate the properties, electronic or magnetic properties of an buried interface, you can grow these two materials, the two materials of interest, in a form of a periodic superlattice. And then when you illuminate it with the X-rays of a given wavelength, and you do it at an incidence angle that corresponds to the first order or maybe second order Bragg condition of that superlattice, then the incident and the reflected waves will interfere constructively and destructively within your sample and above your sample to create an X-ray standing wave interference pattern. So the standing wave is going to consist of real regions in real space where the E squared, the electric field squared of this interference pattern is higher. Those are the antinodes of the standing wave, and in between you're going to have some dark spots, the nodes of the standing wave. And naturally, the antinodes of the standing wave are going to act as a sort of epicenters for photo emission in this particular case. And the trick is then to change the phase of the standing wave within your sample and above your sample so as to drive these antinodes vertically through the buried layers and the interfaces. And this way you facilitate depth sensitivity to the measurement. And it's usually done by rocking the sample a little bit, changing the incidence angle around the Bragg condition. All right, so, and the depth resolution that has been demonstrated with this technique, we did the study a couple of years ago in soft X-ray regime was about 1 perovskite unit cell, so somewhere between 3 and 4 angstroms. So we are in that way competitive with other techniques such as STEM and EELS. All right, so what do? We look at the superlattice, we generate the standing wave inside of the superlattice, we drive the standing wave through the superlattice, and we look at the spectroscopic signatures of the valence state of the manganese cations near the interface and further away from the interface. The spectroscopic signature that we picked in photo emission, which is very clear, is the splitting, the multiplet splitting of the manganese 3s core level, which due to the exchange coupling interaction between the 3s core hole and the 3d electrons in the valence bands, it is split, and it is inversely proportional to the manganese valence state. So this was actually pointed out by Fadley and Shirley in the late 60s, 1970, that's when the paper came out, and then a very extensive paper on manganites came out about 20 years ago by Galikov. All right, so we drive the standing wave through the sample, and we do a lot of modeling and a lot of analysis of experimental data to figure out exactly where the standing wave is. And what we realize is that splitting, that multiplet splitting, is higher at the interface and lower toward the bulk of the film. So, and here are the examples of the spectra near the interface and near the bulk. Here is a difference just to show that they do move apart. Those peaks move apart and the splitting changes. So what that tells us is that there is an increased concentration of these off-stoichiometric manganese 3+ cations at the interface. And what that suggests is that perhaps that concentration, that increased concentration, might create an electronic environment that is favorable for the stabilization of the ferromagnetism via the manganese 3+, manganese 4+ double exchange interaction. All right, so how do those off-stoichiometric cations get there? Well, when we first look at the data, when we first saw this, our first thought was, of course, it's some kind of defects, some kind of oxygen vacancies. And we've actually did 2 extensive studies of oxygen vacancies in calcium manganite films. We did that in collaboration with Nicholas Spalding, and then with Andy Millis, we did a collaboration on the oxygen vacancies in lanthanum nickelate films, right? But then the answer, and the answer is yes, there's definitely oxygen vacancies. There's plenty of reasons why there should be this manganese 3+ cations in the system. But then that doesn't really answer, first of all, how do they get to the interface, and why do we see this LNO, the dependence on the thickness and metallicity of the adjacent layer. And this is where a more recent study came out by my student Ravini, where she examined this and then with some theorists and with some experimentalists suggested that it is the charge transfer across the interface from LNO to CMO that creates these just a little bit of extra manganese 3+ cations. So this was actually suggested before us. It was suggested for a system CMO-CRO, calcium manganite, calcium ruthenate. There's an extensive study of that using DMFT, I believe. And the idea is that when LNO is metallic, you have these itinerant EG electrons near the interface, and just a little bit of a leakage across the interface. In fact, it turns out you only need 0.07 electrons per manganese cations in order to stabilize the ferromagnetism at the interface via the double exchange interaction. All right, so we looked in this first study, we looked at this critical thickness of 4 unit cells, which in our case was actually, I believe the samples were a little bit better than in this prior study. The LNO did show metallic behavior, so we did expect the charge transfer at the interface, and then just to make sure that it really works, we went to one extreme where LNO is really thin, 2 unit cells, so here it is definitely insulating, and another extreme where it's 6 unit cells. We couldn't go really much higher because of the limitation of the standing wave technique, so 6 unit cells where it's clearly metallic. So we look at magnetism first. So this sample over here, the thickness of CMO is the same everywhere. The LNO, however, here is thicker, so we expect to see charge transfer, and in fact, we do see a 3 times higher magnetic moment compared to this sample over here, which exhibits much lower XMCD signal, and we speculate that is due to the fact that LNO is insulating and there's a less charge transfer that is happening at the interface, so you have less of these manganese 3+ cations at the interface. All right, so then we do our standing wave game. We generate the standing wave through the sample, we drive the standing wave through the sample, and once again, look at the manganese 3s splitting, and lo and behold, for the sample where we do not expect to see significant charge transfer, the splitting remains the same near the interface and in the bulk. So that suggests that the manganese valence state remain constant. However, for this sample over here, we see a clear step, and right at the interface, we are observing the decrease in the average or effective valence state of manganese, which suggests that perhaps there is some charge transfer happening at the interface that facilitates this magnetic moment and increased XMCD signal. All right, so the other side of this superlattice, LNO, is there really a metal to insulator transition that is happening there? So we studied this with ARPIS at the APE LE beamline at Electra. This is a wonderful end station, wonderful facility, because it combines in situ PLD synthesis with spin resolved ARPIS. We did not utilize spin resolution in this particular measurement. However, we grew these types of samples where, once again, we change the thickness of the LNO while keeping the thickness of CMO the same. And we look at what is happening to this Fermi surface cut at the Z point right here, at the Z plane over here for LNO. And we do, in fact, observe a reduction in the density of states, in the spectral weight near the Fermi level. And if we angle integrate and then just look at what is happening near the Fermi level, yes, indeed, we do see the metal to insulator transition. For the thickest film, 8 unit cells, very nice, partially coherent quasi-particle peak right at the Fermi level. Then we reduce the thickness, it drops. Then 4 unit cells drops again, and then finally for 2 unit cells, it diminishes. So it all checks out. So this is nice. Now, when we compare the results to theory, and this has to be done very carefully because the strain that is facilitated by the LAO substrate has to be taken into account. And we calculate these slices, what they are supposed to look like for this particular for this particular strain state, it doesn't look very good. But if we include charge transfer, then I hope I'm able to convince you that this looks very promising. Now, these are very, very recent results, and they still need to undergo some scrutiny, but I wanted to show them anyway, because this is a very exciting conference. So, all right. So now, about the control of the magnetic and electronic interaction at the interface. How do we disentangle the electronic and magnetic interactions? Well, what are we talking about when we talk about electronic phenomena? Well, it's the metal to insulator transition in LNO. And the magnetic phenomenon, obviously, is the interfacial ferromagnetic state. How do we separate these two processes? Well, one of the ways to do it is to go into a time domain, right? So if you stimulate the system with some kind of an ultra-fast pulse, whatever it is, and then you observe both the electronic and magnetic dynamics simultaneously, and then you observe that the dynamic signatures of the two processes differ. For example, one happens first and another one follows, or one happens faster, another one happens slower. Then perhaps you can speculate about the origins, and then perhaps even speculate about the possible cause-effect relationship between the two. Now, how do we stimulate those superlattices? Well, we want to do it in a way that it would be done in future spintronic devices. We want to do it with electric fields. However, we have to do it with a ultra-fast resolution to capture these processes that happen extremely fast on a tenth a second or picosecond scale. So we use terahertz, single cycle terahertz electric field pulses that are generated by a femtosecond laser. All right. We've had some success doing that at a linear coherent light source at Stanford with a vanadium dioxide, where we were observing, we were using this to separate the structural dynamics and electronic dynamics in VO2 undergoing metal to insulator transition. So once again, we have two samples. On the left, thin LNO sample. CMO is the same everywhere. Thin LNO, so thickness is below the critical thickness. We expect little to no charge transfer, weak magnetism. Another sample, above critical thickness, metallic LNO, we expect strong interfacial magnetism. All right. So for the electronic dynamics that is initiated using this ultra-fast electric field pulse, terahertz pulse, we measure infrared reflectivity and transmissivity. For magnetic dynamics, we use time-resolved magneto-optic Kerr effect, and we do it at the same time in the same setup. All right, so last 3 minutes, I will summarize the results. First, we look at room temperature dynamics. Above the Curie temperature for this interfacial ferromagnetism. So this is supposed to be a purely electronic dynamics. So what we observe is that this terahertz pulse, which is shown in this plot over here, it creates a short transient response that is followed by this long-lived state that actually lasts for tens of picoseconds. Reflectivity goes up, transmissivity goes down. We speculate that this is a characteristic of a sudden metallization of the superlattice. It's impossible to tell which component of the superlattice metallizes. We suspect that it is lanthanum nickelate. The reason for that is because when we look at the magnetic dynamics exhibits a very strong LNO thickness dependence. So the Kerr effect is very strong for the thicker film, for the thicker superlattice where we expect to see magnetic signal at the interface, and much, much weaker for the thinner superlattice where we expect to see very weak ferromagnetism. And the same thing is observed for the 300 Kelvin data above the Curie temperature. So this data over here suggests that we are perhaps metallizing somehow with this terahertz pulse, the LNO film. All right, so now you will see that the dynamics is very complex. First, we have this very sharp peak in the beginning, right? It exists everywhere, in every data set. And then we have in some of these data sets, particularly below the Curie temperature, slower dynamics, this little hump here, that is followed by the exponential decay. So when we look at this ultra-fast dynamics, it essentially follows the integral of the electric field squared of the terahertz pulse. So this is really an electric field generated process, just follows the shape exactly. So this is the direct stimulation of this electronic structure. Now for the magnetic dynamics, here is a Kerr rotation, here is the change in the reflectivity. So this is more characteristic of magnetic dynamics, more characteristic of the electronic dynamics. We do a very careful temperature-dependent study across the Curie temperature, right? And what we observe, just first, by a very rudimentary analysis of these amplitudes, of the fast peak and the slow peak, that it has this critical behavior with this cusp that is happening around 75 to 80 Kelvin. Now, when we look at the magnetization data, and here you have to look at the black curve because the red curve is a different orientation, it's 111 orientation, you can see that it essentially mimics the magnetic behavior. So what that tells us is that observed temperature dependence suggests that the origin of the observed effect is at least partially magnetic, right? I cannot say anything more about that, really. So, but when we look at the reflectivity, we still see a similar trend. However, we don't really see a sharp cusp here, especially for this slow peak. It's just kind of a smooth here. We're not quite sure what is happening there at this critical point, some kind of an instability we're still thinking about that. We don't really know what's going on. All right, so this suggests the possibility that perhaps the electronic and magnetic processes could indeed be somehow disentangled. So this is where my student Abby did a fantastic job taking all of this data and fitting it using one model, using a genetic algorithm for the fitting. And when we look at the above TC data, which I've showed before, it is pretty clear that it can be fitted using two components. This fast pulse that is present there while the terahertz pulse is present in the sample, and then these terahertz pulse length smoothed, expanded step function, which mimics that, that long-lived state. So when we add them together, it's a very nice fit. However, when we go to the critical temperature, to the Curie temperature, a new component starts to emerge, right? So this is no longer enough to describe this line shape, right? This is the sum, the green one is the sum of the two. Cannot do it anymore. There's extra stuff going on here, which can be explained by this slower dynamics followed by the exponential decay. All right, and finally, when we go to the lowest temperature, way below the critical temperature, once again, this peak essentially increases in amplitude. It also shifts a little bit. All right, so now when we look at the individual dynamic components, this first sharp peak that happens just within the first picosecond, it's beautifully uniform for all temperatures and only exhibits amplitude modulation. Right, here it is. And the time scale for that is 250 femtosecond. So we think that it's just an electronic dynamics that follows the terahertz pulse. However, when we look at this purple component here, much more interesting dynamics here. First of all, it starts to emerge at the critical temperature. Actually, a little bit above the critical temperature, but there's a sharp change at the critical temperature that happens right here with this green spectrum over here. And then the characteristic time scale is much slower. It's on the order of 1 picosecond. That makes us think that this is possibly some kind of a magnetic dynamics. We've tried an experiment where we rotated the polarity of the terahertz pulse to see whether it's some kind of a coherent spin oscillation, some kind of a rotation. And we did not see any difference between the data for the two different pulses. So we suggest that it's probably just an ultra-fast demagnetization of the interface that we are inducing. All right, so once again, if we do a more careful, rigorous analysis of all of these components, we see this very nice cusp right at the critical temperature for this interfacial ferromagnetism, and we see the same thing happening for the decay time of this peak over here, but not so much for the rise time. The rise time is almost uniformly about 1 picosecond, so it's very interesting. Now, this is magnetic dynamics, and the very last plot that I'm going to show is electronic dynamics. Once again, no clear cusp at the critical temperature, but once again suggests that perhaps we can decouple it. Now, how can we decouple it? And this is the future outlook. Well, we should go back to X-rays. So free electron lasers that facilitate, first of all, the element and orbital selectivity, momentum resolution, polarization dependence. We can do this with XMCD, XMLD, XLD, and so on and so forth. And in fact, in the near future, a actually next week we will be doing an experiment at Porsche and Juli, where we'll be looking at time resolved remote at the manganese and nickel M edges. And then in the near future also the alpha-fast M edge experiment at Fermi and alpha-fast L edge experiment at LCS. So with that, I once again want to thank our collaborators and students, and I want to thank you for your attention. Thank you.
No, it's not. It's not. Thank you so much. This is a wonderful question and something that I omitted from my talk inadvertently, but very important. It's not a resonant excitation. The central frequency of the terahertz pulse is... Oh, sorry. Yeah, thank you very much for this question. It's an excellent question. No, this is not a resonant excitation. The central frequency of the terahertz pulse is about 1 terahertz. So this is way below any of the, for example, phonon modes in both CMO and LNO. So we really are kind of distorting the electronic structure, I believe, and perhaps causing interband tunneling from the valence to the conduction band. That's my guess. It's speculation, yeah. Yeah, catching. On the defects? Oh, the strain effect. Oh, yeah, excellent question. Unfortunately, I cannot answer it right now because we are in the process of exploring it, but there is definitely strain effect. There's a strain effect and also a defect effect. So the oxygen vacancies, intermixing, chemical intermixing, cation intermixing at the interface also is very important. So this was kind of a broad strokes, but the devil is in the details and there are other things that are happening there. Yeah, that perhaps is a follow-up study. Thank you. It's a great question.
So I don't see any other questions, so we'll thank the speaker again. Thank you. And we're going to go on. Hello, have we got Chongwen Zhu online?
Yeah, I'm here. I'm just online. So can you hear me?
Yeah, we can hear you. Can you share your slides?
Okay, I just share my screen. Yes, can you hear? Can you see my slides?
Yeah, we can see them. It's not in presentation mode yet, but we can see them.
Okay, I just display the.
Great. So while you're doing that, I'll just introduce the speaker, Chongwen Zhu, who's going to talk on the hydrogenation-induced multiple phase transitions in vanadium oxide. Thank you.
Okay, thanks. I'm Chongwen Zhou from University of Science and Technology of China. And firstly, I'm very thanks to Professor Bianconi and Massini for the invitation. So that we have a chance to share our recent studies. And the topic title is hydrogenation-induced multiple phase transitions in vanadium dioxide films. Okay, it's outline my talk. At first, I want to show some background about the phase transition of VO2 and its potential applications. And then I will show our recent experiments for doping the VO2 by normal catalyst or by exclusion. And then go to the final conclusion. Okay. This image just shows some oxide materials which has a mental insulated transition property. And you can say that they have different phase transition temperatures, range from about tens of Kelvin to more than 1,000 Kelvin. Well, among these oxide materials, you can say it has a critical temperature of about 340 Kelvin, which is very close to room temperature. So people pay much attention to this material. Also, it had very special phase transition property. For example, at low temperature, it showed insulated state. When the temperature goes up, 70 degrees, go to the metallic state. This change is just with a sharp change of resistance up to 4 to 5 orders of magnitude. In addition, it also has a very pronounced switching effect as the infrared radiation. So that means at low temperature, VO2 just show infrared transmission mode. But if the temperature goes up to over its critical temperature, then it will block the infrared. So these particular properties make these VO2 materials many applications. It can be smart windows because of it very sensitive to infrared. Also, it can be used as some optoelectronic device. For example, some thermal sensors or some optic device or some phase change memories. And so on. And also, it can be used as some uncooled infrared detector because of temperature sensitive or some laser protection. Well, though it has many applications, while it's still a bottleneck for the problem. That means the critical temperatures is still. So how to make a phase transition at room temperature is still a big challenge. This challenge is just associated with the phase transition mechanism and the way to modulate its phase transition. The phase transition mechanism, there are always two phase transition models. For example, including the Pierce transition, which is related to the lattice distortion induced phase transition, or the Mott transition, which is close to related to correlated inaction. Well, at low temperature, this VO2 has a monoclinic structure just like this. Well, if the goes to a higher temperature, it will turn to rutile state. So these two factors always couple together to make this mechanics, to make this phase transition complex. So as many. Excuse me? Hello? Hello?
Yeah, we can hear you. We can hear you, but we've lost your. We can hear you, but we've lost your slides.
Oh, okay. So I just share the screen again.
Yeah, now we can see the slides and we can hear you.
Okay, just go ahead.
Yeah, carry on.
Okay, you can say that VO2 is a typical correlated electron systems, so that the lattice, charge, orbit, or spin, all of these rhythms are closely associated with its phase transitions. So many ways is adopted to modulate these phase transitions. For example, use the strain effect. So especially for those epitaxial films, we can use the interfacial strain or external strain to modulate its phase transition. Or temperature, it also normally triggers phase transitions as well. And also we can use some laser exciting or radiation to modulate the phase transitions, or by using the electric field or some other external field to control the phase transition as well. Well, normally people use doping effects to modulate its phase transition. Normally for doping, the charge effect or lattice distortion always play a very important role for this phase modulation. So this in just in this paper, the group just learning the VO2 microbeam in hydrogen gas assisted by gold catalyst, and they just convert the VO2 to metallic states at room temperature. And then a group from Korea just learning the VO2 films in hydrogen gas and assisted by a PT catalyst. And then they obtained a metallic state at room temperature as well. And they also observed the new insulated states by very heavily doped hydrogen. So in our lab, we just used oxide molecular beam epitaxy method to prepare the high quality VO2 films. And then we use the synchronous source techniques to examine our samples. In SSRF, Shanghai Synchronous Facility, or some other facilities overseas. So this is the sample we just prepared by our oxide MB, and it's a 2-inch wafer size. And then we use the X-ray diffraction to examine our samples. So,
hello, we've lost you
hello?
again. We can't. I can hear you. Can hear you, but we've lost your slides again.
Yeah, I can hear you. So something wrong with the signal? Okay, just go ahead.
Yeah, that's fine. Carry on. Yeah.
Oh, okay. Okay, this is our sample just prepared by oxide MBE, and very nice samples here. And also it's uniform because this is the insulated state at room temperature, and this is the metallic state at higher temperature. So it's quite uniform samples. Okay, it's a hard diff image taken by STM for our samples. And you can see that very clear interface and also atomically resolved image for this interface. So very nice samples. Okay, it is known that the temperature can trigger the phase transition from insulator to mental state. Well, we observe that the hydrogen doping is very effective to modulate these phase transitions from the initial insulated state to metallic states if a small amount of hydrogen doping, while if further increase the doping concentration, and then a new insulated state will be obtained. And also this electric measurement also confirm these continuous phase transitions, and from the new insulated state to a metallic state, and then if the metallic state can go back to the initial state if the hydrogen atoms just escape from the lattice. So we just use the X-ray absorption spectroscopy to examine the electronic state. So this is the vanillin LH record for this pure VO2 and the hydrogen doped state. You can see that this VLH just shifted towards the low energy direction, which means that the valence state of vanillin is decreased. And then the oxygen KH is also recorded. You can see that a clear change can be observed. For this T2G, you can see that the red curve is just for the pure VO2. The T2G is very strong. But if we dope the hydrogen, then it will decrease gradually. So based on this atomic structure for VO2 at the monadic state, so there exists the vanillin dimer structure, so that there is a very strong hybridization between the vanillin 3D and the oxygen 2P together to form a bonding level and anti-bonding level, which is related to the T2G or EG states. So if some hydrogen doping into VO2 lattice, the electrons will be occupied the T2G level gradually. So that means this T2G peak just become smaller because of it's become to the occupied state. So this observation is quite consistent with this model. Well, we also do some theoretic simulation for this system. For this pure VO2 system, you can say that there's a small band gap here, so which means this initial state is insulated state. Well, if we add some hydrogen atoms into this crystal, you can see that the Fermi level just increased, and then across the vanillin 3D level. So that means a metallic state is formed. While if we add more hydrogen atoms into the crystal, you can see that the Fermi level just rise further and then into another band gap. So that means a new insulated state was formed. So this theoretical simulation is quite consistent with our experimental observations. So normally hydrogen is very effective for phase transition modulation of VO2. So normally this treatment is just learning VO2 epitaxial films in hydrogen gas assisted by some low momental catalysts such as gold or PT, or some high energy protein implantation. So this treatment is always required always high energy consumption or lead some hard conditions. So it is known that acid solutions eventually provide a rich protein source. So it is possible to hydrogenating VO2 in acid solutions. Yes, the answer is yes. Normally, we just a student in our group just conduct the experiment. They just use the plastic tweezers contact with the VO2 films and then put it into acid solution. You can see that the yellowy VO2 layer it disappeared because of the closing. Well, if you use the ion tweezers contact with these VO2 films and then put the system into acid solution, you can see that after 3 hours, the yellow film is still there. And I also test the film thickness. You can see that if the VO2 contact with the ions, you can see that the film thickness is almost the same. Well, without the ion tweezers, the film thickness just decreased gradually because of the closing in acid solutions. Then we conduct another experiment. We just prepare the 2-inch wafer size samples with the same thickness and also always with the same conditions. And then we just put these 2 samples into acid solutions at the same time. And then if we put a corporal mantle just in the center of one sample, and then we can see that after 20 hours, these samples just become transparency because the VO2 is closing away, just disappeared. And while for this sample, the yellowy coating is still there. So what happened for this situation? Exactly after we examine the resistance of this sample, we can see that it had become converted to metallic state. The initial is a insulated state, while after this treatment, then the film is become a metallic state. And also it can be converted to the initial state by linear treatment. And also if we put zinc or aluminum grains on the surface, we can see that we can obtain insulate hydrogen doped VO2 just like this. So we think that this should be the heavily hydrogenated samples. And then we conduct the systematic examinations for these samples. And for example, the X-ray diffraction or some X-ray absorption, and also the binding, the X-ray photoemission. You can see that this vitamin 3 plus peaks in the XPS just become stronger due to the hydrogen doping. And also there's a very strong oxygen hydrogen bond here, become very strong. Also the Raman test also confirmed this metallic state formation. Well, there is a direct evidence for this hydrogen doped process in these acid solutions. You can see that this this green curve is just for the pure VO2, just means it has very low concentration of hydrogen atoms. Well, the metallic films just show the hydrogen concentration here, and then the insulators is just for this red curves. So that means as the hydrogen doping concentration increasing, then the VO2 will be converted to mental state at first, and then we'll go to another insulated state. So we conduct some more experiment to examine these observations. We just put aluminum, copper, or silver, PT or gold on this surface. And then this one is just a bio samples. We put off these samples in acid solution. We can see that these 3 samples, that means still keep the yellowy color. That means the coating is still there. Well, for these samples, 3 samples, the coating is just close away. So it seems that this observation is closely associated with the working function of these metals. So, for example, for this aluminum VO2 interface, there should be some electrons inject from the interface from aluminum to VO2. While for this copper, there's a small amount of electrons injection. While for this PT, almost low electrons inject. So, based on this simulation, we just propose a model for these observations. So, for this mental and VO2 interface, and when the mental has very low working function, there's some electron inject from the interface. And then if we put this system into acid solutions, we can see that many free proteins will be attracted into the oxide layers to form the hydrogen of the metallic state. And then more electrons will come from the metal grains to oxide, and then more proteins will be attracted into this oxide layer. And then finally, the total films will be hydrogenated. Well, this is the very interesting result that we can hydrogenate VO2 in acid solutions, but for device application it is impossible for. So that we just fabricate a three-terminal device just by use the solid electrolyte, and then we just use the positive gating to insert the proteins into VO2 lattice, and we can see that we can also realize these continuous phase transitions. And then by negative gating, we can just change this states, just go back to the initial state. So that means we can use this gating controlled VO2 phase transition for some smart Windows applications. So because of the time limit, I can't show more details for this device. Also, we just conduct a more interesting experiment just to realize the oxygen vacancies removal in VO2, because you know VO2 is very sensitive, because and the oxygen vacancy is very easy to be formed. So how to remove these oxygen vacancies is very difficult, since if you just heating these samples in air or in oxygen atmosphere, if the temperature is too high, the VO2 will be over oxide to, for example, to V2O5. But if the temperature is not high enough, the oxygen vacancy will be not removed from the lattice. So here we just propose a strategy just to hydrogenate the VO2 with oxygen vacancies, and then we realize a very easy way to remove these oxygen vacancies just by learning the samples at 200 degrees just in air. So it's very interesting work, and we also use the theoretical simulations to reveal that in this VO2 crystal, if the oxygen vacancy exists there, the electron doping will decrease the diffusion barrier of oxygen vacancies in the lattice, so that we can remove the oxygen vacancies very easily at quite low temperature Learning treatment. And also this route is very universal for the general. It is general for some other oxide materials. So we also use theoretically calculate this situation for example, for hydrogen doped titanium oxide or titanium or tin oxide. We can also confirm that this, because of the interaction between the hydrogen dopant and the oxygen vacancies, then these oxygen vacancies can be easily removed from the oxide materials just by low temperature Learning treatment. So just go to the final conclusions. In this talk, I just tell 3 points. And first, we just realized the hydrogen doping in VO2 and found that there's continuous phase transitions, which is seriously depending on the hydrogen doping concentration. And the second is just we realized the hydrogen relation of VO2 in acid solutions, which means that we don't need some low momentum catalyst to realize the hydrogen doping. We just realize this hydrogen doping at room temperature. And the third is that we just realize the interaction between the hydrogen atoms and the oxygen vacancy defects in some in VO2 or some other oxide materials, which means that this hydrogen doping will favor the oxygen removal. Okay, this is the acknowledgement from some fundings for the group members in our group. Also thanks the cooperators from for example, Professor Douglas from Rice University and Jiangjun Loi from our university, and also Professor Augusto Maselli from Italy. Okay, thanks for your attention.
Thank you very much. Are there any questions? Yep.
Okay, sorry. For the electrostatic gating of the HVO2, does that affect the voltage required for the gating? And does it also affect the kinetics of the gating?
You mean, okay. So this one's right? You mean the gating control, hydrogenation? Hello? Can you hear me?
Sorry, I left. Okay, so right, here's the electrostatic gating. So in HVO2, does that change the gate voltage to induce the transition? And also, does it change the kinetics of the transition?
Yes, exactly. If we want to use this hydrogen doping to make some device, it is better to use the gating treatment. And also, because we use the solid electrolyte and then apply the gating voltage. And this gating is also dependent on the gating time. So normally we just apply the voltage of about the 1 2 volts. And then we can continuously drive some proteins into VO2 lattice. And then if we apply the negative voltage, then we can drive the proteins out of the lattice. Yes, this process is just depending on the gating time.
Okay, we're having a little bit of trouble hearing you, but are there any other questions? No. Okay, so thank you again.
Okay, thank you.
If you can stop sharing your screen.
Okay.
So do we have Marta Gilbert ready? Hello. Excellent.
Yes, can you hear me?
Yes, we can hear you. So
Okay.
the next speaker is Marta Gilbert, and she'll talk about critical length scales at metal insulator and magnetic oxide interfaces. So thank you, when you're ready.
Okay, perfect. So, the only thing is, okay, now it's better because I was just hearing me twice. Let me just put pointers. Okay, so let me just start thanking the organization for the opportunity to present these results. And at the same time, I would like to apologize for not being able to join here today in Italy. Okay, so let's go on. So, and as we had been saying in the previous talks, in fact, transition metal oxides, they display a large variety of very interesting properties. And among them, and especially as we had been saying in the previous talk, we have metal to insulator transitions. So we have seen, again, in the previous work, that these metal to insulator transitions have been very widely investigated, and also they are very interesting for potential technological applications. However, in the region where this, in which this metal to insulator transition happens, that is in the region where we have coexistence of metallic and insulating phases, very little is known about how things evolved. So for instance, here in the left side, I'm just showing you a work in which through PIN, they investigated the nucleation of these different phases. However, questions such as, for instance, what is the length scale over which a metallic and an insulating phases can be established, they remain still quite vaguely explored. So what I would like to show you that we can address this question by using perovskite nickelates heterostructures. So the perovskite nickelates are are shown here are characterized by this R nickel oxygen 3 formula, with R stands for one of these rare earths. And one of the main characteristics of these materials is that they display a rather sharp metal to insulator transition across the temperature. So this phase transition also occurs together with the structural transition, and the low temperature phase is characterized as well by a bond length or a charge disproportionated state. In the nickelates, the temperature at which this metal to insulator transition happens is strongly related with the size of the rare earth. And this can clearly be seen here in the bulk phase diagram, where we are plotting the temperature as function of the tolerance factor, or let's say we are plotting the metal to insulator transition, which is the one here shown, for the different rare earths. And essentially what we see that is as larger is the rare earth, or equivalently bigger is this nickel oxygen nickel angle, lower is this metal to insulator transition temperature. So this is in bulk, but if we take, for instance, two different nickelates, we can see that this difference in metal to insulator transition temperatures are also reproduced in thin films. So here we show the case of neodymium nickelate thin film, which has a metal to insulator transition around 100 Kelvin, and the case of samarium nickelate film that has a metal to insulator transition around 320. So what we would like to do in the following is take these two different nickelates and generate superlattice structures in which we alternate different layers of these two compounds, so neodymium nickelate and samarium nickelate. So the idea is that these two materials in bulk, or also in thin films, they have different metal to insulator transition temperatures, and then we would like to see what happens with these transition temperatures as we make the layers thinner and thinner. So because we expect samarium nickelate to become insulating faster as we reduce in temperature. So in all the examples I'm going to show you in the following, we are always growing the same number of neodymium and samarium nickelate layers in each period, or unit cell, sorry, and we call the period of the superlattice lambda, which is just the sum of this number of unit cells. So let me just show you that we grow these samples by off-axis magnetron sputtering, and here in this TM image, I think that we can nicely appreciate the quality of these heterostructures. So let's go to the transport properties. So in this slide, we are showing the resistivity as function of temperature for three selected superlattices with different periodicity, a different number of neodymium and samarium nickelate layers. But in fact, we can maybe better zoom in. And what we see is that for relatively thick superlattice periods, like for instance, 15 unit cells or a 10 unit cells, so in this case would be about 4 nanometers thick each layer, what we see that is we can clearly see the two transitions that we expect in our samples. So that is first, the samarium nickelate layers become insulating, and then at lower temperatures, we have the neodymium nickelate layers becoming insulating. However, as we decrease the thickness of each layer, we see that at the end, for low period superlattices, we just have a unique metal to insulator transition in our system. So in fact, we have been growing many different samples, and the result of the determined metal to insulator transitions are plotted in this figure, where we show the temperature as function of the superlattice wavelength, that is the thickness of this superlattice period. And what we see in this figure is that indeed, for the superlattices with a higher or larger wavelength, that they are thicker layers, we can clearly see what we were saying, the two transitions. So the system first, it's everything, it's metallic. Then we have a region where we have coexistence of the insulating samarium nickelate layers and metallic neodymium layers, and then at low temperature, everything becomes insulating. However, as we have seen, for the low period superlattice, we just have one transition. That is, the system prefers to go from being everything metallic to being everything insulating, and the two materials have a metal to insulator transition at the same temperature. The thickness at which this transition occurs is what we call the critical wavelength, and it is about 16 unit cells. That means that each nickelate layer needs to be 8 unit cells, or equivalently about 3 nanometers. So we need 3 nanometers layers so that we can have separate transitions of the two materials. Otherwise, the material prefers to go from one state to the other simultaneously. So the question is, what is determining this critical wavelength of 16 unit cells? So since this region here corresponds to very low period superlattice, obviously the first question, we can wonder about the material quality, but in terms, for instance, of chemical material quality in intermixing. And in this TM image, this corresponds to a superlattice of 5 unit cells neodymium and 5 unit cells samarium, repeated several times. So it's one of the superlattices where in transport we just observe one transition. So in these beautiful images, what we can see is that the location of all the different cations, but maybe it's better we just directly focus to this plot here where everything is superimposed. And what we see here that we can clearly define the layers containing samarium and neodymium. So it means that chemical intermixing cannot observe or cannot explain our results in the superlattices. So the other possible explanation could be the coupling of the oxygen octahedra across the interfaces. So on an interface, we have a strain, but we can also have this coupling of the oxygen octahedra that, as it has been shown here, it's a very efficient way to also manipulate the properties of the system. In the case of the nickelates, and as we have seen in the phase diagram, the metal to insulator transition is very susceptible to the nickel-oxygen-nickel angle. So we can think that as we reduce the thickness, we are just stabilizing the same nickel-oxygen-nickel angle in the whole heterostructure. So if we turn to our superlattices, here we have the DFT calculations done by our colleagues in Liège, again for a 5 unit cell periodicity sample that is insulating in transport. And what we can show, or what we plot here, is that this nickel-oxygen-nickel angle for different as function of for the different layers. Sorry. And it's just, maybe let's focus in this out-of-plane nickel-oxygen-nickel angle in one of our periods. What we see that even if it's just 5 unit cell layers, the neodymium nickelate has the more adopts the nickel-oxygen angle that it would like in the film, and the same happens for samarium. So in fact, we just get 1 layer, maximum 2 of transition. So if we now turn to the experiments, what we see in this transmission electron microscopy images is that we can extract the antipolar motion, or also we can extract the nickel-oxygen-nickel angle from these TM images. And again, what we find is that each neodymium has its own values, and its samarium nickelate layer, also the values that it would like to have in bulk, but in fact, we just have 1 layer, 1 transition layer. So the coupling of the nickel-oxygen-nickel angle or the stabilization of a unique nickel-oxygen-nickel angle is not the reason why we have such a behavior in our samples. So instead, what it's determining the critical wave length that we have observed is the energy cost of having a phase boundary between our metallic and our insulating phases. So that is when we have a metal and an insulating phase. Here we have a phase boundary that it costs a certain energy, and therefore our films or our layers needs to be at least 3 nanometers thick, so that the gain in energy by establishing the bulk phase in fact compensates this cost in energy of the phase boundary. So I will not go into details, but if we go back to our diagram, where here we have the experiments, points, we can develop a Landau model using the electronic disproportionation as an ordering parameter, and this the results of the Landau model is this dashed line here, which indeed allows us to reproduce the experiments. So the critical wavelength for establishing this metal and insulator phases is in fact determined by the energy of this phase boundary. Okay, So far I have been focusing in the perovskite structure, and what we have seen in the case of the nickelates is that depending on the A cation that we have in our perovskite structure, we can determine the metal to insulator, or we can change the metal to insulator transition temperature. Now, another kind of doping that we can imagine in our system is substituting half of these B cations by another transition metal cation. And particularly if we do this in a kind of ordered way, we can end up with what we call a double perovskite structure, as the one that is here depicted, where we have B and B prime cations that they alternate nicely along all three directions. So one of these materials in which we are interested is lanthanum 2 nickel manganese oxygen 6. This material is interesting because it's an insulating ferromagnet with a relatively high Curie temperature, very close to room temperature. In this case, magnetism, or particularly ferromagnetism, is achieved when one has a long-range order of these manganese 4+ and nickel 2+ cations, which interact strongly ferromagnetically accordingly to the Gudenaf-Kanamori rules. We have been growing these samples, and here again, let me just show the high crystalline quality of the films that we are growing. And I think it's quite interesting that if we take these EDX TM images, which had been taken with the 110 on Macis, essentially what we see, if we look here on the top, that in the regions where we have manganese, we don't have nickel, and indeed in the regions where we have nickel, we don't have manganese, so, which really proves the long-range order of manganese and nickel in these films, and this is also translated in the bulk properties that they show these films in terms, for instance, of saturating magnetization, and also in terms of the Curie temperature. So in all these films, we are achieving bulk-like properties, despite these films are just about 30 unit cells. So, and also it's quite relevant that this transition temperature, this Curie temperature, seems to be independent of the applied strain. Okay, we can grow these films. So the question that happens, and this is a general question that happens in many oxides, is what happens as we make the films thinner and thinner, because we know that many oxides tend to lose the functionality of interest as we grow just very few layers. So this is in fact just a cartoon. So what we are doing in our lab is every time we are growing a sample with a different thickness. And one of the characteristics, or one of the systems that we have, is a RIT-enabled sputtering, which allows us to monitor in situ the thickness of our layer. I'm just here emphasizing that it's a RIT sputtering because typically RIT is not happening with a sputtering due to the presence of the magnets, but here we managed to implement this technique. And it's quite nice because just following the oscillations, we can, if we stop on the top of an oscillation, we know that we have complete 1 unit cell, whereas if we stop in the bottom, we know that we just have half coverage. And obviously here you have final thin films. Okay, so we can just now turn to the magnetic properties of these samples as function of thickness. So here I'm plotting the magnetization as function of temperature for several of these double perovskite thin films of different thickness. And what we can see here is that films that are 30 unit cells or thicker, they really have the expected transition temperature around 280. However, as we make the films thinner and thinner, this Curie temperature decreases. However, I think it's still quite interesting that when we have just 5 unit cell thin films, about 2 nanometers, we see still a Curie transition temperature around 200 and around 100 when we just have a 3 unit cell thickness. These are just bare films on top of strontium titanate substrate. These results for the lower thickness samples, they have also been further proof through XMCD measurements. Here particularly, I'm showing the XMCD nickel integral of the nickel edge as function of temperature for these ultra thin samples, where we see that the squid and XMCD nicely matches. And in this case, we could, in the XMCD, it even seems that the 2 unit cell thin film are still ferromagnetic. We can measure XMCD not only as function of temperature, but also as function of the applied field. And again, we see that these films are really still ferromagnetic. ferromagnetic. So it's quite interesting because it's very thin, ultra thin films, about 3 unit cells, maybe 2 unit cells, are still ferromagnetic. However, it's clear that if we plot, for instance, the Curie temperature as a function of thickness, the properties, or particularly TC, decreases faster as what we would just simply expect from simple dimensionality effects. So in order to further understand what's going on in the system and what makes this a faster decrease of TC in the system, we can turn to X-ray absorption spectroscopy measurements. So here I'm showing the XAS at the manganese edge, and just for those who are not familiar, we can just compare to reference spectra, and essentially the existence of these 2 main peaks clearly indicates the presence of manganese 4+ in our samples, as we would expect. However, as we make the films thinner and thinner, what we see is that we have some additional spectral weight developing here in the middle and also at the pre-edge. And this can be, the presence of these additional features can be clearly compared to the presence of manganese 3+. So in our samples, as we make them thinner and thinner, we have an additional presence or an emergence of manganese 3+. And we can also look to one specific sample, the cross-section, and this is again a TM image of a 14 unit cell, lanthanum 2 nickel manganese oxygen 6 on top of a strontium titanate. And now what we can do is at the yields, we can resolve the manganese yields spectra at each of these layers. And what we see is the upper layers, they have manganese 4+, but close to the interface is where we have manganese 3+. And maybe we can also, it's difficult to say, but maybe there is also a bit of manganese 3+ in the upper layers. Moreover, what we also see that as we go close to the interface, we have some oxygen vacancies, as it can be seen through the shift of this peak to higher energies, and to some extent maybe in the upper layers of the field. And these different features also correlate with what we observe in terms of ordering. So in the regions where we have manganese 3+ and a bit of oxygen vacancies, we see that we are not achieving the nice range order that we achieve above. So we have a region about 5 unit cells where we have a combination of manganese 3+, oxygen vacancies, and also partial ordering. And this is precisely the region where we have all these coexistence or reduced magnetic properties. So just very rapidly, let me know that by growing thin films on top of different substrates, we can exclude strain-induced oxygen vacancies, because it doesn't matter the strain, the sample that has larger amount of manganese 3+ is the one grown on strontium titanate, followed by the one grown on LSAT. Instead, what is happening in this system is that the existence of a polar discontinuity is what is playing a role. So if we turn now to our perovskite structure and we just look it as into planes, we can just plot these planes and count the nominal charge in these planes. And what we see that we have a polar discontinuity as we move from the substrate to the double perovskite structure. So this is similar what is happening in the so well-known case of lanthanum aluminate strontium titanates as heterostructures. So in these systems as well, in order to compensate the polar discontinuity, what we have is charge transfer to the interface, resulting in this manganese 3+. But differently to the LAO STO case, in this case, the additional electrons stay within the double perovskite layer and they are not transferred to the interface, to the substrate interface. So we don't have to deck, but just doping of this double perovskite. And moreover, we have also seen that if we have some allow for oxygen vacancies, they may also populate the first layers close to the substrate, and we may also have some oxygen vacancies on the top. So this complex interplays is what it's explaining this, the polar discontinuity explains the reduced properties of the samples. And moreover, I think it's also quite nice to see that as soon as we have more electrons in our system, then the ordered double perovskite structure is not the favored structure anymore. So just before finishing, let me just rapidly show you that if we have manganese 3+, we can just imagine that we put a layer such as nickel containing nickel 3+, and then because of the difference in electronegativity between these two atoms, we can just expect charge transfer from manganese to nickel, and then recovering the manganese 4+ configuration that we would like. And this, what we have done is we have just capped with a very thin layer of lanthanum nickelate, which is non-magnetic in this case. And here now, if we look again the SAS spectra at the manganese age that now we understand. So if we look at the uncapped film, we see that it has a large amount of manganese 3+, but simply by capping this 2-unit cell film with an additional lanthanum nickelate layer, the amount of manganese 3+ is drastically reduced. And if we look at the TM measurements, it also seems that somehow, or at least a bit, the order is also improved. But what it is more important that if now we compare the XMCV magnetization as function of the applied field at the manganese age, so this is the one for a 2-unit cell uncapped film compared to the cap layers, the magnetization drastically improved. And moreover, if now we plot again the Curie temperature as function of the LNMO thickness, we just see that in this ultra-thin regime, the Curie temperature has drastically increased in these cap layers. And moreover, if we plot as function in the linear scale the thickness, we see that now it extrapolates to 0 as we would expect somehow by dimensionality effects. So with this, I would just like to finish highlighting obviously the people who has contributed to the work, especially Claribel, who did most of the work on the superlattices, on Gabriela, on the ultra-thin double perovskite layers. And obviously I should highlight our TM collaborators, the synchrotron collaborators, and our theory collaborators. And with this, I would just simply like to conclude that we have used neodymium nickelate, samarium nickelate superlattices that are structures to further investigate the critical thickness of the metal to insulator transition. And we had also been investigating very ultra-thin films of double perovskites, which are still magnetic. And with this, I would just simply like to thank you for your attention.
Thank you very much. Some beautiful images there, the TEM. Are there any questions? Yep. We'll just wait for them to come down to the front to ask you the question.
Okay, yeah, no problem.
Kind of an off-the-wall question on your heterostructures. So your diagram shows how the film thickness determines the transition temperature. I'm just kind of curious, what if it is simply a solid solution for the neodymium and the samarium? How does that affect the MIT?
So in the MIT, let me just show you. Yeah. So a solid solution, in fact, has it should be a point here that it has exactly the same metal to insulate. It's the same transition temperature. However, it's clear that in this case we don't have a metal to insulator transition. This is just 5-unit cell sample, so which would be the one that we have here. But yeah, it's part of the model. Yeah, it would go here. So it's in line with these results, yes. Is this answering your question?
Well, I mean, if you have the solid solutions that the neodymium and the other metal are randomly, so you don't have two different compounds, but just have a single one, which is the mixture. Do you get like an average temperature for the MIT, or the MIT is completely suppressed?
No, the MIT, it's going to be here. Can you see my pointer?
It's going to be at the low temperature. Okay.
Yeah, it's going to be here.
Right. At the low temperature. All right.
Yeah, sorry, you couldn't see my pointer.
Thank you again. We've got an announcement, I think.
Okay, so unfortunately, COVID affect our life, and one of us is this morning was positive. I was getting informed this morning around 11. So we are closing this section with this, and then this hall and the other environment will be sanified. So this means that for today, we can, the next session will work in remote. And maybe the next one, I think there is only one or two which are in presence. But unfortunately, we cannot go to the cafeteria, me included, all that take part to the conference. Tomorrow, we can restart the operation here because it will sanificate, but to get in, we need a test. So everyone that wants to participate tomorrow to the conference inside need to show a test, even a rapid test done today or tomorrow morning. I apologize for this, but these are the rules, and we cannot manage in a different way. So if you need more information, if you want something, I will be available outside, eventually even for arrange a test in the afternoon today, or in Rome, there are many places where you can do tests. That's the scenario we have to face. So I invite you to sanificate your hands, to use a mask, and that's all. We can do much more now. It up. Okay? How? So the first session cannot be done here, only remote, because after the sanification, you cannot get inside at least for 1 hour because of the sanification. So the next session will be essentially in remote. I think the majority are in remote, but there are people. So I don't know exactly how to manage, but that is the only way. For the last one, we can probably return, but I think there is only one, which is in presence, apparently. So you are free to do whatever you like, okay? And for tomorrow morning, just to remind that you need a test, okay? No, you just show the rapid test when you get in, okay? Excellent. So if you want more information on that, I will be outside. So let's go to the final.
Okay, guys, so maybe it was not clear. There is still my talk here, for now. So we can conclude this session, if you want. Then from the next one, we'll not be allowed to be here, because of the sanification. Okay? So, okay, it's a pleasure to be here. Yeah, I think I can go. So, I'm Alessandro Delia. I'm here to present you the latest result of my investigation on vanadium dioxide on titanium dioxide film. So, for the one who will stay, thank you for your assistance. Okay, so brief outline. Introduction on vanadium dioxide metal insulator transition. then why I decided to study this specific crystal orientation, and then the results, basically. So very quick, vanadium dioxide is an oxide. It undergoes a reversible metal insulator transition around 67 degrees in bulk. And at the same time, it undergoes a monoclinic to tetragonal phase transition. So of course, this attracted a lot of attention because it has a span of 10 to the 3, 10 to the 5 order of magnitude, 3 to 5 order of magnitude in resistance. So the phase transition was long debated because of its physical origin. So it was thought in the beginning to be a Mott transition, therefore driven by electron correlation that opens a band gap at Fermi level. But at the same time, since there is a structural phase transition, also the electron-phonon coupling could drive the metal-to-insulator transition through a Peier's pairing mechanism. Nevertheless, in the last years, basically the scientific community more or less converged on a cooperative mechanism of these two pictures. So, possible application, so metal-insulator transition-based memories. In this nice video here, you can see an actuator which is light-induced, and it exploits the structural phase transition to perform nano-actuation triggered by a laser, or as Professor Zhu said, energy conversion and saving application, basically. So being a strongly correlated material, vanadium dioxide phase transition can be controlled by multiple degrees of freedom, and therefore it can be controlled basically by using different kinds of stimuli, increasing its versatility. So I will very brief here why vanadium dioxide 101. So I was just reading this article by Hong and collaborator, and I noticed something. These guys take the care to study also the intermediate case of strained vanadium dioxide films. So usually you study the 001 orientation, which has the C-axis of vanadium dioxide perpendicular to the surface, or the 110 or 100 that has the C-axis in plane. This guide studies the 011, which is the twin of the 101. In this case, the C-axis is in diagonal. And as you can see here, the phase transition, the resistivity drop is in between the two extreme cases. So I dug a little bit more, and I find this article, which is a little older, and you can find also here the 011 surface, which is in between the 001 and the 100. But what I noticed that in this article that they did a little bit of diffraction, some measurement, and they saw that with the thickness of the film, you had the C parameter, which was increasing. And this sounded strange to me because it went against everything I knew about the phase transition of vanadium dioxide, since the correlation, the critical temperature is positively correlated with the length of the C-axis. So the more it is long, the more it is high, the phase transition temperature. So I only had one chance, and it was to study a set of three strained samples of vanadium dioxide 101 of thickness 8, 16, and 32 nanometers. So, of course, so this is a brief outline of the crystal structure. You have the tetragonal unit cell, and then the surface with the 101 and minus 101 lattice vector in the plane. And if you see at the top where the sample surface goes outside the screen, you can see the A and C lattice parameter. So the expectation was, since the in-plane lattice vector 101 and minus 101 increases because of the strain, since titanium dioxide has larger lattice parameter than vanadium dioxide, I expect one of these three possibilities, since the in-plane vector depends from A and C, and it must increase. So, or CR increases and A decreases, or C decreases and A increases, or they both slightly increases. So of course, to solve this minor mystery, I did some diffraction. So you can see the diffraction pattern of the 101 peak around the 101 peak for the 32 nanometer film in the insulating and metallic phase. So you can see this delta theta shift, which was expected from bulk data to be 0.09 degree, is actually 0.02 or 0.03. That this tells us that the structure is heavily affected by the strain. In addition, anything? Just next slide. So in order to measure the lattice parameter, we had to do some asymmetric diffraction, and we made the reciprocal space mapping of the 301 peak. So the shift is the opposite as in the 101, and this is because the 301 basically has a 3A lattice parameter inside its composition, let's say. Anyway, we managed to measure the lattice parameter, and we found that with respect to the bulk, we have a compressive strain on the C-axis and a stretching strain on the A-axis. So one minor mystery solved. The C-axis is actually decreasing. This explains the decrease of the phase transition temperature. Unfortunately, for the thinner film, the signal was not strong enough to perform the RSM. Nevertheless, we can see the same trend also for the 16 and 18 and 80 nanometer films, and this is confirmed by the fact that measuring the two extrema samples, so 8 and 32 nanometer, if we measure the resistance, we can see that the transition temperature decreases, and therefore the C-axis is shortening as we go to thinner thickness. So very quickly on the band structure of vanadium dioxide. So each vanadium atom is surrounded by an oxygen octahedra. The hybridization between the oxygen 2p and the vanadium 3D electrons generate this pi star band. In the metallic phase, it crosses Fermi level, while the hybridization along the C-axis generate this d parallel band. So what is important here that the electronic structure is strongly anisotropic. So the d parallel band is oriented along the C-axis, and the pi star is oriented along inside the AB plane. If we apply some strain, reducing the C lattice parameter, what happens is that we are increasing the overlap within the vanadium 3D wave function. This will upshift the d parallel star. At the same time, we are increasing the apical oxygen distances, and this will shift down and destabilize the pi star. The overall take message is that the orbital hierarchy is inverted, and there is a change in electron population between d parallel and pi star. So to investigate the electronic structure of this system, I performed some Xanes measurement at the vanadium L3 edge, and our sample is such that, as you can see from the left sketch, we are in a lucky geometry in which we can perform linearly, linear dichroism. So just rotating the sample, we are able to align the polarization vector along the A axis or C axis. In the central panel, there are the vanadium L3 edges for the metal phase, for the 3 thickness, and for the 2 polarization. And we performed the dichroism calculation in this region mostly to be coherent with the literature results that we found. And we can see that the dichroism increases while we reduce the film thickness, and therefore this confirms that the parallel star occupancy is decreasing as the strain increases. Then we move to study the valence band. So this is just a model, not data from this sample. And the valence band of vanadium dioxide can be modeled as with 2 peaks, basically, that are generated by 2 different screening channels. The ligand hole screening channel, which is a local screening channel where the photoelectron hole is screened by oxygen atoms, and the coherent hole screening channel, well, there is a cooperative mechanism that screens the photoelectron hole. So having this in mind, we performed some resonant photoemission in the 3 films, aligning the polarization of the light along the C-axis and the A-axis. You can see the results here in the left. There are reported the resonant photoemission spectra for all the 3 films normalized to the photon incident flux. And you can see that except for the 16 nanometer, which where something unclear happened to our sample, but you can see that when the light polarization is aligned to the z-axis, we have a much stronger coherent Hall contribution, while when it is perpendicular to the z-axis and therefore parallel to the a-axis, the coherent Hall contribution is much smaller. This means that actually the band along the z-axis is much more metallic as we respect to the one oriented in the plane. So the parallel results to be more metallic than pi star. Using this relation, basically in resonant photoemission, you can correlate the normalized intensity to the screening length, and we did it. We integrated the spectra, and you can see the trend as a function of the polarization that tell us that the thinner the film, the overall metallicity of the film is being reduced. Most likely because thickness is just a thickness effect that reduces the number of electrons inside the samples. But if we model this the screening length, we can calculate the ratio between the screening length due to the D parallel band and the one due to the pi star band. And if we make the ratio, we can see that this ratio between the screening length along the z-axis and along the a-axis, it decreases as a function of thickness. Same time, if we adopt this model, the same is true for the effective mass of the bands. So some consideration on this. So first of all, the first one is that these data are in good agreement with some independent ARPES measurements performed by Johnson and collaborators, where they measure the ratio between the effective mass along the z-axis and along the a-axis to be 1.5 for a 20 nanometer thick film, and for 20 nanometer we may be around 1.35. So not so bad agreement. But most important, we see that the trend as a function of the film thickness points out that the ratio between the effective mass or the screening length tends to 1 the more the film is strained. This tells us that basically the strain is controlling the orbital anisotropy, and the electronic structure of vanadium dioxide 101 becomes more and more homogeneous the more the film is strained. So the parallel and pi star are more and more similar the more the strain is increased. So in conclusion, so we solved a minor mystery using X-ray diffraction. We demonstrated that vanadium dioxide 101, when it is strained, actually has a reduction of the z-axis, and this is positively correlated with the reduction of the TC. We demonstrated also in this sample that there is an electron transfer on an orbital band population inversion between the parallel star and pi star as a function of strain, and that the anisotropy of the band structure of vanadium dioxide is actually controlled by the strain, where we measured the ratio between the screening parameter of the C and A axis, or the effective mass as you wish, tends to 1 the more the strain is increased. So strain control the electronic band's anisotropy in vanadium dioxide. I would like to acknowledge all the people who helped me in this work, and okay, the few survivors of you who are here. Thank you.
Thank you very much. That's all. Are there any questions? I don't think so.
It's okay.
Thank you very much.
No problem.
Forse perché non sono più... No, questo no. L'ho già fatto ripartire stamattina.
Ah, di nuovo?
Sì. Questo darsi che rimane acceso. Oh, Alexander, I don't know when to restart, so maybe even Maggio is linked. So Ivan Maggio is the first. Brosco.
Yes, that's right. That's right.
And Brosco is the second. I don't see him. I don't see him.
Yeah, that's right.
I'm not able to start the video. That's my problem. But I can see you, and I can hear you. And
that's okay.
So maybe now it's 2:30.
It's 2:30. That's right. But we only have one speaker so far, and
So
7 participants.
I think since the session will be in remote, you can manage much easier and eventually close if people is speaking too much.
Yeah, yeah, no problem.
And so maybe in 2-3 minutes you can start with Ivan Maggio if he's available. Okay.
That sounds great. Yeah. Oh, I see Valentina. Valentina is online now.
Okay, so I'm now I'm going in my room, so I will monitor things. So here
oh yes,
the
great.
Regia is here, so they will continue to monitor the registration. That's all. Okay.
That sounds great. And there is thank you. There is right now a bit feedback, but I think it's just from your microphone.
There is a feedback.
Yeah, I think we might want to turn off the sound in the room or somehow disconnect the room.
Yeah. I don't know. There is in effect.
There's a big echo. Big echo.
Yes.
Maybe just mute the microphone. I think that would be just fine. Just mute on Zoom. Why don't you try and mute it, and I'll tell you if it's okay. So just Augusto, just mute yourself, and I will tell you whether it's working. There's still quite a bit of sound, quite a bit of noise. Try to just mute for a few seconds, because there's no one in the room.
Now is better?
Now is a little bit better. Yeah, but I can still hear myself. There's echo. Yeah. Will you eventually mute yourself? Because, yeah, oh, yes, this is perfect. Yes, so for when the speaker speaks, this is the mode. This is the right mode. This is the best. This works great. Yeah, thank you, Augusto. I appreciate it. I see that more people are joining, so we will be able to start maybe in a few minutes. I'm inclined to give the speakers maybe start the session maybe 5 minutes late, just to give more people a chance to join. Ivan, would you like to share your screen? Because you're the first speaker.
Do you hear me? Can you?
Yes, I can hear you. Yes, yes. Do you want to try and share your screen? Just so that we make sure that everything is working.
Do you hear me now?
Yes, yes, I can hear you very well. Yeah.
Because I have a big I have a big connection problem. The Wi-Fi of my room is not working, so I'm using my smartphone to make the bridge. So
okay.
It will last enough. Okay, so I will try like that.
So I can hear your voice very nicely.
Okay, good. So I'm switching off the video because I'm not sure the bandwidth will be okay.
Yeah, that's a good idea. Yeah.
And for the share, I guess here.
Yeah.
Just wait, I'm coming. Can I share this?
Okay, that is great. So let's wait for a couple of more. Yes, I can see it. It looks very nice, and I can hear you too. So I think
good.
This is good.
I think, how many minutes do you want to wait? I will switch off the Wi-Fi for the number of minutes, and then I will turn it on again.
Oh, okay. Let's wait for maybe 3 more minutes.
I think,
yeah, because we already have 10 participants. I'm guessing people will be joining soon. Well, hello, everyone. I think in the interest of time, we should go ahead and start the session. I'll be chairing the session. I'm Alex Gray from Temple University. Our first speaker is Ivan Maggio-Aprile from University of Geneva. Please go ahead and start. I can see your slides, you can see your screen. You're good to go.
Do you hear me? Also? Do you hear anything?
Yes, yes.
Okay,
you're good.
Great. Okay, I'm sorry. I'm not turning on the video because my bandwidth is quite limited here. So, okay, let's start. So, first, let me thank Antonio and all the organizers for the invitation. Okay, it's a strange session instead of present, but okay, we try to do our best to go to the end. I hope my connection will survive for 25 minutes. Okay, so I'm going to present to you some scanning tunneling spectroscopy measurements we have done in Geneva on cuprates. Now, can switch. Okay. So, okay, once again, this phase diagram, I'm not willing to describe all the phases, but let me just illustrate what STM has done yet. So, try to probe a lot of these different phases. The interesting ones being these charge density wave regimes, which are pretty new actually, and are a bit merged with the pseudo gap phase. And so STM, of course, is an ideal technique to probe that kind of modulation, charge order. So I will not focus on this specific feature, but you will see that from the study of the vortices we're doing, we might say something about possible problems when we detect this kind of modulation. So, of course, all these phases have been investigated a lot, and there were so many different theories trying to understand different phases, different mechanisms at the origin of the high temperature superconductivity. Many of the recent ones are focusing on this charge density wave. But let me draw your attention of a pair density wave scenario, which actually emerged quite a long time ago, and is from time to time revived, and probably also you might know some STM measurements which are specifically devoted to the study of this pair density wave scenario. And here is an example published in 2019 where actually the pair density wave or the fluctuating pair density wave scenario is taken as the mother order. So it's behind everything, and it's at the origin of the pseudo gap of the charge density wave. And so, okay, this is still debated. It's not clear. Some measurements focus like here in the vortex cores at high fields. And the author claimed that they could detect this phase, this periodic modulation associated with this pair density wave. I'll come back at the end of the talk to that problem. So the main question is actually, yeah, the ITCs are on many aspects not so conventional. We know that on the overdoped side, they might be a bit less exotic. And this is where we focus. Actually, I will show you that in this study. And the question is, are the vortex cores so unconventional in the ITCs? So, okay, this is the outline. So let me start just a brief presentation of what is expected from STS in the course of the vortices. So you see, okay, STM, you know, is a nice technique to probe the vortices because the spectroscopy which is acquired at the center of the course is different from the one acquired outside the course. And the reason is that the order parameter in a vortex shrinks at the center of the core, both in amplitude and in phase. As a consequence, this kind of potential well leads to the formation of discrete excitation levels. So the different levels are at least in conventional S-wave superconductor, the levels are spaced by the magnitude delta square over EF. And usually the spacing is really small. It's micro electron volts, so it's too small to be resolved at the usual temperature the STM works. So as a consequence, what you see is that the center of the core, you have a zero bias anomaly. And when you exit the core center, this feature splits in two, and then the two peaks merge into the superconducting gap. So this has been observed on a lot of superconductors, conventional SWF superconductors like the vanadium disulfide or iron selenium. And again, here you cannot see the individual bound states because of the spacing. There is a case which is quite recent in the iron, tellurium, and selenium compound where the Fermi level is so small that the spacing between the levels starts to be large enough, and you see here in the figure that the first peak you see is the first bound state taken at the center of the core. But that's quite exceptional for a conventional superconductor. And now we know that the cuprates are not S-wave but D-wave, so the gap has nodes. The picture doesn't really change. Actually, if you try calculating the spectra you acquire at the core, at the center of the core, you will also get a zero bias anomaly. You will get a split while going out from the core. The only difference is that here there are no bound states. So whatever is the temperature, whatever is the EF, you will never see individual bound states. There will always be a continuum of excitations. That's the main difference. So in the case of the cuprates, we long time ago measured the YBCO 1, 2, 3. And what you see here in the figure, so the top figure is the vortex disordered lattice in YBCO, and the bottom figure is the spectroscopy. The last spectrum is the one taken at the center of the vortex core. And what you see that instead of the zero bias anomaly, which is in the case D wave, we have a set of low energy states that we call subgap states for the rest of the talk. And these subgap states are not explained at all from the BCS framework. As I told you, the D-wave spectrum should also present a zero bias anomaly. There were a lot of models trying to understand this feature at the center of the core, like adding an order parameter here. In this case of Franz and Tezanovic, they added a DXY component, and then the result was a finite gap at the center of the core. But none of the models were really satisfactory. And in addition, we started more recent measurements of YBCO, and you see here a trace of spectra taken from the outside to the inside of core in YBCO, and you see that this subgap state, they remain all along that. So even outside the vortex, we have the signature of these low energy features. It's even more evident in zero field when there are no vortices. You see here on the left a map of the gap of over 120 nanometer area. The average spectrum showed on the right clearly resolve this subgap state. So even in the absence of the field, we have this state. So they are not linked to the cores. So we had a very simple model to try to understand, and the model is considering two different channels for the tunneling current. One being non-superconducting, it's the one carrying this low energy feature, the conducting background, and the other one being completely purely superconducting. And the simple addition of the two is able to mimic the spectra we measure. Actually, the non-superconducting channel is dominating, so it's almost 80 to 90% of the total current. And so what we did is we took a reference spectrum from the map and then made a subtraction of all the spectra with this reference. As a consequence, this non-superconducting channel, which is assumed to be homogeneous, is cancelled out, and then we remain with the difference of two purely superconducting spectra. And the idea is that here we can compare with a model which calculates this superconducting spectra when a distribution of flux line is provided. This is what I show here. You see the bottom are calculated spectra where the vortices have been placed exactly where we measure them. And you see on the right the difference of the spectra with the reference, and the matching between the calculation and the measurements is quite good. Especially if you consider specific crystallographic direction, like here, the 100-110, you see that the decay of the zero bias anomaly along the is not exactly the same. In 100, the decay is much takes place over much longer lengths than on the rest. Okay, so that was YBCO. Now I will show you the BISCO, which is always taken for better samples because you can cleave them, so the surfaces are cleaner. And this is a measurement taken across a vortex in optimally doped BISCO, and you also see that you don't see the zero bias anomaly, and you also here see the small feature at low energy, similar to the one seen in YBCO. Now, in addition, okay, we know that these pseudogap and charge density wave regimes are detected by STM by showing this modulation, the modulation that the electronic modulation seen in the figure here. The period is of the order of 4 unit cells. This was taken above the critical temperature in the pseudogap regime, so not in the superconducting phase. And you can also see the same kind of pattern at low temperature, but in the course of the vortices. And this is seen from a quite long time. You see that all the cores also reveal this kind of pattern. And if you compare the spectra and the different spectroscopic images, here on the left, you see the spectroscopic map taken at zero bias, or at the right taken at the position of the superconducting gap, and you see no pattern, no clear pattern at the center of the vortex. But if you probe if you plot the spectroscopic map precisely at the position of the subgap state, you see the modulation. So there must be a link between the position of these subgap states and the modulation seen in the vortex cores. Okay, so to get rid of these charge orders, we decided to measure heavily overdoped BISCO. This was TC of 52K, corresponding to a doping of 0.22. There is no pseudogap, as can be seen in the spectra shown at the bottom. So you see above the critical temperature, you have no feature at all, no gap, so no pseudogap. And again here, measurements taken, overdoped samples, high fields of 3 Tesla, and you see this pattern at the center and in the vortex halos. All vortices show that kind of 4x4 pattern. Okay, so in a sense that was a bit disappointing, but and if you take actually the trace of the spectra, you see the 4x4 pattern and no sign of zero bias anomaly at the center of the core. The other feature is that if you take the period of this pattern as a function of energy, you see a dispersion. And this is typical, typically illustrating the fact that this is a quantum quasi-particle interference, QPI, which is actually connecting the different portion of the Bogoliub of energy levels. So this pattern that we see in the vortex core is for sure QPI, and it's probably helped and enhanced by the presence of the vortices. Okay, so the other idea was that this QPI might be the consequence of the surrounding vortices. So the idea was to go to really low fields. So we use a permanent magnet to be really stable. And then the next measurement I will show you are taken in this field, which is 0.16 Tesla and not 3 Tesla. So you see here the individual vortices in the same heavily overdoped sample. And the first thing you see from the low energy spectroscopic map is that the patterns, okay, number one, you see kind of a small weak pattern, but in number 2 and number 3, you definitely don't see this 4x4 pattern that we see at higher fields. And moreover, if you take the spectra across the vortex cores, in that case, we recover a zero bias anomaly. Okay, the 3 different vortices are exhibiting slightly different spectroscopy spectra, but this is not such a surprise. But it's the first time that we definitely see a zero bias anomaly feature at the center of the vortex cores. So to get rid of the various inhomogeneities which are inherent to all bismuth-like compounds, ITC compounds, we made some four-quadrant averaging. Okay, so which smooth out the inhomogeneities, and you see here in the central spectra, like I showed you in YBCO, two different crystallographic directions with a zero bias anomaly at the center of the core, being the last spectrum. And here again, you see that the decay of this zero bias anomaly is not the same. It's much faster in the 110 than in the 100 direction. You see also that this low energy feature evolve and split progressively towards the superconducting gap. And this is precisely modeled by the calculation shown on the right, where the zero bias anomaly splits towards the superconducting gap with different decays along the different crystallographic directions. Okay. So one question was, okay, we see these zero bias anomalies. Zero bias anomalies in STM and spectroscopic measurement are quite often the consequence of impurities. So to check that the vortex and impurities, of course, are pinning site, very efficient pinning site for the vortices. So to be sure, we cancel the field with applying an opposite field to the 0.16 Tesla with the solenoid, the coil in our system. And what you see here is that at the position of precisely at the position of the vortex that we can really detect from the atomic, the right images or the atomic topographies on the same area of the vortex. So when the vortex is not present, as in the bottom, we recover the expected spectrum for a zero Tesla measurement. A very small gap. So we are definitely sure that the vortex signature with a zero bias anomaly is not a consequence of any impurity or defects in the area. So it's an intrinsic signature of the core. Actually, do you still hear me?
Yeah, we can hear you. Your connection is a little bit unstable, but we can hear most of it.
I guess, but I was not sure I was still with you. Okay, so good. Okay, so another, what you can extract from that kind of spectroscopy is from the zero bias conductance. You can get the profile of this of the conductance and fit it with a function which is routinely used in the vortex studies, which is this hyperbolic tangent, to get access to the coherence length. It's not the exact, perfectly exact model, but it's quite good to get a good idea of what the coherence length is in this system. We get a value of 2.7 nanometer. And if you try calculating the Fermi velocity, you end up with 160 kilometers per second. And the band structure with taking RPS values in a tight binding model is providing the same value for the perpendicular Fermi velocity. So we are confident that this measurement is quite accurate. And the 2 delta over KTC in that case is 4.5 at the minimum, which is quite low for bismuth compound, the high TC compounds. So they're usually much larger. But this was expected from the fact that we are really measuring on the heavily overdoped side. So the comparison here for the heavily overdoped compound we measured is that at high field, we have 2 consequences. So we see this 4x4 modulation. and we have no sign of any zero bias anomaly, which is expected from BCS. While at low field, we lose the 4x4 pattern. You see that actually the core is even, it's inhomogeneous. So we have a zero bias anomaly, which is clear, but it's not as smooth, the evolution is not as smooth as in S-wave convection at superconductors. One of the reasons is that the coherence length is really small. It's 2.7 nanometer compared to the tens of nanometer for the conventional superconductors like niobium diselenide. And this is also the reason why the evolution of the spectra across the vortex is not so close to the calculation. The rough peculiarities are here, but if you take one spectrum after the other, of course, you have quite a lot of variation. If you compare the various measurements which have been published, they all used a field which was above the measurement. So underdoped, optimally doped, or overdoped at high field don't show any zero bias anomaly. The only measurement that we did and revealing the zero bias anomaly was this low field in the overdoped. We didn't yet measure at low field the underdoped compound. This is, of course, to be done. But for now, this is the only measurement. So we know that from low field to high field, we lose the zero bias anomaly. So we lose also, and we gain the 4x4 pattern. Why this vortex core structure is so much affected by the field and the surrounding vortices, this we don't know. So we know from the calculations that depending on the surrounding vortices, you get three different configurations. The central part are the vortices actually measured on YBCO, and all the black dots are vortices which are randomly distributed around this area. And you see that in all cases there are slight variation. Take the first two traces. The split is not taking place at the same place, and so in a sense the surrounding vortices are really doing things to all the other vortices. And in addition, the lattices are never ordered, so always really disordered. So as a consequence, a single vortex core will reveal a specific signature. But from all the calculation we made, we could never completely lose this zero bias anomaly and remain with this subgap state we see at high field in BISCO and YBCO. So this is still something we have to understand. We don't know why the field has so much effect on the vortex core structure. Okay. So these measurements have been performed essentially in the PhD thesis of Tim Gazdic, and other measurements are going on with the PhD work of Tejas Singer in a group of Christoph Renner in Geneva, and calculation by Christophe Berthaud, also in Geneva. Okay, so as a summary, in both YBCO and Shmitt 2212, we recover the expected one McDonald electronic structure. In the case of BISCO, we had to do a kind of normalization by subtracting this unknown background we see uniformly over the surface. But on BISCO, we clearly see a peak which is lying close to zero bias and the splitting. Everything is really consistent with the D-wave picture, with the doping level and the Fermi surface topology we have. So it's pretty obvious that this 4x4 pattern, at least in the case of these heavily overdoped samples, are linked to the field, so the presence of the surrounding vortices, together with this zero bias anomaly, which disappears at high field, and that we still don't exactly know why it is so. Okay, so thank you for your attention and being here. And so if you have questions.
Thank you, Ivan. Thank you so much. The talk is now open for questions. Do we have time for maybe one or two? If you have a question, please go ahead and unmute yourself. All right, it looks like there might be no questions. So I'd like to thank the speaker. Thank you very much.
Thank you,
our next speaker is Valentina Brosco from CNR. Ivan, if you don't mind, could you please unshare your screen so that Valentina can share hers? Thank you. Valentina, could you share your screen?
Yes.
Thank you.
Okay. Let me.
All right, I can see your desktop.
Can you see it? It works.
Yes, your slides are coming up and you're now in the speaker mode. So please go ahead and start. Thank you, you're all good.
Okay. So first of all, I would like to thank the organizer for giving me the possibility to present my work. I did a slight change in the title, but the topic is essentially the same. This work was done in collaboration with the group of Massimo Capone. And well, the outline is quite short. It's about the interplay of Rashba-spin-orbit coupling and the strong correlation. I will first try to focus on the magnetic phase diagram and then discuss the paramagnetic mode transition. So a number of interesting phenomena in matter can be predicted just on the basis of symmetry consideration. So example are topological phases, transport phenomena, such as also weak localization. In this talk, we are gonna break two fundamental symmetries of lattice models, and these are parity and SU2 spin rotation. The typical example of interaction that breaks these two symmetry is Rashba spin-orbit coupling, that essentially is a node in K splitting of the bands stemming from relativistic effects and induced by structural inversion asymmetry. Let me just give you a quick introduction to Rashba spin-orbit coupling. So in general, when you have a free electron in an external potential and you do the weakly relativistic limit of Dirac equation, you get a term of this form that couples. You get a term of this form that couples spin and momentum. This term also affects the band structure, and essentially in two ways. So first of all, it gives a symmetry independent, let me call it like this, splitting of the atomic level. So this is present in all crystals, and the typical energy scale is around, for example, for gallium arsenide, 0.3 electron volt. So as you see, this affects essentially the macroscopic structure of the spectrum, okay? Rashba spin-orbit coupling instead requires a breaking of inversion symmetry. And the typical energy scale, for example, in quantum wells, the system where initially Rashba was studied, Rashba coupling was studied, is much smaller. It's about, let's say, 0.01 milli-electron volt. So this term essentially affects the shape of the bands, but not, let's say, the overall structure. Oh, sorry, this doesn't work, okay. And why it is interesting? But in my opinion, for two reasons. So first of all, is a prototypical parity breaking interaction. So as I said, it's a simple term that can be easily relatively easily included in the Hamiltonian, and it breaks parity, so it allows you to study a lot of effect associated to the breaking of this symmetry. And on the other hand, is tunable with external gates, because you can tune somehow the inversion symmetry breaking by external gates, or by constructing heterostructure. This means that spin-orbit coupling can be used for applications such as pure spin current generation, as it happened in the spinol effect, spin filtering, as in the data dust transistor, or the generation, as I already said, of topological phases. This led, let's say, to the birth of a new field called spin-orbitronics that essentially exploits spin-orbit coupling in non-magnetic material to manipulate, generate, detect spin-polarized currents for, let's say, electronics application. But related to the first fact, so to the fact that it breaks parity, you can already, that is associated to the breaking of parity, you can immediately realize that spin-orbit coupling is actually not so, let's say, not so rare. It can be found in many materials, and recently it has been also somehow engineered in various materials. So, for example, in optical lattices, in quantum gases, in correlated oxide with broken inversion symmetry, in Dirac materials, in surface alloys, and also is also present in the pyrochlor iridates. Some of these material have also a strong correlation, and some instead are more, let's say, weakly correlated. Essentially in all these systems, spin-orbit coupling is so strong that it can become really the dominant energy scale. And this is, let's say, the situation we are interested in. Since we want to look at the interplay of correlation and spin-orbit coupling, we will consider in particular this kind of systems, so correlated oxide, surface alloys, but also artificial, let's say, lattice systems. There have been many works studying the interplay of Rashba spin-orbit coupling and correlation. However, to my knowledge, there was no work studying the paramagnetic mode transition. So this famous work by J. Kelly studied the magnetic phase diagram. The Fermi liquid properties were studied by the group of Maslov, and more recently also superconductivity was studied by Maria Vittoria Mazziotti and by Antonio Bianconi. Oh, okay. Here, what we want to understand is if Rashba spin-orbit coupling can affect the Mott metal insulator transition. Okay, let me explain my model, which is very, very simple. It's just a square lattice with this spin-dependent tunneling and Hubbard interaction. So essentially, it has three energy scale: T, associated to the normal tunneling over the square lattice, TR, that is the Rashba coupling, and U, that is the Hubbard interaction. If we look at the Hamiltonian in K-space, we find two chiral bands. Okay, so this coupling becomes essentially sort of relativistic spin velocity coupling term. So you easily understand also the physics, that the physics is the same that we found in the original Dirac equation. And as I said, you find two bands. So the original dispersion of the square lattice is split into two bands, into two chiral bands that have essentially two terms. This epsilon 0 is the standard square lattice dispersion plus this term. If you look at the structure of the eigenstate, you see that they are essentially the overlap of spin up and spin down state with a k-dependent phase. Okay, with a k-dependent phase, and this makes this overlap. If you try to rewrite this state in a local basis, you get a very non-local state. And this is somehow the reason why it's so difficult to treat this problem with standard local approaches. So for example, we tried with slave bosons, but you lose like the main feature, the chirality of Rashba coupling, let's say. Okay, so to get some feeling of what happened, we decided to study a minimal system, a 4-side plaquette in a Rashba system. So essentially, this is just like a sort of minimal chiral unit. Okay, and when the electron tunnel along X and Y, they get the corresponding, let's say, spin rotation. The interesting thing is that, okay, clearly this has the symmetry of the square, but associated with appropriate spin transformation. So, for example, the Hamiltonian is invariant under pi half rotation. So if I rotate the square by pi half, the Hamiltonian remains the same, provided that I also rotate the spin quantization axis. Fine, so this also helps a lot in determining the structure of the ground state. Actually, at TR equals 0 and U equals 0, we can diagonalize the Hamiltonian exactly. And at TR equals 0, sorry, at U equals 0, we have essentially 4 Kramers degenerate doublets, and the first 2 are occupied. And the symmetry properties of this Kramer doublet implies that the ground state has S-wave symmetry, so it's invariant under pi half rotation, it's S-wave symmetric. On the other hand, when we go to finite U at half filling, the ground state is a singlet with D-wave symmetry. So we know already, I mean, the Hamiltonian, as I said, that TR equals 0 can be diagonalized exactly. And what you find is that the ground state is the overlap of different terms having different double occupancies. One is the standard, let's say, resonating valence bond state, and the other have 1 or 2 doubly occupied sites. Clearly, when U goes to infinity, you remain with the resonating valence bond state. The fact that the symmetry of the ground state changes is due to the fact that when you have an even number of particles, you don't have Kramers degeneracy that instead allow you to get the S-wave ground state. And this, in some sense, it reflects the many-body nature of the state. So we also at finite U and TR we use numerical hexadiagonalization to find the ground state, and what you can see is what you expect from the previous slide. So at TR equals 0, the ground state is D wave. Here I plot the energy of the D and S wave ground state. You see that at TR equals 0 you have a D symmetry, while as you increase TR, you have a transition to the S wave. These two states have a different symmetry properties, therefore the transition is clearly discontinuous, and you have discontinuity in a number of properties. At a certain value of TR that depends on U, you have this DS transition. Okay, clearly you can check, you have a lot of, let's say, continuity equation. The various terms are constrained by symmetries, for example, the spin current and the charge on the bonds. Okay, but this, of course, doesn't tell you what is the nature of this transition. This doesn't tell you what drives this transition. To see that, you have to consider the breaking of the SU2 spin rotational symmetry. So essentially, since you have spin-orbit coupling, S square is not a good quantum number. So while in the absence of spin-orbit coupling, we know that the ground state must be a singlet, in the presence of spin-orbit coupling, SU2 spin rotational symmetry is broken. So the ground state will in general be a superposition of singlet and triplet. One thing that you can guess on the basis of energetic consideration is that in the S-wave ground state, the triplet is dominating, and this you see it, and you can see this fact from this picture. You see, I plot the total magnetic moment in the D and S wave ground state, and you see that is much larger in the S wave than in the D wave. Okay, in both cases you don't have a well-defined total magnetic moment. Clearly, the total what you see here, however, is that the total magnetic moment, at least in both states, increases with increasing U, and this is somehow a sort of, and this is due to the fact that the system essentially creates the triplet creates triplet correlation to screen the interaction. Okay, so for example, starting at U equals 0, as we increase U, the first thing is that the triplet interaction increases. Then when they essentially saturate, so the effect of interaction cannot anymore be screened by increasing the total magnetic moment, the system makes a transition to the D wave. So essentially, by looking at the total magnetic moment, you can essentially draw a phase diagram in the space TR-U. And this is what we do here. So you see, you have really a jump for a certain value of TR in the total magnetic moment. So here, where you have a low total magnetic moment, you have D wave. Here, where you go to where you have a large total magnetic moment, you have S wave. Okay, this, however, still doesn't tell us anything about the mode transition. Okay, so this doesn't tell us anything about the mode transition, neither about the ordering, so the magnetic phase diagram. So to see that, we looked at the spin-spin correlation function. So you see here, as you can see here, so let's start from this figure here. At TR equals 0, what you have, and fine at U, you have what you expect, an antiferromagnet, so purely antiferromagnetic correlation. As you increase TR, what you have is that the system becomes this antiferromagnet, this initial antiferromagnet become anisotropic, and eventually it makes a transition to a state which has, let's say, ferromagnetic ZZ spin correlation and a sort of XXYY correlation with opposite sign, so a sort of vortex state. So using this kind of analysis, you can eventually draw a magnetic phase diagram. So you see that in the insulating phase, you essentially have an antiferromagnetic insulator at small TR. Then as you increase TR, you go to an anisotropic antiferromagnetic insulator. In the S wave ground state, you get first a stripe phase, and eventually a very large TR, you get a spin vortex phase. As you see here, let's say I added a metallic phase. Let's see why I added this metallic phase by looking at the gap. Clearly, this is a very small system, so we cannot really define a charge gap. We just looked at we define the charge gap as the difference between the ionization and affinity energy. So if you look at the gap, let's look first at this green line that has a very large TR and as a function of U, is the gap as a function of U. And as you see, it has a sort of flattish phase that I call Pauli metal. Later we will look at bulk system and understand what this means. And then it starts to grow linearly with U. And this I call the insulating phase. So if you look at this, you may let's say imagine that the change in the let's say in the slope of this delta C may somehow indicate the presence of a transition. And this is what we plot here. So we plot the second derivative in this plot here on the right, the second derivative of this delta C. You see that this kind of halo represents the mod transition. So it's this very, let's say, smooth change of slope. This very narrow peak is the DS transition. So it's really a discontinuous transition. And actually here you see also this weak line that is actually related to the onset of Nagaoka ferromagnetism. So this is a discontinuity in En-1, En+1. Okay, and it is known that spin-orbit coupling may enhance Nagaoka ferromagnetism. Okay, now we are ready for let's say now we are ready for bulk system. To get I mean, as a first step to go to small cluster, from small cluster to bulk system, to solids, we tried to use cluster perturbation theory. Let me say just a couple of words on the method. So essentially in cluster perturbation theory, you solve exactly the cluster and treat, which can be as large as you can. In our case, we took the plaquette because they were well controlled, were under control. And then you treat, let's say, perturbatively the coupling between the cluster. So in this case, the intercluster hopping, that in this case I call B. This method, and then basically by treating perturbatively the intercluster hopping, you calculate the green function. Then clearly this method breaks the periodicity of the lattice, and you have to restore the periodicity by an appropriate periodization, which in this case is done so to preserve all the let's say conservation continuity equation and symmetries, original symmetries of the different terms in the spin current and charge current. Okay, the nice thing of this method is that it gives you exact result both in the atomic limit and so at U infinity and at U equals 0, so in the fully metallic case. So if you do the periodization correctly, you recover essentially the also the non-interacting situation. So and that's one hope that at least it gives a good indication of how things go in between. So let's look at the result. So here, essentially, I show you some result in the very high correlation limit. So here the spin-orbit coupling is small as compared to the tunneling and to the Hubbard energy. As you see, essentially you see two Hubbard bands that are splitted, and each of the Hubbard band become splitted by get some chirality. This result here on the left is essentially is the result of Hubbard 1 approximation, you would call. So you just consider the in the very high for the Green's function in the very high correlated regime. So as you see, they are roughly similar. Quite similar. Now let's instead look at the transition, but you already see that there is an important difference, that is the strong K dependence of the spectrum and the fact that the Hubbard 1 approximation misses this spin wave part, let's say these satellite bands. Let's now look more in detail at how the transition goes. So how do we go from the non-interacting spectrum to the strongly interacting one? At the end, we have to go from 2 bands to 4, and and we want to understand how. So this is really the mod transition done with spin-orbit coupling in cluster perturbation theory. Okay, let's start once again from the Mott insulator TR equals 0. So this is this is the well-known case in cluster perturbation theory. gives reasonable result. Then you start to increase spin-orbit coupling, and you see the splitting of the two chiral bands. And okay, I have 2 minutes left. Wait, sorry. Okay, and the splitting. Oh no, and the splitting of the two chiral bands. As you increase Rashba spin-orbit coupling, okay, as you increase Rashba spin-orbit coupling, you see that the two bands start to, let's say, the two upper bands start to glue together, and eventually you arrive to this situation where you essentially reconstructed the standard Rashba dispersion. The blue and the red are just the chirality, but you see you still have a small gap here. Okay, so the gap closes at X and X prime, but it remains open in this part. Analogously, similar situation you have in the limit in which you have a large Rashba spin-orbit coupling, and you slowly decrease the U. Okay. Oh. Okay, now it's a bit, I still have some time. Okay, now let me show you 2 more results. So essentially, this is the total magnetization on the lattice. So essentially, I divided the magnetization into 2 parts. The first is the local magnetization, this red line, that as you see, it doesn't change much. And the blue line is the non-local magnetization. Remember that due to Lieb theorem, usually this total magnetization is fixed, so it must be 0, let's say. In fact, this is what you see here. But in the presence of spin-orbit coupling, somehow you are free to change this total magnetization, as in the Pauli screening case, as in the small, in the small cluster case. More interesting, if you want, is the gap. So as you see here, the total gap. So here I'm comparing the behavior of the gap as a function of TR in the presence of spin-orbit coupling and of an equivalent system having the same bandwidth. So essentially this T effective depends on TR, okay, and in such a way that these two, the blue and the red line, even if this does not have spin-orbit coupling, have exactly the same bandwidth. As you see, as you increase spin-orbit coupling has a very strong effect on the gap, which clearly closes. So it's essentially what we believe is that spin-orbit coupling gives a metallization. And okay, now here I show essentially the behavior of the density of state. And as you see here, as we cross, let's say, the mode transition. So as you see here, this is the situation where U is pretty small. Spin-orbit coupling just what does it does? So essentially here there was a Vanov singularity in the middle of the band, the two-dimensional square lattice. This is split in 2, okay, by spin orbit is this thing. But here you see some peaks start to appear due to the opening of this gap. Okay, and then you have the Vanov singularity at the band, let's say at the band edge, which was also mentioned by Maria Vittoria Mazziotti yesterday. As you increase this gap here around the gamma point opens, but here the system remain, let's say, semi-metallic. So essentially, it doesn't make a full transition to an insulator. Okay, in this part here, you have also a non-trivial spin texture. So because the two bands, the two chiral bands split, the two upper bands split by spin-orbit coupling intersect each other, and so you have this strange chiral spin texture, which also depend on where you are in K-space. Let me now give you what we think is the explanation of this, let's say, resilience of Rashba metal to correlation, and then I close. So essentially, what we have in a Rashba system are two kinds of fermions. So the nodal fermions, so look at this, this is the non-interacting dispersion for large TR, okay? So if you try to construct a low energy effective model of this system with interaction, so essentially you have two kinds of fermion. Nodal fermion here around the X point and also X prime point, and standard, if you want, fermion, parabolic ones, around the gamma point. The nodal fermion are known to be, let's say, resilient to interaction, also for graphene. I mean, and the transition has a well-defined value of the critical Hubbard interaction, while standard fermion instead become gapped immediately as you, at least in our model, as you increase interaction. So essentially, to describe this transition, you should make a two fermion model plus interaction to see what happens. This effect, in my opinion, have been also seen in some systems. So, for example, such as the surface alloys, but maybe I leave this for question if there is any. Okay, and there are many things to do, like here studying doping effect, inhomogeneities, superconductivity in this particular framework of strong correlation, and also do a many body theory of Pauli screening. That's all. Yeah.
Thank you very much, Valentina, for a very interesting talk. It's okay. In the interest of time, I think we should move on to the next speaker. Yeah. So, okay. So Valentina, if you could unshare your screen so that Krzysztof could share his. Yeah. So our next speaker is Krzysztof Wohlfeld. Krzysztof, please go ahead and try and share. Yeah. Okay, good. Something's happening.
Second.
All right. Yes, we can hear you. Oh, and Valentina, if you could also mute your microphone, that would be great.
Yes.
Let's see.
Yeah.
So, okay. This is great. So now we can see it in a presentation format. So please go ahead and start. Thank you.
Okay, perfect. Yeah, okay, good. So, let me start. I hope you can hear me. So just in case I lose the connection or something is unclear, please just ask and talk, okay? So, first of all, well, thanks a lot for inviting me here. It's really a pity that now it's all online, but well, that's life. So nevertheless, I hope we can still enjoy some physics now today in this afternoon. So the title of the talk is like a question where I basically want to understand the differences between outputs on quasi one-dimensional and quasi two-dimensional cuprates. And actually, I already stressed from the beginning, I mean just outputs on the undoped compounds. So before I start with the introduction, let me just tell you, like where we are in the cuprate phase diagram and in which limit is of interest to us. So I'm showing the phase diagram here of the cuprates. It's a bit different one than most of us have shown during last days, but nevertheless, it's also a valid phase diagram of the cuprates to some extent, a phenomenological one. So what we basically, like what I want to stress here with this phase diagram is that what we all agree, actually, especially coming from the theory side, I think I relatively broadly agree, is the basic models that describe the cuprates here, that can describe this phase diagram, and which are to a large extent, of course, I'm not claiming it describes all of the phenomena of the cuprates, but some of the most relevant ones. So the models that describe such basic phenomena that are found in this phase diagram are, at least it's wide belief, are the quasi two-dimensional Hubbard or TJ-like models, or this, that's even more highly probable is the free band or so-called charge transfer model. So, so that's like quite a broad agreement. Then the second point that actually is also kind of agreed or kind of understood is the point that here, when we have zero doping level, so we are exactly at this straight line here, at this vertical line, then this is the so-called undoped limit. Then we all know it's a Martin-Slater and quasi two-dimensional antiferromagnetic state here, and we basically understand the state. So we understand the ground state and the excitations, the low-lying excitations, and the temperature dependence of that. So that's kind of relatively well understood. What's of course puzzling is to understand with the model in question, like with a given model, like be it Hubbard, TJ, or charge transfer, the question is how to understand what's going on in this model and how it relates to this phase diagram of the cuprates. Yeah, so to understand really the mechanism of superconductivity, pseudo gap phases, and so on. Of course, there's a lot of progress here, but still, you know, that's the point that is not understood, as we all know. So where the talk is located is actually in a very special limit. So we are already in this doped limit, but basically infinitely close also to this vertical line. So what I want to discuss today is a peculiar limit of the doped case where we start with the undoped cuprates and we just add one single hole to the otherwise undoped ground state. So it's an extremely low doping limit, one can say, view it this way. And this actually is of interest, firstly for theoretical reasons, because it's the simplest doped limit of the cuprates, and secondly, because of experiments, because of ARPS, okay? Because it corresponds to ARPS on undoped samples, okay? So so that's like where we are, and now let me start with the introduction. So let me start with the first part of the introduction, which is the actually canonical understanding of this limit that I just showed. So what is the canonical understanding of what happens when we do ARPS on undoped compounds, like two-dimensional ones? Actually, here we start with these. So for instance, on this copper oxide and copper oxide chlorine, and then actually this limit roughly corresponds to the problem of, on the theory side, of looking at the single hole being mobile or moving around a two-dimensional antiferromagnet. So it's like for the theoreticians who are here in the audience, it corresponds to calculating the single particle Green's function or spectral function of the TJ model with the ground state being a two-dimensional antiferromagnet. Of course, this is a simplification based on the Zhang-Hai singlet picture. If we rather believe in the free band model and that the Zhang-Hai singlets are not really stable, then of course this all changes a little bit, however not that much as one would expect. And if you want to know details, there's a Nature Physics paper from George Savatsky and Mona Berchou from like already 8 years ago, which discusses this issue. In other words, if you feel that charge transfer model is the right one, still some of the physics that I'm going to present today will be valid. So that's why. Okay, so we are here on the theory side. It's a mostly theory talk. So we want to understand what happens if we put this one hole into the two-dimensional antiferromagnet, which corresponds to this experiment. Okay, so how to understand it? So this is like a very old story, and it's a very old concept, and I think some of you are extremely familiar with, but to those who are not, let me go through it. And also you have heard from this from me for several times, but anyway. So imagine we have this two-dimensional antiferromagnet pictorially viewed like that, and we put a single hole and we ask how it moves. So it moves by the electronic hopping here. It is allowed because the copper electrons can move and fill this empty side, this hole here. But when the hole moves from that side, for instance, to this one here, then it interchanges with the electronic spins. And because of this interchange, we see that we produces this string of black spins, which are aligned in a parallel fashion with respect to its neighbors. That's why they are colored black. So we say that the mobile hole overturns spins. Yeah, that's what is written here. But overturning spins, of course, costs energy. So each, because the neighbors are not happy. And this is more properly described in the Magnon language, where each overturned spin is a Magnon. So the moving hole just excites magnons. Yeah, at each step it excites one Magnon, and each Magnon costs the same energy here, roughly speaking. And this actually gives rise to the fact that the hole here feels a kind of a discrete linear potential. Yeah, why? Because the further the hole moves, the more magnons it creates and the more energy it costs. Yeah, and it grows. The energy cost grows exactly linearly with the distance of the whole motion. That's why it's a linear potential. It's also called a string potential because it's a discrete version of a linear potential. Okay, so the hole is in a string potential due to these excitations when it moves in the antiferromagnet because it excites magnons or it overturns spins. Of course, it's not the full story here, because what can happen also is that in such an antiferromagnet, there are the spin flip processes. These are the processes which lead to the magnon dispersion that you observe with neutron scattering or X-ray scattering on the cuprates, and these spin flip terms actually can restore these defects, or in other words, can annihilate magnons. So the magnons the hole creates magnons, but some of these magnons can be annihilated. Altogether, when one considers these two processes, the whole exciting magnons and the magnons being annihilated by the spin flips, we end up with a story where the hole moves around through this antiferromagnet, through the crystal, and it moves by coupling, with a cloud of magnons which fall over. And these magnons surrounding the hole just slow down the hole. Yeah, and this hole together with these magnons, it forms a quasi-particle with an effective mass and with a particular quasi-particle spectral weight. And this particular quasi-particle is called a spin polaron. It's a spin because of the magnet coupling to magnons, and it's a polaron because it's like coupling to, it very much resembles the electron coupled to phonons, and hence the name polaron. Yeah, because mathematically it's very similar. Okay, so it's a very old story, and there are lots of papers. Like it goes back to 1968 to a paper by Bulaevsky, Nagayev, and Komsky, and then it was all rediscovered kind of in the end of the 80s and in the beginning of the 90s by Kane, by Peter Horsch and others. And there are tons of papers from the 90s. So it's a well-known concept. And this is, it's so well known, not only because it's a nice, simple quantum many-body problem, but also because it's the essence of what happens when one calculates the Green's function, or the single particle Green's function, for the two-dimensional TJ model that you see here. So what you see here is the single particle spectral function of the undoped antiferromagnet calculated for the TJ model. And this is the momentum here, this is the energy. You see it's relatively incoherent, but there's a nice band here, and this band is the spin polaron band, actually. So it's where you can find this quasi-particle moving. It's actually in this spectral function. And you can also find it in the experimental, in ARPAS for instance, again, on this copper oxide, but also on other anode copper oxides. And you see a relatively good agreement between ARPES and the spectral function of the two-dimensional TJ model. Of course, one can go a bit better quantitatively with with more elaborate TJ-like models, but anyway, the essence is here. So that's why it's popular, because it is there. It is the physics of ARPES on undoped cuprates. Okay, so now let me go to the question that I would like to ask today. So the question that I would like to ask is, why is ARPES on 1D cuprates different with respect to the 2D case? So again, to the undoped. So, well, the first question is to show that it is different. So the question is whether can we use the spin polaron concept to describe the 1D version of the problem. So let's do the same, but now much like the previous slide. So let's show the theoretical spectrum function for the 1D antiferromagnet. This is shown here, and let's compare it to the experiment. Actually, this is on the quasi 1D cuprate. Here it's actually done on strontium copper 02. So to compare the spectral function, which is, for instance, shown here on the left-hand side, I hope you see my cursor. Anyway, so then in order to compare this directly with the experiment, what one has to do, one has to search for the dominant features of this spectral function, and also one has to flip it vertically, because usually experimentalists use just the opposite convention for the energy axis. So the energy axis is reversed typically in ARPES community with respect to what the theoreticians usually use. So when one flips this, one sees that there's this kind of feature and this one dispersive that corresponds to these two correspond to these two dispersive features here, which are actually visible, very nicely visible in the experiment. Anyway, so this is theory and experiment, but how to understand this theoretical spectral function? The point is that this is actually not a spin polaron. It's also a complex spectral function. It's not that of a non-interacting case, because otherwise we would just have nice quasi-particles here. But it's not a spin polaron. So what is it? So actually, some of you know it pretty well. So this is actually, to understand it, one has to invoke the so-called spin charge separation concept. So what happens here in one-dimensional antiferromagnet is that when we kick one of these spins, we introduce a hole with spin and charge. Then in this 1D antiferromagnets, what has been postulated many years ago for the Hubbard model, there's in the 1D Hubbard-like models, there's a separation of spin and charge degrees of freedom, and the elementary quasi-particles are spinons and holons carrying just spin and charge. So, and that's the language that is typically used to describe the spectrum. And indeed, for instance, this large dispersion here is actually due to a kind of liberated holon, yeah? Whereas this one here is the spinon dispersion. So these are really different creatures with respect to the two-dimensional case. Okay. So how to understand it? Yeah, what's the typical understanding? The typical understanding here of this problem is that why the 1D cuprate is so different with respect to 2D is to use just to say, okay, we have to use two different languages, yeah, two different bases. Because this is like a basic paradigm of quantum magnetism, that in one-dimensional magnets we have spinons, and in two-dimensional magnets, ordered magnets, we typically have magnons as elementary excitations. And then if we use these two different languages, then in 1D, in order to understand what's going on, we can look at this cartoon where we put a hole in the antiferromagnet. Then when this hole moves around, it hops one, then another time, and another time, it excites so-called domain walls, which are actually, to a large extent, can be viewed as spinons. So these domain walls are here. This is a single domain wall. It's where the two spins are parallel next to each other. And you see that when the hole moves, there's just one domain wall excited. Yeah? And then in this cartoon picture, at least, there are no more spinons, no more domain walls. So this is actually the essence of the spin charge separation. So the hole with spin and charge degree of freedom separates into a spinon, this guy, and a holon, which is this guy, and each carries just spin and charge degree of freedom. And this holon can freely move then after splitting and separating from the spin. Whereas, so that's the 1D case. The 2D case is the spin polaron, which I just explained, which is like a different cartoon where the hole moves, it excites these magnons. Magnons are actually different creatures. These are not domain walls, but just over 10 spins with respect to the long range ordered ground state. And each step that the hole moves, a magnon is created. Of course, then they can be annihilated, but anyway, the hole moves by coupling to these magnons, and hole is subject to the string potential. So this is the understanding. Now, my question is, can we have a unified picture of the 1D and 2D case? Can we do something better than this? So what we aim at is to use actually the magnon language, so the two-dimensional language, to describe the 1D. So we want to use the same language to describe both cases. And we choose actually not to do spin-ons in 2D, but rather to do magnons in 1D, because, for different reasons that we can discuss later. Anyway, so let me now start with the model and method that I will go quite quickly and jump to results. This is like more for the theoreticians who are in the audience and who are familiar. Focus now for like 3 slides. So I hope you can hear me. Okay, because I got a message, it's unstable, the connection. Anyway, so just let me know if I should repeat something.
You're okay, you're okay.
Okay, thanks. So that's the Hamiltonian that I consider as the TJ, the one-dimensional TJ, and consider the spectral function, the single particle spectral function, which is defined in the usual way, and the ground state is the Heisenberg antiferromagnet. Okay. By the way, do I have like 5 more minutes, or how much time do I have? Can I ask?
Yeah, you have about 6-7 more minutes.
7 more minutes, perfect. Yeah. Okay, that's good. Okay, I was worried it was a bit less. Okay, so that's good. So anyway, so that's what we consider the TJ model and the spectral function for this TJ model, where the ground state here is the Andor ground state of the one-dimensional antiferromagnet. It's a very well defined and well-known problem. And what is new here, this is for theoreticians, it's the only slide with several equations. What is new in our approach is that we use now in this one-dimensional setting, we do the slave fermion and Dyson-Malayev transformation. So we introduce first the slave fermions, and then for spins we introduce bosons. Yeah. So in the end of the day, we end up, instead of having C's and S operators, we end up with holons and magnons. So we introduce the holon-magnon basis. And crucially, what we do here, we do an exact expression. So we don't do linear spin wave theory now, but we express exactly the full TJ Hamiltonian. So the T part is the usual polaronic part, it's the holon-magnon polaronic coupling shown here, but the J part and the J part is shown here. And typically, if you do linear spin wave theory, you just stay with these quadratic terms in magnons, in terms of magnons. These are the terms that I am just showing now. But here we have an exact expression of the TJ model, and we need to have also the magnon-magnon interaction, actually the attraction between magnets. And there are also the projection operators which take care, sometimes one can have square roots if you do Holstein-Primakov, we do this Dyson-Malayev, so we have the projection operators which just take care that we then go to the unrealistic Hilbert space. Yeah, we stay in the physical Hilbert space, but you should not care too much about peace, like for now. Anyway, so that's the Hamiltonian that we have. And then we diagonalize it, it's an interactive problem for 2 reasons. There's this polaronic coupling and the magnon-magnon interaction. So we diagonalize it exactly. So it's like exact diagonalization, but now in a different basis. And that's the essence of the story, that use the usual basis for the TJ model, for reasons that will become clear in a second, or maybe they are already clear. Okay, so we go now, okay, before I show you the result, first let me remind you that I just talked about, that if you do spectral function of the 1D TJ model, that's the spectral function one should get. There are no quasi-particles, everything is incoherent spec, but with some distinct features. coming from the spin charge separation, and the understanding is this one. Yeah, so we have this hole separated into spin-on and holon. Okay, so that's in the holon spin-on basis. That's what I showed like a few minutes ago. Now we go to our results in the holon magnon basis. So first of all, everything is fine. So we get exactly the same spectral function as before. You see this one and this one. There's no difference, of course. Yeah, everything works in just a different basis. But now the cartoon is different. It has changed because now we use a different language to describe the problem. And what we have here is actually that when the hole moves, it excites magnons now. It excites, at each step it moves, it excites a magnon. It's not just one domain wall. It's like at each step, one magnon, okay? But the energy cost is like that the first magnon costs energy, but which is actually J/2. But the next magnon, so here, for instance, we create the second magnon, here the third one, and so on. They do not cost any energy. And this is because in this cartoon picture, if we create these magnons next to each other, and there's an attraction between nearest neighbor magnons in the Hamiltonian, then because of that, and this magnon-magnon attraction exactly cancels the cost of exciting a magnon. This is a specific, basically, property of a one-dimensional TJ model, one-dimensional Heisenberg, actually. Even. So if you put magnons in one-dimensional Heisenberg, then the cost of creating more than one magnon is basically free. Yeah, it goes for free because of the magnon-magnon attraction. But you have to have this term. So this is one of the main results here, that the holon, which says that the holon magnon basis is okay, and that that what is crucial here is this particular value of magnon-magnon interaction, yeah, because only then we can have free magnons, yeah, we can instead only except for the first one, and then everything is fine. So now, in order to learn something from out of it, what we want to do is in the final step, and then I finish, is that we want to tune these magnon-magnon interactions to see what's the effect here, because it looks like they are crucial for the physics here. So what we do, and here is in the next slide, is that we neglect the magnon-magnon interactions completely. We kick them out from the model. So it's not a genuine TJ model, but without the magnon-magnon interactions. So with the spectrum that we get is this one. And when you get this quasi-particle, you see peak here, or I have some backup slides which show it's really a separate delta function here, separate from the continuum. So that's the main point. And moreover, the cartoon understanding is such that we have the spin polaron physics now, yeah, because we have no magnon-magnon interaction. So then each magnon costs, energy always, yeah. So we are in the string potential limit in this spin polaron picture. So basically, in other words, in the 1D, if we take the 1D TJ model without magnon-magnon attraction, then we recover the spin polaron physics, which is known from the two-dimensional case. It's exactly like for the two-dimensional cuprates now, if we neglect these magnon-magnon interactions. So that's the point. So now let us compare these two results, with and without, to just understand a little bit better this full one-dimensional TJ model. So what you see when you compare the two spectra, this is with magnon-magnon interaction, this is without, you see first of all that there's a difference from the ground state. Yeah, this quasi-particle is here, but not here. So there's a big difference. On the other hand, the excited part of the spectrum is surprisingly similar. So this is a completely surprising result here, that this part here and this one is is surprisingly the same. So what it tells us, and this is the main result, and at the next slide is the conclusion, which repeats basically this result, is that first of all, the ground state with a single hole in the antiferromagnet in the one dimension is different on the left and on the right-hand side. And this means that the spin polaron for the particle, which you see on the right-hand side, is killed here on the left-hand side due to this particular value of the magnon-magnon interaction. So these magnon-magnon interactions kill the spin polaron for the particle in 1D, yeah? Because they have a very specific value. So that's the point. We then have the spin polaron for the particle in 1D because it is killed by the magnon-magnon interactions. On the other hand, and this is like a positive message, is that the excited spectrum is similar. And because here on the right-hand side, we have the spin polaron physics, this means that here as well. So there's some spin polaron, you know, it's not like that the spin polaron coupling disappears in 1D, it is there, and it is visible in these excited states, which do not feel so much the magno-magno interactions, okay? So this is my basically last slide, or penultimate slide, where basically what I just repeat what I showed before, that the differences between 1D and 2D outpairs is due to the fact that there is this particular value of a magno-magno interaction which kills the spin polaron for the particle in 1D. So that's the origin of the differences. On the other hand, you know, it's not like that the spin polaron physics known from 2D is completely irrelevant for 1D cuprates, because it's actually a valid description of the excited states of outpairs. So a large part of the spectrum can be described using the spin polaron language, everything is fine. And moreover, that's something that I then show you, is actually that if we are in the quasi 1D setting, and actually in reality it is the case of the cuprates, then this effectively, this particular value of magno-magnetic interaction is never realized, and we are always safe to use this spin polaron picture. So in other words, it's not that spin charge separation is invalid, but strictly speaking, the spin polaron picture is still okay. Okay, so that's basically all. I have some outlook, which if you have any questions, I will tell you how it is relevant for the cuprates. But I just show you the last slide where I thank the 2 PhD students and the postdocs, so Clio Agrapidis, Adam Plucinski, and Piotr Brzezicki, who did most of that work together with Mona and Yao, and the work is on the archive. Thanks a lot for your attention.
Thank you very much, Krzysztof. We have time maybe for one quick question. If you have a question, please unmute yourself. All right, if there are no questions, I'm going to thank the speaker once again. And thank you very much, Krzysztof. If you don't mind, if you could unshare your screen and mute. Our next speaker is Wojciech Brzezicki. So Wojciech, are you there? Could you try and share your screen and unmute yourself?
Yes, I'm here. Can you hear me?
Yes, we can hear you. Mm-hmm. Yes, please go ahead and try to share your screen and see what happens.
Okay. Can you see the slide?
Yes, we can. If you want to go to a full screen mode, if it's possible, that would be great. Oh, yeah, perfect. All right. Thank you very much. Okay, please go ahead and start.
Okay, thanks. Okay, so first of all, thanks the organizer for this invitation. Second, okay, I just want to say I will not talk about cuprates. Or even not about particularly strongly correlated systems. And actually, third thing is I would try to make it short because I have some problems with my throat. So I will try not to be too talkative. So this would be about Berry phase effects in topological metals. So first systems we are interested in, which was really studied in Warsaw, where I worked part-time, right, in this research center Maggio. There's this topological crystalline insulator, tintelluride. And basically, this is
Wojciech, sorry to interrupt you. If you could turn off your video. Your bandwidth is a little bit too low, so maybe turning off the video will help.
Is it better or still bad?
Yeah, I can still see your video. Okay. Yeah, try now. Let's see what happens.
Yeah, well, it seems that everything I do is with delay. So I don't know. Well, I can try to switch to the to internet from the cell phone.
No. The last few 30 seconds were okay. Maybe try to continue like this.
Okay. So basically, classically, if you think about transport, you have the conductivity, and it gives you basically the Ohm's law. It tells you that, well, when an electron goes, it undergoes some random scattering on the lattice and uses energy, and this is not accelerated linearly with electric field, but dissipates some energy. And basically, but this is when you think of electrons as not quantum entities, just like classical objects. But if you think about quantum things, and electrons are waves of matter, and waves can basically interfere. And the effect of this interference is what we call localization or anti-localization. So small corrections are positive or negative to the conductivity. And it was kind of established some time ago, but it has something to do with the Bary's phase, that actually it can detect the Bary's phase of an electron sitting on a Fermi, let's say, circle, right? If you think of 2D system. And basically, when the electron sitting on this Fermi circle, it has zero Bary's phase, you typically get localization, which means you have negative correction to conductivity. So your system conducts walls because of quantum effects. And when you have pi, it actually conducts slightly better, right? And this is typically associated with the time reversal symmetry class, whether you are in the class where you have time, when you have spinless time reversal symmetry, so the system can be regarded as spinless, meaning that essentially spin-orbit coupling is weak, or pi when you have spin 1/2 system ready. So in practice, it means that your spin-orbit coupling is large, so it means that the spin sectors cannot be decoupled, so you cannot treat the system as spinless. And this classical version, this trivial version of this phenomenon, when you don't have the Bary's phase, it has many other analogies, right? It is present in different areas of physics. And basically this weak localization, you can call it also enhanced backscattering phenomenon. And it always happens when you have some disordered medium and you have some waves. Basically, for instance, waves of light, yes, in this old paper here, popular paper, you have profiles of intensity of light, where you have some here electric, and you shine light through it, and you see what is the intensity reflected, and you see that actually, if you calculate it correctly, you get this blue curve, and it has the peak at 0 angle. So what is reflected at the same angle as it came, right? So this is backscattering, and it's indeed increased because in this gray curve you don't get this peak, and gray curve is obtained when you forget about the interference, right? And you can use this phenomena, for instance, to estimate how clean is the air, right? If you have dirty air, then you will get a lot of backscattering. And this phenomenon was also observed during the World War II in this military radar stations. And it was also observed in many other systems. Okay, maybe I will not talk about everything, but it's quite universal behavior, right? But now we have something which carries the spin, right? So it has some internal degree of freedom, not like waves of water or something. And the spin makes a little bit complication, right? Because when the electron goes, when it scatters, you can think of it when the disorder is not very strong, you can think of it that it actually will interfere with itself along the Fermi circle. And now, so now when you make this kind of parallel transport electron along the Fermi circle, it actually matters that it has spin, right? Because the waves which will interfere have more structure, not only space structure, but also spinor structure. And this will affect things. Right? So that's why you can get this anti-localization. And it's typically related to this type of time universal symmetry. But here we show actually both experimentally kind of and theoretically, but it can be also related to the space symmetry, to the here mirror symmetry. So basically the experiment is done in Warsaw is such that you have your bulk crystal. It doesn't even matter that this crystal is topological crystalline insulator because this topology here is not important. And then you either have it clean, which are these featureless straight lines, or you have it actually with some mess, with some garbage on it, amorphous selenium, and then it's these curves which are saturated. And now the question is why this covered and uncovered sample behave differently. So here it's not so important what is on this axis, it's just that they behave differently. And we claim that this is related with breaking of space symmetry because our system, these are the layers, actually, this is the one-on-one surface of this thing. So we claim that this covering actually breaks this crystalline symmetries, right? And the story goes like this, that we basically simulated the system by implementing like some number of layers of the system, which has this log-salt structure, right? So binary, basically. You can forget about this doubling, it's not so important. And then the surface Brillouin zone is this thing, right? This hexagonal stuff. Now you have some Fermi, you have, your system is not in the charge neutrality point, so you have some patches of these Fermi surfaces, right? Because you cut your Dirac cones, and you see these Fermi circles, right? And now along the circles, along these circles, you can calculate the Bethe phase, basically. And we claim that now, actually, this Bethe phase, it can be quantized to pi by this spinful time universal symmetry, or can be either quantized to 0 pi by this mirror symmetry. And this is okay, some little calculation, maybe I will not go too much into details, but here there's also this kind of subtle point that actually in your system, the system is like, it's not really three-dimensional, right? It's like, it's finite in one direction. So it means that your bands, three-dimensional bands now are split into pairs of subbands. And this is because now your system is not full inversion symmetry. Because this, you see that this bottom layer of atoms is different than the upper layer of atoms. And you get this tiny splitting and this like large splitting, right? And now this is Fermi level, you get your Fermi circles, right? And now you have this tiny Dirac point here, and actually this quantization of this Bethe phase along the circles, it tells you that either this Dirac point is inside these circles or not, or maybe it's completely gapped and there's no quantization. And we studied numerically also different cases of breaking of time reversal symmetry and of mirror symmetry. And we are looking at how these Bethe phases are changing, right? These are the Bethe phases in the unions pi. And actually, we could say that this change of the Bethe phase, the deviation of the Bethe phase from the quantized value, actually can be related to the change, to the correction, to the conductivity. And by this idea, we kind of managed to some extent explain this experimental data here. And you have covered and uncovered sample as a function of in-plane magnetic field. This is the correction to the conductivity. and this is our theoretical result. Right? So you see that depending on whether you have broken or not broken middle symmetry in the system, this deviation from the quantitative value to better phase is different, and this coincides with different behavior of this conductivity. Okay, this is kind of simple theory, a little bit hand waving, but still okay. But it works only when you have in-plane field, right, in the system, because when you have out-of-plane field, well, something more complicated happens, right? Because electrons will try to form odd Landau levels, right? So we would like to form this orbital, these orbits, right? And this is more complicated, right? And this will affect, of course, all these better phases, all these phases gained by the wave function, right? And to see, to understand what can happen in the out-of-plane field under the breaking of this middle symmetry, we have to employ this old concept of this what is called Coulomb correlator. And this is basically hard to do for the full model. So we take just one type of subbands, this two kind of interpenetrating paraboloids, or we can call it, just this alpha spectrum, single one. We put the Fermi level somewhere here, and we consider low energy Hamiltonian, right, up to the squared order in K, in quasi-momentum. So obviously it has these two parabolas, so you have this thing, K square. It has there are two bands, so there should be some spinor structure, so you have your sigmas, and it should have Rashba, right? So this structure is shaped in this Rashba interaction. And this G here is something which we control, which allow us to gap out this tiny Dirac point and to basically see what is the effect of breaking of the middle symmetry. And because this is what, on the level of this model, breaks our middle symmetry. And then we have to look, well, rigorously to do it, but lots of papers from the 80s, and this is a kind of classical paper of Kamil Lapkin and Nagaosa. And they derive actually the exact formula of this magnetoconductance, quantum magnetoconductance for different cases, depending whether spin orbit coupling is weak, small, whether the disorder is weak or small. So we want to do the same, but with this G, right? They were doing without this G, so this is the difference. And basically, technically, this is a little bit complicated, so one has to consider one should do it perturbatively, right? So you can imagine you should have some impurities, you have some this potential disorder on site, right? In the simplest way, the disorder is uncorrelated, this disorder is weak, and then you think about disordered average green functions, and basically you do it by solving the Dyson equation, by summing up all the ladder diagrams with this kind of trivial interaction vertex, which is just basically the strength of this local potential which you add, right, as a disorder. And basically, this gives you this what is called Coulomb propagator. This is the kind of correlation function of pair of electrons, right? And these pair of electrons are exactly these two waves of matter which would like to interfere. And as I said, it's a little bit complicated, but maybe let me go just this formula here. But basically, all comes down, all this calculating this correction, it comes down to taking the trace and summing over all total quasi-momenta cubed. So these are the sum of quasi-momenta of these two electrons. So something here we assume always we think that this Q is something small because typically these electrons which are counter propagating will interfere. And so this is the backscattering, right? And then here you put the inverse of something which is called Cooper Hamiltonian. Actually, this Cooper Hamiltonian is non-Hermitian if you assume that we have this G breaking of the middle symmetry. And why is non-Hermitian? Well, of course, from this derivation, it's not even obvious that you will get any kind of Hamiltonian, right? Because you're summing up some diagrams, but just turn out that you can assign some operators here, and you get this form of an operator which you have to actually invert here, and some under this breaking of the mirror symmetry actually gives you this imaginary part here, which makes all things actually non-Hermitian. So here this Q is the total quasi-momentum of 2 electrons. This QSO is quasi-momentum, something of the dimension of quasi-momentum related with the which keeps this value of the spin orbit coupling alpha. And here this S is the total spin of the 2 interfering electrons. So either 0 or 1, right? You have one singlet state, 3 triplet states. And here this term breaks everything because it contains difference of sigma z's of 2 individual spins, right? And here you have this matrix gamma, something which tells you whether, if you think of eigenvalues of this thing, it tells you whether it lies in this singlet or triplet sector, right? Depending on this, the sign is different, right? And basically, if you have interference of these 2 electrons in a singlet sector, this thing becomes negative, right? And if it happens in the triplet, it's positive, and this makes gives you a difference between anti-localization and localization. And you now just need to diagonalize this Hamiltonian, and this diagonalization here looks rather simple because on the operators it just spins 1 or 2 spins 1/2, so 4x4 matrix. But now we want to do it under the Landau, right? Quantization, having the Landau levels. So how do you get Landau levels? Well, you have to add this out of plane fields, for instance, in the Landau gauge. So this comes down to minimal substitution of this Q. So sum of quasi-momentum of 2 electrons, basically. That's why you have 2E here. And standard way now to go on is to introduce this ladder operator bosons, which either destroy or create Landau level, or read out the number of the Landau level. Right? And actually, this is an interesting point in all this derivation because everything is done in a very approximate way, but actually the sum over the Landau levels, which now comes instead of sum over the quasi-momenta, one has to do exactly. But to do it first, one has to, for each Q, actually one has to, in each kind of sector, one has to diagonalize this kind of Cooper Hamiltonian, and this is a Hamiltonian of a single spin, right? The 1 coupled to a single bosonic mode. And this thing which contains the difference of 2 spins, actually it has nice enough structure not to spoil everything, mildly speaking. And basically, it's also not obvious that this Hamiltonian can be diagonalized because the space of bosons is infinite. But actually, you can do it if you notice that here this Hamiltonian conserves SZ plus the Landau level. So it's like total magnetization, right? Spin part and orbital part of the magnetic moment of the electron, right, in the Z direction. This is a conserved quantity, and this allows to split these things into 4x4 pieces like this, and then, well, in each piece you can either diagonalize or just invert, and you can calculate your correction, right? Calculate this. So now you have sum over the Landau levels, when the maximum number of random levels decided by the strength of the field, 1 over the strength of the field, right? So the weaker the field, the larger, the more random levels you have to sum up. And this kind of known, but basically simulating small magnetic fields is always more difficult because you get huge magnetic unit cell. So here this is the same. Here, of course, you introduce some reduced quantities like the small b, which contains both a magnetic field and the spin orbit coupling. And then, then you get this, this formula, and you actually, the sum is very strange, but the sum can be done exactly. And it gives you what is called the gamma functions, the different derivatives of the standard gamma function. And for instance, if you here put this this breaking of the mirror symmetry, which is this eta to 0, you recover what is called this Hikami-Larkin-Nagaoka formula. And this one, so this is like correction to the conductivity written with just one reduced parameter, which is this. Just one function of a single parameter which contains everything. So magnetic field contains this kind of quantum diffusion constants and contains also tau phi, which is kind of infrared cutoff. So this is dephasing time. This is some slow, long time. It basically tells you that after this time, your system, your electron is no longer in the pure state, so it will no longer basically interfere. So this is how it works. Basically, in our formula, I want to go beyond this Nagaoka. And it turns out that it can be well represented by just enriching this formula with this effective dephasing time now, which you can also upgrade to be time dependent. So now the dephasing, so basically temperature will just make this dephasing faster, right? Because it will create mixed states, and then you here you get some characteristic new length scale, which is the length scale related with the breaking of the mirrors. And after doing all these things, you have to of course put in the numbers and compare with what guys the experiment got it. So this is what guys from the experiment got it. So this is the conductivity, magnetoconductance is the field for the uncovered and covered samples, and you see that actually our plots here, vertical plots, give you exactly the same. And for sure, you recover this trend here. This is in this outer plane field. But actually, if you have covered sample, this decay of this curve is slower. We also find it. You can now recover this first plot I was showing in this first slide with this hexagon, with these hexagons. That if you look at this effective dephasing length, if you have obeyed mirror symmetry, it is featureless, and when it's broken, actually it saturates, and it saturates actually to what it saturates is related with this effective length scale related with breaking of the mirror symmetry. So we are kind of nicely done, right? We managed to kind of generalize old formula, and actually it's also nice that this G you have to put inside this breaking of the mirror symmetry really tiny. It's order of milli-electron volts, and it's well below the resolution of ARPAs which we have. So, but the splitting actually can be here, but you just cannot see it. But you can measure it with this localization phenomenon, which is extremely kind of sensitive, right, to such things. Okay, so that's it about this kind of semiconductors stuff, which probably nobody is interested here. And now I tell you, if I still have time, okay, I got lost.
I'm sorry, you're completely out of time.
Completely, okay. Oh, very good. So let's say I finished, right? Okay. Yeah, you could have told me. Yeah, okay. So yeah, so this is kind of summary, right? So thank you for your attention.
Thank you very much, Wojciech, for this very interesting talk. Maybe one question? All right. So we started the session a little bit late because we were still waiting for people to get to the hotel. So our next session will start in about 8 or 9 minutes. Krzysztof, I think you are the chair. So I'd like to thank all the speakers in this section. Thank you very much. And I'll see you in 8 to 9 minutes. Bye-bye.
Okay, perfect. Okay, good. So let's start. So we've got 20, well, altogether it's 25 minutes. So after like, maybe in like 15 minutes, I send you a message that, you know, it's 50, okay? Minutes past, so you should finish then in 5 to 7 minutes, let's say, okay? So the next speaker is, or the first speaker of the session actually, is Omar de la Pena-Seaman, who is from now in Mexico, yeah? And the title you all see here. So please, the floor is yours.
Thank you. Thank you so much for the introduction and also for the invitation, the opportunity to talk about a little bit about our current research project, superconducting metal hydrides, analyzing the effects of doping together with reduced applied pressure. So this is a work I've been performed with in close collaboration with Dr. Sergio Villa Cortez. He was my postdoc the last year, and now he's starting a new postdoc position in US. So as a brief introduction, probably you already saw the nice talk about Emirates in Tuesday, very early in the morning. So, well, the main idea of superconductivity in hydrogen, on metallic hydrogen or system with hydrogen actually, was that since the TC is related, as you could see here, with the divide temperature, and that is basically related with the frequencies. So, and the relation between frequencies and the mass is in the inversion proportion. So the basic idea was, if you want to have a high TC, a high phonon spectrum, and then a high TC, then you have lower masses, okay? And the element with the lower masses in the periodic table is hydrogen. So the basic idea was that. And I could apply to the BCS theory the idea to have a metallic hydrogen, and he found, using this equation, a TC around 55 Kelvin for a hypothetical metallic hydrogen. The only tricky part in that idea was that hydrogen is not a metal, it's a gas, it's not solid, so they have to apply a relatively high pressure in order to metallize. Well, that was in the 68, and was the idea was very, very promising. So I could actually retake that idea. That the only handicap that the idea had was the high pressure value. So he reformulated the question or the idea in 2004, almost 40 years after that, and say that, well, it's true, hydrogen is not so easy to metallize, but if you put hydrogen in a kind of metallic alloy, where the internal pressure of the crystal could exert some of this high pressure that you need, then you could have reach the metallic state at lower pressures, and then reach the superconductive state also in a relatively easy way. So this idea has been in the community of superconductivity long time ago. There were a lot of efforts for the computational point of view. And one of the more important ones was the paper from Lee in 2014, when they analyzed the different crystal structures in order to see for this compound, H2S, sulfur and hydrogen, if they could reach a kind of crystal structure that was stable enough to have a metallic system and also possible superconductivity. So the two most promising crystal structures was that P1 and CMCA. These are the crystal structures, quite complicated one. And they saw that a high pressure was quite stable, the system. They analyzed all the structural, superconductive properties, TC, density of states at the Fermi level, the logarithmic average of the frequencies and the electron phonon coupling. And they learned that in the transition pressure between the P1 and CMCA crystal structures, they could reach a highest value of TC around between 80 and 70 Kelvin. All these is calculations at a pressure around 160 gigapascals. And the interesting part here is that, first of all, you have the highest critical temperature close to the crystal instability or structural instability. And in that case, the frequencies goes not so low in value, but you had a maximum in the lambda, in the electron phonon coupling parameter. So you are closing to phonon instabilities. The density of states at the Fermi level is higher, it has a high value, and lambda also has the maximum value. So the ingredients that you're starting to expect here is a high value of density of states, a lower value of frequencies, and a high value of lambda. So the experimental confirmation of this computational report came soon after by Drozdov and co-workers, and actually they found that was H3S, not H2S, what was the superconducting system in that structure. They found actually a very nice and simple structure to this system. They found a superconducting temperature around 203 Kelvin for a pressure around about 140 gigapascal. So the pressure was lower and the TC was higher, and the crystal structure was extremely simple in comparison with the other two. So the reconfirmation of this observation came also from theory, from the group of Duan in 2014. And they actually started with higher systems, but this structure or this crystal is basically HS3 with different decorations and so on and so forth. And they found actually with an enthalpy analysis that in fact this structure for these elements was the most stable one in the regime of the pressure analyzed from the experimental point of view by Drozdov. These are the most stable one, and obviously for higher values of pressure, the cubic one that was found in the experimental observation of Drozdov was actually this one, the 1M 3M. So what are the more important characteristics, at least for H3S system, superconductor system? Well, from the electronic point of view, the most important features was that you need, in order to present this superconducting state, you need to have a high density of state at the Fermi level. You could see here the band structure and the density of states for this material in this structure, right? In the cubic one. Another interesting feature that was discussed a lot at the beginning of the discovery of this material superconductor was the appearance of Van Hoff singularities close to the Fermi level. This was a very, very important feature for this kind of properties. And finally, the occurrence of strong covalent bonds between hydrogen and the metal, in this case, sulfur. So this was, at least at the beginning, the more important characteristics to look in possible sibling systems related to H3S. From the vibrational point of view, here I present the phonons from Duan, the phonon dispersion, also the phonon density states, and the Elliott function, together with the electron phonon coupling paradigm. So the most important part here was the appearance of high frequency phonon modes. Basically, now we know that this region is the most important one, the intermediate region, the low optical frequency modes. But these modes has to be related with the hydrogen movement of the atom, the hydrogen atom movement. So in this calculation, Duan found electron phonon coupling parameter quite high, 2.19, just to give a frame, an idea. One parameter of lambda equal to 1 is strong, is high. So anything higher than 1 is quite strong. So with this value and the modified Elias Allen-Dines equation for TC, they get a value of roughly 200 Kelvin, so very close to the experimental result. So with what is the highest system that with the highest TC that we could have right now in literature is the lanthanum H10. First of all, was explored by theory. This is a structure, a caltrite structure, and they get values as high as in TC as high as 280 Kelvin for pressures around 200 gigapascals. And the experimental confirmation came a couple of years after that. They got, this is the normalizing resistance, a function of temperature, and they got a roughly 260 Kelvin around 190 gigapascals. It's not strictly speaking a very good comparison, but it's good enough to have an idea that the theory drives and helps the discovery of superconducting systems in the laboratory. So what's the catchy part in this, or the tricky part in this area of superconducting metal hydrides? First of all, you have to put a lot of pressure in the system to, first of all, in some cases, metallize it and then transit to the superconducting state. And secondly, well, these pressures are not so high for actual equipment. However, the way to make the measurements and also low temperature measurements in this setup is quite complicated. This is very challenging from the experimental point of view. And that's why so far there are two systems that have been confirmed experimentally: the lanthanum H10 and also the H3S. So in order to help to get the superconductors, high TC superconductors made with hydride to lower pressure and maybe tune these properties that we already saw, the vibration and the electronic, that's the we present the basic idea of include an additional variable or dimension in this phase diagram, not only TC and pressure, but also doping. So that was the idea of our FIRS approach with a very, very simple system, scandium H2 or yttrium H2, and both of them doping with holes and electrons in a very simple crystal structure, as you could see. And this is the final result. We found that, first of all, without pressure, this is a system without applied pressure. So this is the values of TC as a function of doping with holes or electrons into two different systems, scandium and yttrium. And we found that if the scandium H2 you dope with holes, that means you substitute the scandium by calcium, then you have a slightly increase in TC and then a free fall. And in the case of electrons, you're starting with a free fall, and then for some reason, it's starting to increase the TC very rapidly. Okay, you will see that the scale of DC, there is no mistake here. It's quite low values in comparison with the two previous examples that I presented. However, this is just a kind of proof of concept. Try to see if for a simple system this works. Maybe we could extrapolate to complex systems. So I want to show the different effects in the ingredients of the doping in order to understand why we have this strange or funny behavior of the TC. So first of all, for the electronic properties and the vibrational ones, here the TC is just for the scandium system. For the yttrium is basically the same. So the TC, this have this behavior. The electron phonic coupling parameter as a function of the doping content is also presents a relatively similar behavior in the hole and electron doping, and it hits the density of states. Okay, so it seems that for the electron doping regime, the density of states is the more important part. However, and you could see here the line in this is the density of states for the three different cases: the doping with holes, pristine, and electron doping. So you see that the density of states at the Fermi level is quite stable in or a standard value for these kind of systems for the pristine case. However, when you dope with holes, you decrease this value very, very strong. Okay, so you are not giving enough importance to the electron part. However, in the electron doping, the most interesting part or the most the part with a heavier contribution to the superconducting properties, it seems that is the electronic part. As you could see here, this upward of the values has a strong effect in the TC in this region. And in the phonon, this is the phonon density of states as a function of frequency. You will see that this region is the most important one for the whole doped system, and this region is moving to higher values for the electron doping region. So in order to understand the effect of each of these regions, is the Elias-Verth function as a function of frequencies, and is the TC for whole and electron doping for the scandium system. We take it out different parts of the spectra in order to see how strong is affecting the TC. If we take it out, the acoustic one for the scandium, well, is going to be the green one. So it seems that the acoustic part is the more important part for the pristine system, and also for the major part of the whole doping. So the acoustic is the good one, and you could understand it. Well, yes, it's the acoustic one, and there is an important contribution to the optic one. Okay. However, for the electron one, the optic one is no longer affecting anything, almost anything in the TC, since as you can see, when you take it out the optic, basically they are the same results as the full value of the TC. Okay, this is the main part here, and the acoustic is not sorry, and the acoustic is getting basically all the weight of the critical temperature calculation in this particular part. So what is the meaning? That depending of the region that you are doping, Hall or electron systems, you will get a different behavior of the TC, and you could tune these properties very easily, quotation marks, with doping. So what about if we now dope and trading doping and also pressure at the same time? So we did that with this system, also scandium and yttrium, but H3s. So more hydrogens in the crystal structure. The crystal structure is still very simple to study, this cubic structure. And also I present first of the lab results. The TC, these are the diagrams of TC as a function of pressure and also doping content. And also here in the lower panel are the lambda values, the electron phonon Copley parameter values for each systems. This is for scandium, H3, and this is for scandium, sorry, H3, and this is for yttrium, H3. As you could see, the TC is changing as a function of pressure and also as a function of doping. And you could reach an optimal region of TC for values of not so high doping of calcium, and in this case of strontium, but also you could lower the value of the critical pressure, where you could get the highest value TC. In the case of pristine scandium, you will get around 20-something, 25, 24 gigapascals. But if you optimize all the properties of the system by pressure and by doping, you could lower the pressure to around 11 gigapascals. So how is happening this? Well, this is the density of the states at the Fermi level. Sorry, so only the density of states and the phonon density of states. This is the pristine system. This is the whole doping, and this is the electron doping. And this is just for scandium H3. More or less the same is for yttrium H3. So we see here that it's no longer so important the electron part, because you are not close to any kind of Van Hoff singularity. The values of the density of state at Fermi level are quite small. And in fact, when you apply pressure, the blue lines is the lowest pressure where the system is stable, and the red one is a high pressure value that we arbitrarily choose to 100 gigapascal. When you increase the pressure, the electron properties are getting lower. So you are depressing, in some sense, this contribution to the electron phonon coupling property. And the phonon density of states, the effect that you are getting is again the red one is the low pressure, the blue one is the low pressure regime. Then when you increase the pressure, you push the phonons to higher values, to higher frequencies, and this is is affecting negatively the electron phonon coupling parameter. And in fact, when you include holes, you push to lower values the frequencies, but increasing the pressure, you have the opposite effect. You increase the values of frequency. So it's a kind of competition between doping and pressure in this for the whole doping. And for the electron doping, in the both direction is affecting negatively the coupling parameter, because you are increasing the frequencies by doping and also by pressure. So here is not going to be a very good case to have high values of TC, as you will see later. These are the Eliezer functions for the three different cases, and the TC with this scheme take it out a specific region of the Eliezer function in the calculations. We have the Scandium H3, doping with holes, and doping with electron. And we have three regions: acoustic, low optic, and high optic. Again, the acoustic one, if we take it out, here the TC is with analysis taking out different parts. So for example, if we take it out, the black line is a standard calculation with all the phonon the Eliezer function in the scheme of the solving the mixed Eliezer equations, and we take it out. If we take it out, for example, the acoustic part or the optic part, the high optic part, that means this region or this region, the TC values are not so different from the complete calculation. Okay. However, if you take it out the middle, the low optic region, this is the middle peak, then you depress the TC more than 50%. So that means that for this specific system, the H3 with a metal, the more important part is the low optic region, not the acoustic ones that you could think that is the lower part, low frequency, then is the medium part. And this is very important result, because then you are learning to tune the superconducting properties by not just by pressure, but also by doping. And the doping is helping you to reduce the pressure, the applied pressure, in order to get the superconducting properties, the superconducting critical temperature for this kind of system. So the idea is to translate this approach to more complex systems, to more realistic ones, so to speak, in the sense of the value of the TC could be higher and higher as you are increasing more and more the concentration of hydrogens in the crystal structure. So thank you so much.
Thank you very much for a very nice talk. Are there any questions? We've got like even a few minutes. Everything was clear. To me, the talk was very clear. So,
I think there is one from Emanuel Cappelluti.
Okay, please start.
Yeah, thank you. Now, when you were discussing, I remember there was some very old prediction, which maybe by Alan, I don't know, which is well discussed and reviewed by Carbot. Then the very sensitive TC is very sensitive for little change of phonon spectrum close to the frequency corresponding to the TC itself. So it's more or less corresponding with your analysis. So maybe there is already in literature some explanation for this, which can confirm your results, I mean.
Yes, sure. I am aware of that part, specifically at the very beginning of this situation, of these systems, metal hydride systems that shows a high value of TC. The idea was that the more important part was the acoustic one in the phonon spectrum, right? Because obviously lambda goes 1 over omega in the integration of the Eliezer function. So it's very easy to think and to extrapolate the idea that, okay, we have low frequency spectra, then this integral is going to explode. It's going to have a very huge values. However, in this case, the contribution is not so high from the acoustic part as the low optic part. And why is that happening in the metal H3 and not in the metal H2? Basically because the number of atoms in your unit cell, you have just two specific regions of phonons in the MH2. However, as you're increasing the number of hydrogens, so this optical region is starting to separate in different range. And for this case, specifically for this one, so the intermediate region is the more important one. And at the very, very beginning of the study of the superconductors, the thought was that probably high frequencies is going to be better because affects this value of the prefactor of all the expression in the equation of C. But we started to learn that dependent of the system, maybe it's not so it's not so easy to reach to this conclusion. Yeah.
Thank you.
Okay, thanks a lot. So I think we should move to the next talk. So thanks again for a very nice talk.
Thank you.
To Emanuele for a nice question. So let's try again with Mauro.
Okay.
Could you try? Okay, so maybe to Omar, the first request. Could you just stop sharing your screen? Yeah. And now let's try again.
Okay, let's see.
Oh,
I hope it's okay now.
Yes, now it's perfect. Can you go to the next slide so that we know it?
Okay.
Yes.
Okay.
Yeah, it all works. Okay. So basically we can start. I can just tell you that 10 minutes before before your time is over, I will send you a message and maybe I will show like that. And then 5 minutes before I will send you another message. Yeah. But 5 minutes is already includes discussion. Yeah. So then, you know, like, okay. So 5 minutes before the total end and 10 minutes before the total end. Okay. So altogether 25. Okay.
Thank you very much.
Yes. So please start. Okay. So the next speaker is, okay, maybe I should introduce. So it's Mauro Doria from Rio de Janeiro, from Brazil. And the title is The Spectrum of Bilayers under the Spin Momentum Locking Condition. Please, the floor is yours.
Okay, thank you very much, Christoph, for your patience here. I hope that you are hearing me well. I'd like to thank also Omar, previous lecturer, for exchanging his time with me. Okay, so what I'm going to talk about here is a totally new approach to layers, which is solely based on the Schrödinger kinetic energy. Okay, and from this, I will show you quickly that the direct linear spectrum can be obtained, so it is a non-relativistic effect. The Rashba term is contained in the Schrödinger kinetic energy. Okay, and then I'll show you that the spin and momentum, when they are locked to each other perpendicularly, they lead to topological quasi-particles. These points are more like a review of previous works, okay, that will set up the bilayers. So in this framework, the topological stability can be seen through a residual local magnetic field that surrounds the particles and transforms them into stable quasi-particles. And this local field, it's streamlines. They pierce the layer twice, okay, making difficult to break them up, okay, and bringing the stability of the states, okay. So everything is centered on what I call three-term decomposition of the kinetic energy. And so the result of all that is that if we put two layers together, the spectrum is no longer linear, direct-like, but it is given by a quadratic dispersion relation, at least for low energy regime. So I'd like to thank the Superstripes chairman, Antonio Bianconi, Augusto Marcelli, and my topic here is a radically new approach to two-dimensional topological states. Okay, just to set up a little bit of experimental work, previously the bilayer graphene, yes, the bilayer graphene was studied and found that apparently it's claimed to have very thin imperfections that transform its band from a linear direct spectrum to a composite spectrum with a massive particle and a massless. Okay, so it's interesting to look at these pictures of the energy spectrum and see what they write. We say we have also found spectroscopy signatures of twists. Bilayer graphene would rather induce a twist involving thousands of atoms rather than create an atomic scale defect. This twist induces a small splitting of the direct point. This splitting results in a unique low energy topology near the lowest energy D. The bands have small gaps at direct crossing, which are asymmetrically placed with respect to both Kx and Ky. So you see this picture that you have a little bit of a shift. This is a puzzle. I will make a point here that perhaps there's no twist. That's natural from the two-bilayer system, the perfect system. Okay, I'm not making a theory for graphene. I have general arguments for bilayers, so maybe they apply to graphene. So this is, through the years, I have developed this system in collaboration with a couple of people. Here are some publications, and I'll move on. So what's the spin momentum locking? Spin momentum locking is when spin and momentum are locked perpendicularly to each other. And this has been in the literature associated to Rashba systems and even found in cuprate superconductors. Okay, so there's no clear interpretation of that, but I will give you a precise one that will connect with the original proposal. Okay. Oops. Okay. So my definition of spin momentum locking condition is the following. First, I mean, central to this approach is just the three-dimensional kinetic energy. I emphasize three-dimensional because I'm looking at a layer. Okay, and the spin momentum locking condition. So here you see this is the kinetic energy, psi is the state, is the spinor. Okay, P is always our generalized momentum. And the spin momentum locking condition for me is this condition here, that spin and momentum are, when applied to the state, are equal to 0. Notice that this condition does not fix the direction of spin. Okay, once given the momentum, you have a whole plane of possible spin orientations. Okay, the point is that this kinetic energy can be split into three terms. One, which is the spin momentum interaction. Okay, the other is the Rashba term, and the other is the Zeeman term. This is an exact decomposition, is like a theorem. So this has been largely ignored in the literature, but it is true. Okay, so the spin momentum locking condition means that we can lower the kinetic energy by imposing part of it to be equal to 0. Since it's squared, it's positive, and the minimum is 0. So what's this theorem, so that you understand what I'm talking about? Here is our kinetic energy, repeated once more. And h, small h, is the local field that you may have for some reason here. And this kinetic energy can be written like this: sigma p psi squared plus the Rashba term. This is a three-dimensional integration, but you have the divergency. plus a Seaman coupling, okay? So if I consider just a single layer in space, I have top and bottom, a direction x3, then I can carry this integration here, this divergent term to the surface. And assuming that in the plane I have periodic conditions, I end up with the Rashba term, sigma vector p contracted with the vector x3. Okay, the spin momentum locking condition is nothing but zero helicity state, because if you take the angular momentum of a particle is like that, if you project into the momentum, it goes away the spatial angular momentum, and what you have is just the spin and the momentum. So this is the same things, okay? So now the physics is that that's the kinetic Schrödinger kinetic energy. You can zero the spin momentum locking equal to zero. And the Rashba term also favors that the spin and momentum be orthogonal, not at this level, but it will fix along the x3 direction so that the spin momentum will be like that. So both conspire to the same goal of rendering momentum and spin orthogonal. Okay, so now you go and you solve this equation, sigma p psi equal to zero, assuming that you have a plane. And what you find is this solution here, okay, where you have two-dimensional momentum, okay, but three-dimensional behavior because the wave function evanesces away from the plane in both directions, okay? So this is what is peculiar to this approach, that we have two-dimensional physics in three-dimensional space. Okay, so under this condition and ignoring possible local magnetic field, the kinetic energy becomes essentially the Rashba term, where psi is given by this expression. Okay, and if you feed this expression psi, that the case with k is the modulus of the two-dimensional momentum, you find out that this kinetic energy is exactly V0 hk times number of the states, okay? So this is the origin of the linear Dirac spectrum. And in fact, you have V0, which is an arbitrary parameter here, because this condition does not fix the scale. But when you go here, you have a free parameter that it comes from this volume constant. Okay, so this approach is able to describe the Dirac linear spectrum. So the other interesting thing is that a solution of this spin momentum locking has a local magnetic field associated to it. Okay, this is simple to see. I mean, so that's what I want to show you. You just play around and double this expression here, that's 0, 0, and then if you play around, you see that you have that there is a divergenceless field. Is a current a conserved current? No, it's not. It is the local magnetic field whose divergence is equal to 0. I don't have much time to get into this because time is short, but once you compute this three-dimensional spatial configuration of the local magnetic field, what you get is that you have three-dimensional vortices, okay? The streamlines, they pierce the plane, the layer twice, okay? Giving some kind of configuration like this. This is a cartoon-like, this is an actual calculation done in one of those papers, okay? That you see the presence of these streamlines. So what's interesting about this local magnetic field is that this local field will bring stability to the quasi-particles because it pierces twice the layer, so it's difficult to break them up. Okay, you can see some kind of stability. And besides, if you go and compute the Chern-Simons index, where h hat is the direction of the field, okay, you find out that this is an integer and a non-zero integer, okay, which means that you have topological states. So what is going on in, concerning topology? I have in the x1, x2, say, unit cell, okay, that can be arranged forming a torus. And each point of the cell has a local magnetic field, okay, that is surface of a sphere. So this is a topological state, and the actual calculation gives non-zero solutions, okay? So in case of the two layers, so when you put two layers, then you have two possible states. I mean, here is the cartoon configuration of one quasi-particle. You see, in fact, that the particle, I mean, has some kind of, in one side is a sinkhole of streamlines, the other is a source, okay? So depending how you look, you see a magnetic monopole. These particles, they become magnetic monopoles if seen in one side of the layer, okay? Here I just superposed one layer in the second layer, and you see that this will have a tendency to cancel, okay, here and here, and what I will tend to have here is the same configuration crossing through the two layers. This is one possible configuration. And the other configuration is one that's such that I have here particle with a topological number, in here the negative of the topological number. They are opposite, and they don't annihilate in the middle, so I have another configuration, okay? So you clearly see that you have two kinds of states, which is natural since it's two layers. So how do we work this out? I mean, we just take that previous development and impose that the spin momentum locking condition on psi holds independently. So it holds for layer 1 and layer 2, okay? And if you go to the kinetic energy, which is given by that, okay, you surely can see the presence of an interaction between the two layers, okay? So they are naturally coupled in this system. And now you introduce psi 1 and psi 2 by that expression found before. And what you find is that on the spectrum, I mean, this is the d is the distance between the layers, okay, which has this appearance, k 1 minus e to the minus 2kd, and here the exponential being positive. So it's clear that in the high energy regime, where this kd is very large, k much larger than the distance d, this goes to zero, these exponentials, and what you get is two Dirac linear spectra. You have this, just means that the layers are far away one from each other, okay? But in the low energy regime, okay, where k is much smaller than 1/3d, you have very coupled layers. And if you develop these expressions, what you get is essentially, for one of the branches, a k-squared behavior, and for the other, also a k-squared behavior in the presence of a gap, okay, where this shift is proportional to the distance between the layers, and so is the delta, the gap. So what you have is in the very low energy regime, a shifted spectrum, one quadratic and another shifted here. And in fact, this the effective mass is given by this the Fermi the velocity and the separation between the layers, and you have a natural gap associated to this separation. So if you go and do some very hand wave calculations, take a thickness of 0.25 nanometers, a velocity 10 to the 6 meters per second, Planck's constant, you find that this effective mass is of the order of the electron mass, 10 to the minus 31 kilograms, okay? And you find a high gap of 5 electron volts. So, in conclusion of this talk, the description of a layer is done by Schrödinger kinetic energy, and this is enough to get a Dirac linear spectrum, okay? assuming that you have this spin momentum locking condition. The Rashba term is contained into this Schrödinger kinetic energy, okay? And then you get topologically stable quasi-particles, which are some sort of two-dimensional vortices, okay, in the layers. And the double layer, we find that it displays a massive particle, at least in low energy. So that's all I had to say. I thank you very much for your attention.
Thank you very much for a very interesting talk. So are there any questions? I would have a very naive question, I'm sorry. So like, basically my impression always has been that like, you have to put spin by hand into the Schrödinger equation, yeah? So that's what you do. Yeah, yes.
That's right. I mean, that theorem only holds if the particles have spin.
Yes.
Okay, so it's. I mean, I didn't even put a spin-spin interaction or anything of the kind of spin orbit.
So
I just put the Schrödinger equation, and then there inside the term is the Rashba interaction, as written by Rashba in his paper with Gorkov, because there's no electric field there. It's just sigma vector p. It is contained there. So if you zero the sigma p, which is the spin momentum, make them orthogonal, then your kinetic energy is driven by the Rashba term, plus a magnetic interaction, which I neglected, because I can show that it is small, okay?
Okay, I see. So that's okay. Thanks. So, any other questions? If not, let's thank the speaker again. Thanks a lot. Thanks a lot for keeping up to the time. So it was perfect timing. So we still have a few minutes now. Thank you. And
thank you very much.
Let's try with the next speaker, if he's here. Yeah, and it's Emanuele. Yeah, can you try to share the screen?
Yeah,
let's see.
Let's see.
Oh, perfect. And can you link it in the presentation mode?
Is it working? Yes.
Could you also just check the next slide that it works, just to be on the, yeah, perfect. Okay, so we can go. Yeah.
Let me find the point. Is there a pointer here?
Yeah, we see the pointer and
yeah.
Oh, even this one, yeah. Nice. Okay, so the next speaker is Emanuele Cappelluti, and from Trieste. He will talk about the unconventional hot phonon physics in magnesium diboride driven by anisotropic electron phonon coupling. So, Emanuele, you've got 25 minutes in total, including discussion. So, like 10 minutes before the end of the talk, I will show this, and also I will send you a direct message on the chat. And then 5 minutes before the complete end, I will do the same, but with that. Okay, and okay. So that's yeah. Okay, so please, the floor is yours, please.
Okay, first of all, I would like to thank the organizers for giving me the opportunity to talk about some of my recent research. I'm going to talk about a material that probably many of you know very well. Magnesium diboride was very fancy some years ago, and but mainly for a superconducting property. But I'm going to discuss that even its normal state is very interesting, particularly driven by the anisotropy due to electron phonon coupling, and this can give rise to hot phonon physics, which can be very interesting for many reasons. So maybe anyway, some of you probably don't know material. It's a superconductor with quite relevant, quite high temperature, 40, and it is one of the most diffuse superconductor for application. They do wise from that. It is made by hexagonal layer of boron, just like a graphene or graphite, but there is magnesium within this layer, giving some hybridization between this magnesium and boron. So the electronic structure is like this one. It presents two main features: the sigma bands, which are this one, that are mainly localized in the plane, so they are two-dimensional character, while the pi bands, which are made by pi orbital boron plus magnesium orbital, it has a three-dimensional component. So it, from the electronic point of view, it already presents some anisotropy between these two different blocks of electronic degrees of freedom. And the anisotropy is present also in the electron coupling. So these are the Fermi surfaces. You can see that the Fermi surface of the Sigma bands are mainly two-dimensional. They look like tubes, while these are the three-dimensional part. So if we look at the electron coupling in the matrix of these sigma and pi bands, we have some very strong anisotropy, meaning that the electron coupling is concentrated mainly within the sigma bands, so electron belonging in the sigma bands. And if we look more in detail about where is this electron coupling concentrate with respect to phonon modes, we see that almost all the coupling is concentrated few modes, which are this one at the center of the Boolean zone, and they correspond to the EG mode, which is the one where the two boron move counterphase in plane. This is similar like in graphene. So this complex structure gives rise to multi-band properties of this material. Since there are multi-band, there are also multi-gap. These are being observed, different gaps in different electronic Fermi surface. And superconductivity is known to be phonon-mediating, and there is still a strong intraband. So this, from this is a very interesting complex feature, but if we look at the superconductivity property, then we realize that this anisotropy, it does not play very a role, because if we analyze the temperature with this full matrix, and we just drop all the interband problem, since the coupling is concentrated mainly in one element of this matrix, we are not making a big error. More or less, TC is more or less the same like the full one. So as a matter of fact, the anisotropy does not match much for the superconductivity, but it is still relevant for the normal state, as we are going to see. Because normal state, all transport, electronic optical properties, thermodynamical properties depend on this anisotropy. And in particular, I'm going to show one crucial thing that it is related to this one. This is very relevant now in the recent progress of ultra-fast investigation in kind of pump and probe setup. So just to describe what is happening in this kind of setup, we have a system, generic metal insulator. We shed some pulse that brings a complex non-thermal distribution for the electronic part, some time up just immediately after the pulse. In a very, very short time, the electron try to thermalize among them, so they reach a thermal distribution electron, with very high temperature, because we transfer energy in this electronic block. But still they have a temperature which they are still don't have time to transfer this energy to the electron, to the phonon part, to the lattice mode. And this happens on a longer time scale. They slowly decrease, and transfer energy to the lattice mode. So typically, if we follow the temperature for the electron and for the lattice, we see this kind of scheme, very sudden increase of electronic temperature, then which is not followed by the lattice mode, and then slowly on very long scale, they reach a mutual thermal equilibrium between them. So this is quite a generic scheme which works very well for many materials. There are other situations where things are more complex. So essentially describe this scenario. Is under some condition, this flow of energy is blocked, because the electron cannot really transfer in easy way all the energy to the lattice mode. These lattice modes are not accessible easy, but electron can transfer energy only a few selected modes. This mode then acquire at the beginning most of the energy of the gain from the electron, so they become hot. They mean they have population much larger than all the other lattice modes. So they follow this one. The electronic part is immediately, of course, increase the electronic temperature, and the hot phonon mode follow quite enough the temperature in a very short time. They acquire a lot of energy, they become populated. And only on a much larger scale, they start transferring energy to the other modes. So these are hot modes, and these are cold modes. It's very interesting because in this way we can hope to control dissipation of energy, Joule heating, which is important for planning electronic devices. We can engineer the time scale where all the processes happen, trying to select the time scale, and so on. So it's very useful physics. Now, as a matter of fact, these hot phonon are very known since a lot of time, but the hot phonon is usually associated with semiconductors, or in a few years, for instance, graphene in semi-metals. The reason is due to the reduced phase of space. When you do this pump, you excite particle excitation. In a semiconductor or graphene or graphite, this happens only in the valley, essentially. So only few points in Boolean zone have this particle excitation. So since this restricted electronic phase space, you can exchange energy just to few selected modes. The one with the phonon mode, the one at Q0, meaning that you are scattered within the same valley, or one phonon mode connected to valley. Only these two modes phonon modes are accessible. So they become hot, and this has been experimentally observed, of course. On the other hand, the same scenario does not apply to metals, because in metals we have very large isoenergetic surfaces. Then you can scatter with easily in any part of the Brillouin zone. So all the modes can be excited, and there is no hot phonon bottleneck where you select only modes. So essentially, hot phonon is not observed in metal. Now, the important thing is that MGB2 provides a new possible platform to get hot mode in metal. So, in our knowledge, this is the first metal which presents hot phonons. The reason of that is, again, to the anisotropic electrophonon coupling, because it's true that in principle, you can scatter to any part of it, so you can scatter all the phonons with any Q. But since only few modes have a very strong coupling, in the end, you go and excite only these few modes, because all the coupling is concentrated in few modes. So this anisotropy is the reason of the hot phonon physics in this material, which is metal, which is a completely different, let's say, path than the reason why hot phonon are observed in semiconductor semi-metals. So we did the theory. We want to show on the quantitative level that this is possible, is happening. So we are using ab initio input. This is usual dispersion. We know this, the size is electron phonon coupling, the size of these dots. We divide the full Elias-Ber function in two parts. One which corresponds to hot mode, and we denote a temperature for this hot mode mode, and then we define the other mode, which are the cold. So in principle, this is just a splitting, which is irrelevant if the hot phonon is not happening. It's just a useful tool. It is called the three-temperature model. And once we have this tool, we can evaluate the macroscopic level from ab initio, all the relevant parameters driving the energy dynamics in time. It is related to the specific heat and some electron phonon coupling, which I choose this one. And this thing, everything can be computed. And this is the example of what we get prediction for the possible scenario of pump probe. This shape is the pulse, the pump, this dashed line, And immediately after that, we see that electronic temperature is increasing, but the hot phonon mode are soon acquire energy from the electronic sector degrees of freedom. So they also increase with a very little delay and they reach very high temperature, which can be over the 1000, 2000 Kelvin in a very short delay with respect to electronic part. In the meanwhile, the other modes stay very, very cold. And of course, on a longer scale, in the end, everything gets thermalized, but on a very long scale, which is over the picosecond. So this is a theoretical computation prediction, which sustains the idea that my name is Gibert can sustain hot phonon physics, although it is a metal. Now we can wonder, how can we observe this? We can have a fingerprint or a smoking gun of this feature. There are different ways. One very consolidated is the use of the Raman scattering. We know that the anti-stock mode provides a very good way to estimate the temperature of the modes because the intensity of the anti-stock mode is very sensitive to the temperature of this mode. So in zero temperature, the intensity anti-stock mode is almost zero, but as it increases, this increase. So this is, for instance, the prediction of if we measure the ratio between the intensity of anti-stock with respect to stock, we can easily trace the increase of the hot phonon physics, hot phonon temperature. So these are theoretical predictions which are suggested to experimental groups for a direct observation of hot phonon and MGB2. This is just a feature which is relatively easy because it corresponds to intensity, so it's an integral. It does not require high frequency resolution. If frequency resolution is allowed, we can also look at detailed spectroscopic property of this phonon if we have enough resolution, and we can predict some typical anomalies induced by the hot phonon physics, some softening of the mode in the presence of hot phonons, and a peculiar narrowing of the mode. Although this temperature acquires a high temperature, we predict a narrow mode, which is a bit counterintuitive, but it has a very easy mathematical physical explanation. This is a scenario that we have suggested experimental group in Raman spectroscopy. Another possible way to detect a phonon is in optical probe. This has been actually done in the group by Fabrizio Carbone in Lausanne at PFL. And these are time-resolved measurement of reflectivity. We can see they can see the experimental group that we work together. They can see two typical features, the plasmon associated with the C-axis, which are three-dimensional, and the plasmon associated with this, the electron in plane, which is correspond to the sigma bands. So what they observe is a sudden increase of the kinetic energy of the sigma bands, which is not followed by the corresponding increase of the kinetic energy of the pi bands. And after 200 femtosecond, they start redistributing. So the kinetic energy of sigma band decrease and the kinetic energy of the pi bands increase. What it is passing in this one is that in this initial region, there is an increase, a blue shift of the kinetic energy. This does not have any possible explanation within the conventional scenario, because increasing the temperature would correspond to a smoothing of the feature, so it would correspond to a reduction of the kinetic energy. And so the pulsing feature in this one, why there is this increasing? So this we rationalize this increasing in terms of the, it's not moving anymore. Okay. In terms of effect of many-body physics, electron phonon coupling is described by this kind of diagram, which is the same responsible for superconductivity. And it is very known to give renormalization of the bands for the for the real part, but one can realize this term in a system which have very strong particle asymmetry, like 5 sigma bands in this material. They are almost completely filled. This gives also a shift of the position of the band, a shift up and down the band with respect to chemical potential. This is usually not observed particularly because under steady condition, this shift is balanced by a corresponding shift of chemical potential. But this has a relevant effect under out of equilibrium condition when there is no time for redistributing particles. So we analyze this term, this shift in terms of theoretically, we can in principle introduce different temperature, and we can theoretically we can switch each temperature by putting 0. We realize that this shift is very sensitive to the temperature of the phonon. It's not as sensitive at all on the temperature of electrons. So and this is very it depends a lot. So this means when we applied hot phonon physics, we have a sudden, very strong increase of this shift, precisely with the sign that corresponds to an increase of kinetic energy. So this increasing of the kinetic energy is driven by this hot phonon driven shift of the bands. Sigma bands correspond in relation to the pi bands, and this has been, I mean, direct assessed experimentally by the group of Fabrizio Carpone. So typically the scenario is this one. This is before the pump. When we pump, there is a shift of this band, which corresponds to an increase of kinetic energy, which corresponds to experimental to this part of the experiment. And on a longer scale, now charge start redistributing among the different blocks, sigma bands and pi bands, and we have an increase of the kinetic energy of pi bands corresponding to a reduction of the sigma bands. So this theoretical scenario explained in a very well the experimental scenario. And finally, so far I try to discuss different possible experimental observations, but overall they are all related to electronic counterpart. Is there a way to see host phonon directly in look at the lattice mode? And I'm going to show that this is possible by looking at lattice dynamics. This is the idea is based on experiment that already been done in NGP2 in a group by Antonio Bianconi and Gaetano Campi a long time ago, using diffraction. When you collect diffraction, you can do Fourier transform to look at the distribution in real space, and you see many peaks. Each of these peaks correspond to the lattice dynamic of the couple of a pair of atoms. So the first peak corresponds to the lattice dynamic of correlated lattice dynamic of the two boron in plane. The second peak corresponds to the dynamics of one boron, one magnesium. So what it is conveying, this spectrum, the width of this each peak corresponds to the correlated dynamics of these two atoms. And it is possible to define experimentally a correlation factor by use of property, which expresses the probability that the two atoms moves in phase or counter phase. In under steady condition, all the modes are more or less excited, so they average out, and I mean, in lattice dynamics, this mode that we are talking about, this E2G in play, is just one of them, one of many, so it does not play a particular role. All of them are thermally excited, and the total correlation is about 0. Not 0. But if there is an imbalance, if we are able to increase the correlation, we will see a change of this correlation factor. And precisely this is the idea that comes out. When we have hot phonon in these two modes, we expect that these two modes are moving counterphase. We expect a sudden anomaly in this correlation factor. In particular, we predicted a strong depletion of correlation factor in time scale, which correspond to the hot phonon physics. So we can predict the pressure, and this shape in time will provide the useful way to probe the time scale of phonon physics. So this is also a possible experimental scenario that we are trying to experimental observe in collaboration with the Gaetano Campi. So I'm coming to conclusion. I want to show that MJB2 is very interesting, not only as a superconductor, but also for its normal state. In particular, due to the anisotropy electron phonon coupling, we can predict that hot phonon physics is sustaining this material, which will make it the first metal with hot phonon properties. We provide the detailed microscopic theory, and okay, I try to present an overview of the possible experimental prediction. And okay, these are a list of collaboration collaborator that I work on this team on this topic, and a few publication. In particular, there's a review which is appearing just in these days in the Progress of Science. Thank you very much.
Okay, perfect. Thank you very much for a very nice talk. So, are there any questions we've got?
Shall I stop sharing?
Yeah, you can still keep it because maybe just in case there's a question, unless also people can just look at the papers. So it's good to leave the papers for a second. Maybe.
Okay.
Yeah, it's good. You know, it's a good advertisement. So.
The conclusion, better the conclusion.
Yeah, it's okay. So, any questions? I can't see any, but okay. Looks like everything is clear. Okay, so in this case, I think I suggest, because anyway, we are actually a few minutes over time, so I suggest that we move to the next talk. So the next one is by Łukasz Plucinski. Yeah. So please, yeah, can you say something? I can't hear you. Maybe you unmute, or I can only see your screen, Łukasz, but I can't. Or I see you.
Yeah,
can you unmute?
Can you hear it now? Can you hear it now?
Yes. Now I can hear you, and can you please show?
Is the audio okay?
Yes. Yeah, at least I can hear, so I hope the others as well.
No, sorry, maybe I closed the window.
Yeah.
Okay, because I couldn't see that share button. Okay.
Okay, so please share, and can you go full screen, and we check.
Does it work?
Yes, and can you go to the second slide, just in case?
Yeah.
Fine.
It seems to be, yeah.
So it's okay. So basically, I will tell you, you know, like with all of the others. So like 10 minutes before the end of the discussion and the talk, I will show you this on the video, and also I will send you a direct message. And then 5 minutes before the total end, I will do the same, but just like that, and 5 minutes message. Yes. Okay. So okay. So let me introduce you very quickly. So the next talk is by Łukasz Plucinski, and he will talk about imaging spin textures of novel quantum materials using ARPES, actually spin polarized ARPES. Okay. So please, the floor is yours.
Thank you for the very nice introduction, and I would like to clarify that I would love to be in presence in Rome, or near Rome, where the conference is, as far as I understand. But I just got a beam time here at the advanced light source in Berkeley, so I'm sitting in the guest room and at the guest house here, instead of being in beautiful Rome. But nevertheless, I'm happy to give that lecture online, and the lecture or the talk actually will be on imaging spin textures with spin ARPES. But because this is a rather short talk, 20 minutes, I will basically focus on a single material, which is tungsten ditelluride, on which we made recently experiments. So let me start with introducing people involved in this study. And here is a recent photo of my group. And this is mostly the work of Tristan Heider, who is a PhD student in my group. And we are in the Institute PGI6 in Forschungszentrum Jülich. This is a large government laboratory in Germany near Cologne. The institute director is Klaus Schneider, and we have support, theoretical support from the neighboring institute in Jülich, mostly from Gustav Pillmeyer, and beautiful one-step model calculations from Jakub Schusser from Czech Republic, from Pilsen, and nowadays he's in Würzburg. So very quickly, I would like to introduce my system. So we have this is the system in my lab in Jülich. We have a conventional hemispherical analyzer. This is, I think, clear for everyone who does ARPES from MBS. And this one has the deflectors in the lens. So we can map the Fermi surface in both directions without rotating the sample, which is very important. We have here MCP, where we can make these beautiful images of, for example, topological insulators. This is nowadays a sort of routine measurement. And part of the beam is here directed to the spin detector, where here in this region, do you see my mouse moving? My mouse pointer?
Yes, yes.
Okay, good. So I don't know if I can pointer options. Maybe that is going to be better. Maybe a little bit.
Yeah, it's
here is the tungsten crystal with deposited iron film on it. So basically, it's iron film oxidized a little bit for protection, and we can magnetize that iron film in different directions to measure the spin expectation values along different directions. And in this way, we can map these beautiful Fermi surfaces, for example, of this is in the case of one of the topological insulators, using spin detector. And I will tell you a little bit more detail about that, but I would like to continue that this spin detector is from the company Focus. It's called Ferrum. And our main light source, the most important one, is nowadays 6eV laser that can be focused pretty well, and it has very high intensity. We can cool to 10 Kelvin, and we also have helium and xenon discharge sources. So let me tell you a little bit about the spin. How do we measure the spin textures? In this system, we measure them point by point. You can see pixels here, actually. And this is by scanning this lens. So it really moves like tak, 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 tak. This lens is scanning. The sample is not moving. So the spot stays exactly, the light stays exactly on the same spot. And this way, these spin textures are being measured. In this case, this is for the spin expectation value vertical here in this geometry. Okay, I just want to advertise that a similar setup is available at the beamline in Krakow, at the Polish synchrotron in Krakow, in Solaris, where you can now apply for the beam time. Okay, so let's move quickly to tungsten ditelluride. I'm not sure if tungsten ditelluride has been introduced in that conference so far, but anyway, I will go through it quickly. This is one of the most interesting quantum materials in recent years, and the recent interest started with that work on non-saturating magnetoresistance, which doesn't saturate up to something like 60 Tesla or even more. And then there are interesting properties in few layer tungsten ditelluride, and there is also a possible Weil type 2 phase, and all of these things are somehow related to the band structure of tungsten ditelluride. In tungsten ditelluride, you can see this is a layered crystal. It's not very symmetric. It is less asymmetric, for example, than moly disulfide or tungsten diselenide. These atoms are sort of in strange positions, but nevertheless, it's a layered crystal. And it's a semi-metal. You see this, there is the electron pocket and hole pockets. In between them, there is a surface state. And now, if these electron and hole pockets would touch each other, then there would be here a Weil type 2 phase, and then that should show some Fermi arcs. But this is probably not happening in pure tungsten ditelluride, although it is not clear, not fully clear yet. And the Fermi surface would look like this. You would see these electron and hole pockets and a surface state in between them. So here I listed, of course, we are not the first group to measure tungsten ditelluride. There is already many papers on it. I listed some of these papers. here, and I hope that someone turn on the microphone. Okay. And I hope that our study contributes significantly to, as a continuation of these studies. I would like to introduce a little bit symmetries of tungsten ditelluride, because what's one interesting thing in tungsten ditelluride is it is a material of a very low symmetry. So you can look at the space group and there is only 4 symmetry operations. Really, there is only 3 because identity is a trivial one. So there is one mirror plane, and there is one sort of quasi-mirror plane, because it's a mirror plane with some sliding. And let me explain you here that this minus y is what would be my mirror plane, but there is some sliding, 1/2 plus x and 1/2 plus z. And that 1/2 plus x is irrelevant for ARPES measurements. But that one, because, in a reciprocal method, which is more or less like, the sliding movement of the sample, it doesn't change anything. However, this 1/2 plus z, it does matter because it is basically jumping from one adjacent terrace to the other. So basically adjacent terraces in tungsten ditelluride, if you have a surface, are connected by the my operation. So my is not a symmetry operation of the sample together with the surface, but if you jump to the adjacent terrace, they are connected by this operation. And there is also some other symmetry operation. This is our spectra. One important thing, very important thing, is that the top and bottom surface of tungsten ditelluride, when you prepare the crystal of tungsten ditelluride, you have to cleave it. We do it by cleaving to the tape. They are not connected by symmetry operations. They look here in this picture more or less as if would be the same sort of, and they could be connected, but they are not. It is very asymmetric material, and the spectra from the bottom surface and from the top surface are actually pretty different. So we measured, here I will present the data from the bottom surface, what is conventionally called bottom surface. They look like this. These are our spectra. You can see they are extremely sharp. This is spin integrated data. And with P and S polarization, you can see that there is some changes in the intensity, basically probably related to the probing different orbital characters. And here I explain which part of the Brillouin zone we are probing here. We are probing this part of the Brillouin zone, this portion of the Brillouin zone in these pictures, because this is the portion that we can map with our scanning lens without rotating the sample, and which is very important, as you will see in the next slides. And we are very proud of this data. And tungsten ditelluride is not easy to measure such sharp spectra from tungsten ditelluride. And the previous sharpest, I think, was from the group of Felix Baumberger, and which you can see here. And we think we are significantly sharper than that. So we probably got more lucky with the quality of the sample. Okay, so but this is not this is here the most important experimental result of this study, because we could not only measure the spectra here with the regular ARPES, which is relatively fast and maybe not easy, but it's just maybe 10 minutes to do that. But we could measure the spin polarized Fermi surfaces from tungsten ditelluride, and they are presented here. And you can see there are 2 images here, and these 2 images are measured on different spots of the same sample, of the same cleave. And you can see that each of them is very asymmetric, but they are related to each other by this my symmetry. You can see this red portion here in the other image is here. So this picture and this picture are related to each other just by a visual inspection. You can easily see it. They are related to each other by this my operation. That means that, this suggests, according to this symmetry analysis from the previous slides, that they are coming from adjacent terraces. So they are coming from different terrace termination on the same, on the bottom surface, but on different terrace termination. And to convince you that this is possible in such crystals, this is a photo of our sample. This is 1 by 1 centimeter here. So this portion here that is shown here is a couple of millimeters. And if you look closely, you can convince yourself that there is very likely these macroscopic terraces on this sample. So with the beam spot of 50 micrometers, you cannot avoid to address single terraces in such a sample. Okay, but there is one important and interesting thing here. In the initial state spin texture, which is calculated here by Gustav Pillmeyer, this kind of asymmetry cannot take place. So you can see what is blue here, it is blue here. It has to be like that in the initial state spin texture. And in the ARPES spin texture, this symmetry is broken. So the rest of my talk will be, you know.
Are you advancing?
Excuse me?
I cannot see advancement. I'm sitting on the same slide all these minutes.
Can you see
You're
the slide?
moving slides or not? I don't know. Yeah, finally.
I can see I see changes. Why?
So this is the previous slide.
Yes.
You see it?
Yes.
It's the one with the crystal lattice. Here. Do you see it? Does it work?
Yes.
Slide number 7. And now this is slide number 9. Here. Do you see this?
Yes.
Okay, so it works.
I think it works. I don't know. I
Okay.
think so.
And now I'm making animation, and this is slide number 9, and there is here this theoretical spin texture.
Mm-hmm.
Okay, so I can continue.
Are you okay? I mean, to the participants, is everybody
Yes.
fine? Yeah. Okay. Thanks.
Okay,
Thanks.
so you can let me continue. I'm sorry for this. I don't know. On my side, everything looks fine. Maybe it's internet connection. So you can see that cannot take place in the initial state spin texture, but there is a symmetry in the photo emission spin texture measured by photo emission, and the rest of my talk will be targeted on explaining that. But before I go there, I would like to point out some technical, very important technical remark on how do we measure these spectra, how to convince ourselves that this is really real, actual results. So what we do, and because you have to be very careful when you measure spin polarized spectra. The problem with spin polarized spectra is that you're making a difference of two signals, and these two signals are measuring by remagnetizing that target in the spin detector that are typically not very much different from each other. So this is how one of these pictures, blue-red pictures, is made. Each of them is made out of the two measurements with the target in the spin detector magnetized up and down. But it's not done like this, that first this picture is measured and then that picture is measured. That would not be very good, because maybe it takes half an hour to measure each of them, and maybe something drifts, something changes, and this would then contribute to something that is called instrumental asymmetry in these measurements. Instead, we measure, first line of that picture, then we remagnetize the target, and then measure the line of the second picture, and then you measure the line by line. The second thing that we do, we continuously monitor the laser intensity. The laser is not very stable, and you can see it varies for this measurement, like maybe 10 or 15 or 20%, the intensity. And part of the laser beam, when we polarize it, it is taken to the photodiode and then to the voltage to frequency converter, and it's measured simultaneously by the same counter card that is used to measure this the spin polarized signal, and then it's normalized by that, which is okay, because this variation is not that high. All these things are very important to make a reliable measurement, and then we can make some quantitative analysis of this measurement, and you can see that you can average the spin signal over these squares here, and you go in this direction in this case, and in that direction in this case, and then you can see that the spin polarizations are on top of each other, and that sort of confirms that these two images are connected by the mirror plane operation. So they are coming from the adjacent terraces. Now, there is a question why in the initial state this asymmetry is not possible to have, why it cannot happen in the initial state. And then for the surface states that only have parallel momentum, you can make such a construction. This is the Brillouin zone, and you can think how the spin texture will transform through these symmetry operations. Tungsten ditelluride is a non-magnetic material, so time reversal symmetry is conserved. And then it has that single mirror plane, this mx mirror plane. And then the spin is an axial vector. An axial vector is not like a polar vector. It transforms through the mirror plane in the peculiar way. So for example, if it's perpendicular to the mirror plane, it doesn't change its direction and so on. So it's different to the polar vector. So let's first go to some generic k point and assume some generic direction of the spin. And then transform it, go to the minus k vector, yeah, which is the time reversal symmetry. Then the direction of the spin has to reverse because it comes from some sense of rotation, so it reverses. And then through the mirror plane, the component perpendicular to the mirror plane doesn't reverse and the parallel reverses, and you end up with something like this. And that means that the SY component here, the vertical one in this slide, cannot change between these 2 points. And this is exactly what has happened. This is exactly what happens in this picture. All the top part of this picture is the same as the bottom, is the mirror image of the bottom, because that has to happen for this SY. But that's not what, that's exactly not what happens in the experiment. Okay, so now the question is, which symmetries are broken in the experiment such that this can happen? And this is the slide I showed at the previous superstripes in Erich when I discussed a little bit these symmetries in spin ARPES. I just want to remind you that there are differences when you use p-polarized light or s-polarized light in ARPES. The difference is that you have to consider in the matrix element of ARPES electric field of the light. And you can see for this for the p-polarized light, it lies within this plane, and for the s-polarized light, it lies within that plane. What it means is that, excuse me, if you have that mx mirror plane, that means that in this s-polarized light case, this mx symmetry won't be broken by the ARPES experimental geometry, while in the p-polarized case, it will. So this is important here. And now we have these one-step model calculations of tungsten ditelluride from Jakub. And let me explain you a little bit what is plotted here. So you have the panels, the 2 top panels are for the p-polarized light and 2 bottom panels are for the s-polarized light. Now each left and right panels are basically the same, but they are plotted in a different way. In the left panels, pure spin polarization is plotted, and in the right panels, spin polarization is plotted, but also together with the intensity, using this very special color map, because it can be that, for example, in this region here, you see there is very little intensity theoretically predicted, but there will be some significant spin polarization. But of course, in the experiment, you're probably more interested in this one because spin polarization, you need to have some intensity to measure the spin polarization. Anyway, what is important is that there is, in both of these images, this symmetry of the initial state is not present. And you can see that with the s-polarized light, that doesn't break that mx mirror plane, you also don't have that symmetry. So the top part and the bottom part of the image is not the same. What you have is that you indeed have that mx mirror plane, because you see that the left part and the right part of the image, if you think about these actual rules, it's anti-symmetric. So what is blue on the right side is red on the left side. And that means that this calculation is actually well converged, is a very important and good sign that everything is okay. But we don't have that symmetry. So that means, in my opinion, that what it shows is that it's a breaking of time reversal symmetry in the ARPES measurement. So now I'm almost at the end of my talk, and I know that I knew that there is no way to explain you in detail where this effect is coming from. But what we have done is that we conceived sort of toy model of this situation, and I don't expect you to understand, although this is really like elementary, matrix element of ARPES with the free electron final state is basically a Fourier transform of the wave function. So it's not that complicated. But what you can do is that you can conceive a a minimal tight binding model, sort of assuming, two orbitals and two different atomic sites. And then you can show that the emission to this K point and to this K point, which is the emission for some angles in ARPAS, they can be, the wave functions in these 2 points can be related to each other because there are these symmetry operations in the initial state. And then you can calculate the matrix element. And what you're going to find out is that the matrix elements emit to this point and to this point are of course, very similar, but they have these different phase shifts related to the interference because there are different atomic sites in tungsten ditelluride and there is little symmetry. And these interferences are the effects, are the reasons, the sort of microscopic reasons for these asymmetries in the ARPAS spin textures. And actually it is quite clear that these kind of effects should appear in in many materials where in many materials of low symmetry. Okay, so I'm happy to explain that in any detail, but I know that there is no time during this talk for that. So with that, I'm at the end, and I would like to thank you for your attention, and I'm happy to take questions. Thank you.
Thank you very much for the talk, for the interesting talk. Are there any questions? So you don't have to raise your hand, just speak up if anything. Was it all clear? Didn't see any questions. Okay, so let's thank this speaker again, and let's now move to the last talk. Thanks a lot again. The last talk is by Salvatore Macis. Yeah. Hi, Salvatore. Could you share your screen? And
can you see my screen? I will.
Yes. Can you go full screen?
Okay.
Okay, yeah, it's perfect. Okay, so you've got 15 minutes in total. So just before, like 5 minutes before, I will show you this, and I will also send you a direct message. Okay, and okay, so let me just quickly introduce you. So the next speaker is Salvatore Macis, yeah, if I pronounce correctly, I don't know. I'm sorry.
No.
It's yeah, from La Sapienza, and he will talk about the infrared plasmons in this cobaltate. Yeah, please, the floor is yours. Please start.
Okay. Thank you very much for the presentation. So I'm postdoc at Sapienza University. Today I will discuss briefly this type of material, which is palladium cobalt oxide, its properties and how it was grown as a film, and how was made a sample patterning for these samples in order to study the excitation of surface plasmon polaritons on this system. So we will see the characterization, simulation modeling of this excitation and the optical response, then to move to the results and conclusion that we see in this work. So this type of oxide is pretty interesting. It's part of the so-called group of the Laphosite, which are this type of layer structure that are composed by these cations, in our case, palladium layers, combined with the octahedral of cobalt oxide layers. The interesting part of this material is mainly in its electronic properties. There's a really high conductivity, the highest in the metal oxide, which is 60–70% the one of the copper metal, and also has a really long free path. Obviously, I mean, we take a bulk material at low temperature. But the interesting thing also is that it has a relatively low free carriers at around 30% of copper, of the one of the copper. In our case, we studied thin films of this material, and the first one that was able to grow thin films by molecular beam epitaxy is the group of Shunxin Ho at Rutgers University, which we have a collaboration for this project that prepared the sample. In order to grow this type of thin films is necessary to grow with alumina substrate. And after a grow procedure at 300 degrees Celsius temperature is necessary annealing treatment in oxygen environment of above 500 degrees Celsius in order to achieve good crystallinity and also reduce the resistivity, increase the conductivity of the film. In our case, we used really good thin films of 100 nanometers thickness, and that were grown at with an annealing temperature of above 700 degrees Celsius. And in our case, we want to study a type of excitation called surface plasma polaritons. This type of surface excitation are really interesting for different reasons. The one problem that is only the light cannot excite this type of excitation. In order to generate is necessary a momentum transfer to this surface excitation. In order to do that, we need a patterning of the film on the surface of our sample. So as we can see, this is due to the energy momentum distribution of this type of excitation that as we can see here, there is a mismatch of the momentum between the light at a certain frequency and the momentum of the light. There is a mismatch that the one the momentum of this excitation. We need to transfer this momentum G. In order to do that, we will use a simple structure called the ribbon structure that is made of stripes of equal stripes of material, in our case palladium cobalt oxide, and same with the stripe with no film on our substrate. The periodicity of the structure will be, we will call it 2W, where the W is the width of a single stripe. And the transfer momentum in this case is 2 pi over the periodicity, so in our case is pi over W. This type of surface with this patterning can be excited, and they live in this interface between the metal, in our case this metal oxide, and the electric, that in our case can be both the aluminum substrate or the air on top of the film. These are the patterning of the patterning procedure of the film. So in this case, we work in a collaboration with the Istituto Italiano di Tecnologia on Genova, and the group of Andrea Toma that made this patterning. In order to pattern this the sample, was used mainly the electron beam lithography technique, which means that the sample is coated with a resistor, and then after patterning with this electron beam lithography and different type of chemical procedure, we are able to obtain this ribbon structure with these stripes. In this image, you can see 2 optical images with different width, and the clear part is the palladium cobalt oxide, while the darker part is the alumina substrate. With this technique, we were able to prepare 3 or 4 patterns that we study, one at 5, 2, and 1 micrometer of width of the stripe. And the one at 0.5, so 500 nanometer, this technique didn't give good results, so it was used another type of technique called ion milling with the use of focus ion beam setup. They were able to very slowly prepare this smaller type of ribbon structure. In order to characterize the optical response of the both not patterned P film and the different type of patterned film, we use two different setups. One is an interferometer in the range between 8 Hz and near infrared spectral range, so we can cover all the infrared region. And this was equipped with a Vertex 70V interferometer, equipped with a Bruker infrared microscope. This was important in order to focus all the radiation in the small region of the patterned film. And also, in order to study, mainly for the non-patterned sample, in order to study the higher frequency region, we use a JASCO spectrometer that works between the near infrared to the ultraviolet region. These are, I show the sample characterization. We start for characterizing the non-pattern film that you can see here on the left on the bottom. So this is the wide range spectra. It covers the infrared part and the visible ultraviolet part. We can see that we have a high reflectance of the sample that slowly decreases. Then we have the interband and all the interband and over the gap region, over the plasma frequency region in the ultraviolet. We analyze this type of response reflectance. Mainly in all this work, we focus on studying only the reflectance, because in our case, due to the metallic behavior of our film and also the alumina substrate, the infrared region, in the infrared region, the transmittance is almost zero, so it's not usable. So all the study was performed studying the reflectance of the sample, which is much more trickier also when we want to isolate the plasmon, surface plasmon response. So we perform the measurement on the non-pattern sample, and using data analysis, using a fitting, the Drude-Rollens model, we're able to fit both the substrate and also the film. And in this way, we are able to extract the optical properties of only the film. Studying all these optical properties is important not only for studying the film, but also because we want to simulate and model the optical response of the sample. So the optical properties of the film are needed for those parts. In the right, you can see the response of the pattern film. There are the spectrum measurement were made by polarizing light before impinging on the sample, and we can see the true response. The one with the polarization parallel to the ribbons, so the stripes, we don't see the plasmon excitation, but when we use a polarization perpendicular to the ribbon, so we can transfer the momentum to the excitation, we can see this type of structure that is related to this plasmon excitation. And also we see how it moves to higher frequency when we reduce the width of the patterning, as we expect from the theory. This is another image that we can see two sample pattern. As we change the polarization, you can see how it reduces the metallic behavior of the film, and it's increased the surface plasmon polarity response. This is for two width of 2 micrometer and 1 micrometer. So as I mentioned, we also study with both simulation and modelization this type of response. In case of the simulation, we used a COMSOL software that where we able to model the with a 2D model our system. So you can see this simple image describe the model that we use. So 3 regions, 1 for air, 1 for palladium cobalt, and 1 for the substrate. And using this simulation, we were able both to obtain the reflectance spectra of the samples, but also the electric field map around our structure. These were very important also to extract the field enhancement in these systems. For the modeling, we use starting from the Fresnel equation for with a thin film approximation, we're able to extract both the energy momentum distribution of our surface plasma polariton, but also model reflectance using, in our case, half of the sample reflecting from the pattern film and half from the alumina substrate. These are a comparison of the results that we have. So these are some stacked spectra. In blue, we have the data that are just plotted in the main region. So we didn't plot the phononic parts. And we can see that match very well, mainly obviously the simulation. And also in this case, we model one surface plasma polariton at a time. Why I say this? Because as you can see, we have two dip in our spectra. The first one is related to the metal sapphire, so the substrate interface, which is because the sapphire has an higher index of refraction than the hair, we expect this plasmon excitation at a lower frequency. And this second dip is related to the interface between the metal and the hair. So we are able to see, to model separately these two surface plasmon polaritons. And in this case, I show only one type of model with the interface between substrate and metal. You can see this works for both these width that I show, 2 micrometer, 1 micrometer. So this is at higher frequency for both interaction. The only thing that for the air sapphire air metal interface that this modulation given by these plasmon polaritons is a little bit shallower and much more larger. This is a little bit tricky when you have to assess value of the energy of this excitation. These are the distribution, the curve distribution between energy and momentum that we obtain from our data, model, and simulation. So these were obtained for all the three different spectra I show you, and everyone for our 4 different samples. This is related to the interface between the metal and the alumina. And as you can see, there are pretty good agreement. Also, I show the field enhancement, as I mentioned, from the simulation, we obtained the field enhancement value. And you can see here in the green, so we are ranging between 10 to the 50 and 2 times 10 to the 50 of enhancement field. In order to assess the field enhancement, we studied the electric field distribution inside a region, a certain region, and averaging on this circular region, which is which has a radius that is matching the full width of maximum of the electric field distribution. This show also that these are really high value of electric field enhancement. In some cases, for us, we see that it was higher, slightly higher than the gold similar structure made of gold. And this is very interesting because this oxide can be used both as a sensing structure and also for non-linear spectroscopy in this infrared and terahertz region. These are the spectral distribution, the distribution of energy momentum for the, in this case, the interface between air and the metal, which are at higher frequency, was, as I mentioned, slightly difficult to, because of they are much larger and shallower. So to sum up, this was the first plasmonic excitation that we know of in this type of material, thin film material. We were able to estimate this value, the distribution, plasma dispersion for these systems, and we study also the strong field enhancement through the simulation, which is very interesting for future application. I want to briefly thank all the people that work with me in my university, and also Silvia Tofani made the simulation, and the Russian University for the sample prepared. Thanks for attention.
Thank you very much. It's exactly 15 minutes past, but if I Are there any questions? It's okay because it's the last talk.
Yes.
I didn't see any. Okay, so in this case, well, thanks a lot for the nice talk. And I understand that we close this session unless from the organizers there's still a message, but I didn't see anything. So I understand that tomorrow we either meet online, or if somebody does a test, then we can meet or in person. Okay, I mean those who are in Frascati. Okay, so thank you very much, and let's close the session.